Shall I share the screen?
1 minute. They will introduce you after that. Let them introduce you.
Alone, we can do so little. Together, we can do so much. Good afternoon and a very warm welcome to the second day of Symposium on Geospatial Intelligence, organized by IEEE GRSS Bombay Chapter in collaboration with IEEE GRSS Kolkata Chapter, in association with Don Bosco Institute of Technology, Ram Rao Adik Institute of Technology, Srimati Nathibai Damodar Thakurse Women's University, Anjuman Islam University, and Amity University. A very warm welcome to all the dignitaries, professors, participants, and core GRSS committee members. I'm Frizel Fernandez, one of your hosts for this event. So without any further delay, let's begin with the proceedings of the day. I would now like to invite Ms. Dipali Kayande, Assistant Professor, DBIT Mumbai, to introduce our speaker, Dr. Lisa Armstrong. Over to you, ma'am.
Good afternoon, everyone. So I'm here to introduce Dr. Lisa Armstrong, who works as an academician in computer science discipline at ECU since 2002. Dr. Lisa founded the Digital Agriculture Research Group and has been a member of Center of Ecosystem Management and Center for Innovative Practice at ECU. She has a PhD in Agricultural Science and Master of Science Software Engineering. She has supervised a number of PhD and research master students in Australia, India, and Thailand. Lisa is an internationally recognized researcher in digital agriculture. She leads several international research collaborations in Asia. She has published widely in the area of computer and agriculture since including over 100 publications as journal articles, conference papers, books and books chapters, industry reports, and conference proceedings. It's our pleasure to have Dr. Lisa with us today. So I welcome you, ma'am, on behalf of the whole team, and over to you for your talk. Thank you.
Good afternoon, everybody. I'm quite happy to be able to give this presentation to you all. I'm missing India, having not been able to visit India for 2 years now because of the pandemic, but I hope this presentation will be interesting to everybody. I'm just going to share my screen now. I can. I hope you can see that first slide. So the title of the presentation today is Digital Agriculture, Securing Our Food Futures. And this is an area of research and interest that I have in both social and research aspects. So a bit of an outline of the presentation today. I'll be giving an introduction, and then I'll talk a little bit about food security and food futures, a little bit about what digital agriculture is, and then I'm going to provide some case studies, and the case studies are around the research that I've been involved in, which relates to the use of drones and sensor technologies, data workflows, decision support tools, sensor networks, vertical farming, information data security, and some training and upskilling work that we've been doing, and the key messages, future directions. The focus of this presentation is really around some of the new kind of geospatial technologies and computer technologies that we're using in our research. So the current food crisis is something that we are all aware of. We all know about the issues of COVID and the terrible number of people who have been killed by the COVID pandemic. But there is also another crisis within the world, and that is in terms of how we can feed the world's population. It's estimated that 9 billion mouths will need to be fed by 2050. And in terms of the food production systems that we create as part of our agriculture, it's they are going to need to support 3 billion people globally and try and bring those people out of being in either malnourished or in poverty. So the food production systems that we do create, they are what is going to allow the world to improve in terms of the livelihoods of people and bringing people out of poverty. In terms of the COVID pandemic, it actually has led to an increase in the number of people being in poverty. It's estimated to probably 124 million people in 2020 were put into poverty, specifically because of the COVID pandemic. And it's projected that 840 million people will still be living in poverty by 2030. And with the COVID pandemic, that will increase that number. The UN, which provides or helps manage the production and the study of food across the world, has the World Food Programme, which provides a number of avenues to prevent famines and increase the amount of food that's produced. And it produces a really nice, colourful, what it's called a hunger map. But the more colourful it is, actually the worse it is. So the hunger map is really saying what percentage of population within these different countries are experiencing chronic hunger. And you can see that in the areas which are dark red or light red or orange, these countries are experiencing maybe up to a quarter or a third of their population being hungry or malnourished. So this is principally in the areas of the sub-Saharan Africa, some areas in Afghanistan, Mongolia, some areas in Southern America and Central America, and places like Somalia, Eritrea in the Eastern African equatorial zone. So, and also even in places like Indonesia and some of the Pacific Islands, they're still experiencing some levels. Just in September this year, there was quite an important global conference run by the United Nations, and it was the United Nations Food System Summit. And there was more than 150 nations attended with the goal of trying to work out how food systems could be improved to drive the success of sustainable development, the Sustainable Development Goals, which the United Nations are trying to achieve by 2030. And that basically is to improve the amount of food that is available for the population and to reduce hunger. And one of the really amazing ladies that is part of the United Nations, she is the Deputy Secretary General Amana J. Mohammed, and she said something that is really important for us all to pay attention to. She said anything we must do always must include, in terms of our our food systems needs to include smallholder farmers and the Indigenous people, and especially women and youth, and the role that they can play in improving food security. So the term food security has been around for quite a number of years. It was first talked about by the Food and Agricultural Organization, which is part of the United Nations. And it states that food security can exist when all people at all times have physical and economic access to sufficient, safe, and nutritious food to meet their dietary needs and their food preferences for an active and healthy life. So there's lots of different facets which make up whether a nation has food security. And it relies on, there's basically 4: availability, access, utilization, and stability. So availability relates to how much the country can produce domestically and how much they has in terms of the food stock, how much is stored, and also how much they may need to import. In severe cases, availability may also be in the form of food aid, so from other countries. So even if the food is available, it also has to be accessible to all the different communities. So this factor about accessibility relates to political and economic and social factors. So whether it's being equitably distributed to all different communities, whether the markets and the infrastructure is available to provide access, and whether that food is actually affordable by the average person, and whether that person has enough purchasing power to be able to access that food. The other aspect is utilization, and this has to do with whether the food that is available and accessible is actually safe for eating, whether it's good quality in terms of nutrition and safety in terms of whether it's not damaged or rotten, whether it's got good nutritional value, whether it's been prepared properly. And that is really to do with a lot of things as to how we store the food and how and whether we're wasting a lot of food through not utilizing it in time. So those 3 factors all get together to be able to determine whether it's the food system or the food security is stable. So if all those factors work well, then we'll have a stable food security system. And there's also other factors which we need to consider, which is trying to reduce the risk of loss. And there's other factors such as economics and political systems that can determine the stability of the food system. If there's a war on, or if there's a major drought or cyclone, all these extra factors is going to reduce that stability. So there's lots of different factors which are challenges to how we can secure our food. And the main problems is it's just an underinvestment in rural areas. There's unfair market conditions and poor infrastructure or access to technologies. And there's high production and transport costs. There's some gender inequity as well. There's other factors such as wars and other conflicts, pandemics, natural disasters, all they limit the amount of food. If you're having to deal with those other things, then you're not really worried about producing food. You've got other priorities. The There's also the issue of if you do have to use land for agricultural production, there's also that issue of are you deforesting the natural lands or creating environmental degradation or loss of biodiversity. And in some cases, about food security, it may be dependent on government aid and the ability of government to provide. So in terms of how things are working at the moment, we need to consider about what's going to happen with increasing climate change. This is the big factor which is going to be determining how things are going to turn out in the next 20 or 50 years. So we're trying to see whether we can match the amount of food production that we have to what will happen if we have only a small change due to climate change or an extreme change to climate change. We're trying to get to a point where we are in this safe zone where we have enough food being produced, and with the increase in the population, we can still be able to stay above this line and be able to produce enough food. At the moment, we're kind of around here, even with the low level of climate change, we're still around here, not quite at that safe space. And it's predicted by 2050, we're going to need to produce this amount of food. So if there is effect from extreme climate change, the amount of global food production is going to go down, and the amount of effect from agriculture on climate change, it can also affect it. So it's a balancing act of trying to get inside this green space to be able to produce enough food with the changes in climate. So we can do this in 3 ways. There's 3 different possible ways that we can achieve this. The first one is to change the amount of the diets of people and stop the wastage of food. That would move that green little triangle down so we don't produce as much. And so that will get us into that point where we're safe. We can also find ways to stop the effect of the agricultural effect on gases, climate gases, reduce those greenhouse emissions. So that pushes this back here. Or we can try and find ways to adapt our food systems to boost the yield and increase the efficiency of our agriculture. So in other ways that we can improve food production with climate change is through adaptation. So the agricultural scientists are finding all different ways that they can adapt the different varieties that we're using to produce more food. So this adaptation, sorry, going the wrong way. This adaptation can be through just different varieties or different agronomy management, nutrient and water management. We can also develop the genetics or the germplasm to be more climate sensitive, or we can even find new ways and different types of crops to plant in those different types of ecosystems. So this is what agricultural scientists are trying to do to find better crop production systems. So food sustainability or food security is all about sustainability and productivity. And there's ways that we can do that. If we think about how can we improve sustainability, we can create net zero agriculture. This is where we can generate solar energy or electricity on the farm. We can have less reliance on herbicides and chemicals, or we can participate in carbon farming, or we can improve the productivity. So this is where farmers would use new crops, which are more suitable for where they're growing, or they can use better processes of being able to monitor their crops and make better decisions about the crops. So this is where, as a computer scientist person, we're coming in by using sensors and drone image capture to be able to assist in that monitoring and decision making. So this factor about sustainability or productivity, it is all dependent on what kind of farming system it is. In Australia, it's massive broadacre farming like what we have here on this big areas of wheat production or forestry production. But in India and other places, it's a very smallholder farming systems, and the emphasis needs to be slightly different depending on what the farming system is, of course. So what is digital agriculture? Digital agriculture is really there to improve the food security and sustainability and productivity of those systems. And the traditional ways that we have gone about doing this has normally been through the use of biometrics or crop modeling tools. But in the last 10 years or so, we are moving more towards precision agriculture and towards a decision focus, where we use artificial intelligence and big data analytics and different computer vision systems, robotics, image processing, sensor networks, and even IoT and cloud technologies to assist in all aspects of the farming system. So this can be all the way from just at the cropping, where the crops are growing, where we're storing the grain, where we're transporting the grain to market, or even putting sensors on the tractors to monitor how the tractors are working, or monitoring the livestock, production of the livestock using sensor technologies or image processing, computer vision. And this is all being linked through different either wide area network systems or mobile networks, or through cloud services. So in terms of digital agriculture technologies, I've just made a bit of a table here to explain how some of these technologies are being used in digital agriculture. And some of these do relate to GIS specifically, which is the focus of this seminar. So in terms of AI and machine learning technologies, they are normally used for data visualization and creating decision support systems. In terms of image processing or computer vision, there's using 3D imagery technologies or weed sensor technologies or precision pesticide applications. These are using GPS-based technologies. Sensor technologies being used, GPS-controlled technologies or tramline agriculture. This is where the tractor is automatically set on a GPS map, and it just goes automatically up and down based on that map. There's various large tractor companies like John Deere or other American companies which have very sophisticated tractor computer-controlled tractors, which use GPS systems to create variable rate technologies for fertilizing crops. There's RFID tags and other livestock management tools which use sensors. And there's also sensors being used for just measuring of different climatic parts in terms of the weather or crop. In terms of drone technologies, drones are being used for just taking aerial imagery for scenario planning, and robotics is already being used for autonomous ground vehicles for weeding, for fertilizer, and for also in harvesting of fruits. And robotics is also mainly in Australia, is mostly being used in meat processing. In terms of big data and cloud computing, there's a lot of work being done in using IoT and cloud computing in terms of supply chain integration, and there are many mobile apps being created for farm planning and decision making. So digital agriculture is important, that we need to understand that it's all related to the supply chain. Here's a nice image of the Australian food supply chain, and the capacity of the farmers and the other stakeholders in the supply chain to get the most efficient harvest and collection and transport of the food to market is dependent on many parts of the supply chain. So it could be from just the farm planning to seeding the crop, spraying the crop, harvesting the crop, transporting and storage of the crop, and then sale of the crop. And it's at all those different parts in that supply chain that ICT and AI and other technologies can improve that efficiency. In terms of some of the types of things that need to be done when you're growing, when you're managing a farm. So digital agriculture provides applications for these as well. In terms of farm planning, we have production planning for the crop activities, integrating the market analysis, risk management. Crop management is important in terms of the crop management system to provide decision making. And we have digital agriculture applications which can manage soil and water conservation. They can manage the irrigation water pumps. They can determine soil amelioration problems. Pest and disease management can be, we can use different techniques to be able to detect weed outbreaks or pest outbreaks using image processing and drone technologies. In terms of horticulture and things like vertical farming, digital applications and ICT is really quite important in those areas, especially in fruit production. In Australia, it's very important to use, they use mechanized robots to harvest and collect fruit. Fertilizer management is also important. There's many digital tools which are available for managing when crops and pastures need to be fertilized or looked after. So the whole idea of digital agriculture and the aspect that myself and my other colleagues are involved in how we can optimize the data collection and of information coming from the farm and how we can improve the decision making for the farmer so that they can improve their crop or the livestock production. So traditional approaches of doing this is very expensive. It involves and time consuming, and it's not all that targeted. So what happens with if we're doing research or the farmer is trying to work out what's going on in his farm, he may have to walk around the farm, or the technician will walk around the farm, and they'll be able to take very limited amount of measurements about what's happening in the farm. And they take that information. It may not be applicable for the whole farm, and it requires some skill in collecting that data. If we use digital agriculture techniques, we could set up a network of field sensors which can monitor all across the farm. We can use UAV or drones to cover strategic areas, take images, be able to go out and provide an idea of whether there is any kind of issue and notify the farmer as to whether there's an issue. And that can be put into essential decision-making processes. We can use edge computing to reduce the data overload or the noise coming from the images. Some of the challenges that we still have in this system is that there's a lack of data standards, and all these different data sets that we can collect from the farm come in all different data formats and resolutions. So some of the issues that we have had in terms of the data sets is issues of data fusion and patching inconsistencies, and also restricted access for some of that data. And the issues of that there not being any real data cooperative data co-ops available to share data and collect the most amount of data to make the best decision. So the kind of systems that we're looking at in terms of farming systems is to create a digital agriculture system which would look something like this. So this is some of the research that we're doing in Australia. We're creating local wide area networks using LoRa networks and mobile networks, and integrating those systems to automate some of the data collection. So we have field sensors on the ground, and we have drones flying, taking images, and those images are sent through edge-based computing systems across cellular networks, and the information can then go into the cloud. It may be processed or put through prediction tools which use neural networks or other AI techniques to be able to then be analysed and integrated to allow if somebody is using that system to make decisions. So this is the basic kind of overarching kind of system that we're interested in. The kind of sensors that we're using relate to both, I'll just take a drink. Relate to both plant and the crop data, the soil, the climate or weather data. So all those different different types of measurements are required. So here are some of the types of sensors that we use. We use humidity, temperature, soil moisture, PAR, which is the light, We also have oxygen sensors, radiation sensors, ultraviolet sensors, photometric sensors, chlorophyll concentration sensors, and so they're all measuring different aspects of the light, the temperature, humidity, soil water, and water conductivity. And they can also measure different aspects of the leaf, the amount of chlorophyll it has in, stomatal conductance. These factors will determine how healthy the crop is. So some of the problems with those sensors, many of them are just handheld sensors that the technician goes out and takes some measurements. Very inefficient way to do it. And they're also not calibrated properly. There's issues with having to have access to batteries. In the middle of the farm, there's no connectivity even to mobile phone network. So we have had to set up our own mobile towers or satellite or linkage to the satellites. And also all the information that is collected, it needs to be ground truthed. So ground truthing means we need to take measurements of how the crop is growing, as well as any images we take, and we need to be able to validate those. So the focus that I've had probably in the last 3 or 4 years is looking at how we can use digital imagery of the crops to be able to get some better information about the crops and make it more efficient, to be able to collect that information and link it back to how the crop's growing on the ground. So the types of digital type of information we're collecting is using thermal cameras. So they just measure the different thermal differences in the heat coming off the ground or the crops. We have multispectral imagery cameras, so they have multiple spectral, hyperspectral imagery, many different bandwidths are taken of the crop, and you can see great variations in the crop in terms of its growth or it's so multispectral imagery. And the hyperspectral imagery is at even higher number of spectral points that allows you to find out even more information about the actual image. And we're also using LiDAR. So LiDAR allows you to really get like 3D imagery of the canopies and provides that kind of more sophisticated 3D type imagery. In terms of the satellite imagery that we have available in Australia, we can basically get a very standard kind of map of the farm just using Google Earth. So that is at just a particular resolution. So we can get that just as KMLs, and it will give it just basically outlines of the different paddocks in the farm or where the buildings are. In terms of the state government, they provide natural resource information, so that is at a bit higher level. All of these are not taken very regularly, so you can't get daily measurements of any of these. They're taken every 7 days, the Google Earth imagery. So you're not getting real-time information. Most of the research that is being done around using this kind of imagery has first started to look at whether the use of satellite imagery is reasonable to be able to map different variations across the season and to give enough resolution for studies. This was a study that was done by Zhao et al, and it's done in Queensland, in part of Queensland, and it was looking at mapping the paddock history of some cropping areas, and it was just using basic RGB imagery and trying to map where the cropping areas were across every 6 months, I think it is there. So the issue that they had with this was that just using the satellite imagery was they had a lot of missing data and a lot of sensor error because of the cloud cover during flight paths. They weren't certain whether the scale of the images that they were getting was worthwhile, in that whether it was going to give a regional or paddock focus. It wasn't really suitable for the purpose that they had. And in terms of whether they used RGB or multispectral images, depending on they looked at both possibilities. So the issue that they had was that they could get 10 meter by 10 meter image resolution quite easily. It was for free, but it required a lot of processing. And anytime they wanted a higher resolution, then they'd have to purchase it, and that provided 5 passes over the area per season, which was good. But even with this imagery that they did get, they had to find ways to ground truth that imagery, which is the time-consuming thing of going out and trying to map up what was going on the ground at the time that the images were being taken. So satellite imagery is not the best way of going about things. If we use drones, UAV images, we can find a better alternative to be able to take images when we want to take the images in the field. And it's an alternative to the costly, time-consuming kind of measurement, using kind of either taking them by hand, the measurement. So UAVs can provide multispectral and thermal cameras, so that we can use those to take images. And we can take them at different times at the farm scale, and we can take them in real-time images, collecting them during the crop cycle. We can take them daily if we want. These are the, sorry, go back. These are the kind of drones that we're using, but there's also larger drones that we're now using, which provide a 25 kg payload for being able to take more images. The kind of data that we're collecting through the UAVs relates to some of the crop plant heights, vegetation cover, biomass, plant stress, chlorophyll content, water status, canopy temperature, rates. So most of the UAVs can collect those. It depends on what sensors they are. They can either be just the RGB sensors or multispectral sensors. And if the multispectral sensors can be used to create the NDVI measurement, plant measurements, and some of the other plant indices which are important for measuring the differences in crop biomass and crop health. So there's thermal measurements and multispectral measurements. So there's solutions for all those kind of measurements using particular drone, as long as you have the right type of camera or thermal sensor. Some other studies that I found which kind of highlight the importance of using UAVs over satellites. UAVs can provide, even in terms of orchards and other cropping instances, we can use UAVs and they'll provide a better kind of analysis of what's going on. In this study by Naomo in 2020, they found that UAVs were not limited by the cloud cover for in temporal condition. They could be used flexibly at different times or altitudes. The higher the altitude or the lower the altitude means that you're getting a better resolution. And the images acquired by the UAVs offer observations of individual plants or plots, whereas you can see on the right, using the satellite imagery, it doesn't give enough resolution. Some of the disadvantages of using UAVs, of course, is that it's costly to own your own UAV, and it's costly mostly in terms of the camera. The cameras can be very costly. And maintaining the UAV is a problem. If you crash it, it's a problem. And it's also that you only get a small amount of coverage per image. So you need to be able to stitch those images together. Some other work that's been done, I'm looking at, this was a very interesting paper which is looking at difference between high resolution RGB images, which were being used to try and map out different plots of, I think it's a rice trial. Yeah, it's rice. So it's a crop fertilizer trial, and they're just trying to whether to use RGB, orthomosaic image, or a color NDVI distribution map to see whether they could use UAV remote sensing was better than just using this.
No. Oh.
Hello? Yeah, the satellite RGB image. So the NDVI map was the images that they got from the UAV images were specific enough to be able to map individual plots and also map individual plants within the crop. And then they could do their measurements to see what was happening with the different fertilizer rates. So this provided a good means for them to be able to map or to analyze what was going on. Another case study, which is very interesting, and this provided a similar platform to what we're creating. They created a cloud-based LoRa network, and using UAVs and sensors, and having a precision tool also associated with that, they were able to map different patches of plant disease in the crop. They were able to take those images and then be able to map and analyze where those pests were occurring within a plot. Other study which is interesting also was using modeling maize above ground. So maize is corn, modeling that above ground and being able to use the drone to create the map of what was going on across the paddock, and this could create individual samples. And they created a very good workflow which was able to integrate all the different types of data, either using multispectral images or RGB images, to create a means to create those vegetated indexes. And also they had a process which once they'd created those images, they did some pre-processing, and then they used some predictor tools to be able to, like using neural networks, random forest and support vector machines, to create a model, parameter model, to be able to evaluate what the effects of different treatments were. Some of the issues that have come up about using drones is how you can use the drone images to be able to actually take counts of the plants. There's a couple of studies which have looked at the effects of using these images and being able to process those images. Some of the issues that you get is blurry effects or vibration effects from the camera. So the UAV image is not always the best to be able to individually use that image. Other modeling studies have used RGB and multispectral images to create, to be able to assess plots of crops and try to work out which is the most efficient way of taking these images. So it's found that RGBs were more efficient during the early season, but the MS sensors were found to be more accurate in being able to measure the individual crops later in the season. So it is also depending on what you're trying to do with the cropping system. Just some of the other things that we found that are important in the accuracy of the drone images. It is dependent on such factors as the flying direction of the drone, the altitude of the drone, the time of day is important. So the solar elevation, it's dependent on the altitude, and that can, all the wind speed is also important. The flying speed is important. So all these different aspects can affect the quality of the images that you take and how you can kind of articulate your image to the ground truthing. So just quickly go through some of the other work that I'm doing related to this. So as part of our drone work, we're trying to create some data flow systems for how we can use all that data flow, the data that we collect, how we can integrate the image data into with the other cropping data and the other climate data. There's been a number of different other studies which have done similar work. There's Naomo and Yang have both created quite good workflows to show how we can use drone images and other images to be able to add that to crop breeding trials. There's another workflow that was created by Macheda and another one by Han. These have all kind of showed ways of integrating the different aspects of the UAV imagery, creating the DSMs and the 3-point clouds or the RGB orthomosaics, and integrating that with different canopy heights or the terrain models to create the canopy segmentation and add the UAV measurement to be able to then link it to the ground truth biomass estimates to be able to create that biomass estimate using that UAV image. Skip that one. So some of the focus that we have in our research group is looking at this drone and sensor research, the data workflow work that we're doing, which I've had to go over quite quickly, and creating decision support tools. We're looking at the use of LoRa networks and also vertical farming, and also interested in some of the information data security standards that are issued. And also a major issue in Australia is upskilling the local farmers to use these technologies. So we'll skip that, but we're basically, this is the work that we're doing with some of the drone work. So these are big farm trials, and we're using drones to take images of the crops. We're using thermal cameras, and this is a trial that is looking at the effect of frost on wheat. This is done with the local Department of Agriculture. This is the field trial that this is the drone that we're using. It's a larger drone than the other photo that I showed you. So that's a large scale drone. So these trials are being looked after by the local Department of Agriculture, and we're using some of the plots to do our work. We're flying the drone over a number of times, once each week. We're taking different measurements of RGB and multispectral image, satellite imagery, and we've also got different other imagery, which is looking at different colors, red, green, blue, and NDVI, and red edge. And we're also collecting the weather data. So at the moment, this is all the data has been collected, and we haven't analysed it all yet. Also working in other ways of being able to create 3D drone images. So this is, I think it's chickpeas. It's a chickpea crop in Australia, and it's been reconstructed by using just drone imagery at different angles to create a 3D image. And then you can look at the height and the amount of leaf cover to determine what varieties are performing best. The data workflows, this is the one that I've created for the work that we're doing. Some of the decision tools that we have created, there are some commercial ones which are available, which are using GPS and geospatial technologies to create paddock maps. They're using satellite as well as drone imagery, and they are using different AI techniques such as neural networks, Bayesian networks, support vector machines, and even basic statistics such as principal component analysis and linear regression. So these are all the back-end analytics that are being used with these images to provide decision support tools for the farmer. These are two commercial operations here, Data Farmer and AgWorld, local companies. We have, this is a project that I did with Professor Tripathi and some of the students from DBIT a few years back. It's AgMine decision tool for cereal production. This was using neural networks and some of the historical data. So I would like to update this next time we do it to include drone image data and see how we go. This was the crop variety selection tools that we created. We have some information and precision, some data that was provided for the farmer. I've also done some decision support tools for one student that I had at Mumbai University, looking at decision support tool for Indian agriculture. So this was, don't need my drink. That work has been completed. We published some of that work. So this was for rice crop yield predictions. And also I've done some geospatial data mining work in Andhra Pradesh with another student, an Indian, he was an Indian student, but based at ECU, looking at water catchment management planning using geospatial techniques. Dr. Tripathi was associate supervisor of that student. In terms of other work that we're doing is in terms of some of the work in predicting vegetation change in Thailand using some geospatial techniques and association rule mining. This is looking at the effect of seasonal variation on different types of land use in northern Thailand. And it was really looking at NDVI and other vegetation indices and mapping how the different changes in CO2 levels was influencing it. The work that we're doing in LoRa networking is looking at developing a long range, low bandwidth, low power, low security, low cost alternative for a LoRa network, which can be used across broad acre farming in Australia, where there's no mobile coverage or no internet coverage. And this is to be able to link all those sensors that are measuring information in the crop or on the animal to be able to get back into the cloud, to be able to create our data analytics on that and create our decision tools. This work was done a while back, but this is one of the first projects. Dr. Tripathi was involved in this when he was at IIT Bombay. So this GeoSense tool was created using 3G and GPRS technologies that was monitoring different farming situations and looking at pests.
Dr. Lisa, you have to.
Almost finished. Yeah, just about finished.
Yeah.
So the other work we're doing is in vertical farming, but I won't talk about that. It's not relevant. And information data security issues. It's not really relevant for GIS. And the training, upskill and training efforts that we've been doing as well. Not really related. We've done some work in sensor networks, but not really related to GIS, geospatial systems. So that's my talk. We've been kind of moving towards using drones and sensor technologies and integrating it with satellite data and machine learning and crop modeling to improve the farmer decision making. And we're also integrating these low power networking solutions so that provides the tool, the networks to be able to collect and transfer that data. Some of the references. That's my presentation. I hope you enjoyed it. And if you have any questions or queries about some of the work that our group is doing, I'm most happy to take your questions, or if you want to send by email so that I can reply to you. Thank you very much.
Someone is raising hand, or I think.
Sorry, I think I went a little bit over. Sorry about that.
Yeah, thank you, Lisa. I have one question, Dr. Lisa. Then See, when we are talking about this drone imaging, when you're talking about, and then there are a lot of difficulties in the sense, particularly the power, like battery, and the other side we have a so-called the flying. When you talk about the flying, then at that time there could be a wind and pressure could be there also, right? Of course, it depends upon the different zone to zone, right?
Yeah, I think that one of the major issues that we still have is battery life. So you can own, like for my drone, I have four batteries that I use just for my one drone. So if I go out flying, I have to make sure I've got 4 batteries all charged up to do any of the flying that I need to do. So most drones will only last for about 20 minutes in terms of flight. And then there's a lot of issues in terms of that you've got to fly them at certain time of the day. So we fly them from about 11 to 2. So when the sun is at its highest. And there's issues of if it's too windy, you can't fly it. Or if there's too low a cloud cover, you can't fly it. But we fly it at about, we can't fly it at any higher than 100 meters in height. That's the limitation in terms of the aircraft registration. And you can't fly it, you can only fly it in line of sight. It's quite restricted. I've had to do like a certification, like a proper flying drone operator's pilot's license to fly the drones. And for the larger drones, you have to have even more harder pilot's license to get to be able to fly them. So drones have its limitations. I think it's only one aspect that can be used. I think everything has to be integrated. So it's just one extra piece of the puzzle for the drone images. And I think the main problem is we just don't have the man or woman power to be able to take measurements and be able to go out. It takes, where we're doing our research, it's 3.5 hours drive to get there. And so you want to be able to take as many measurements and get as much information as you can in that time.
All right. Thank you. Grizal, any question? Yeah, something is.
Yes.
There's a question in the chat. Can the system be used to eliminate the middleman involved in selling and buying crops so that farmers benefit more, especially in Indian scenario?
I think middleman involved in selling and buying crops. I think that's another question about creating farmer co-ops and being able to, for farmers in a village level, to be able to sell themselves direct. I don't think that really relates to what I'm kind of looking at in this instance. I'm trying to see whether we can create better, more productive varieties. This is being used for variety trials, to crop breeding trials. It can be used for farmers to be able to manage their crops better. I can't see it being used in a village level though. I think it's more, at the moment, it's just being used in terms for research and being able to manage different aspects of the cropping area. So I don't think it can be used I don't think it's going to be used individually by farmers in India at the moment. So I don't think there's other ways that I think the farmers can get around that, the middlemen. I think that's the way, in terms of India, I think it's creating their own co-ops themselves where they sell directly. But it's all political, isn't it, in India for that aspect?
All right. Thank you.
Thank you, Dr. Lisa, for that illuminating session. I would now like to call upon Ms. Sara Pradhan to present the vote of thanks.
Good afternoon, everyone. On behalf of IEEE GRSS Bombay Chapter and the entire organizing team of Symposium, I would like to, it is my privilege to propose a vote of thanks and acknowledge the contribution of the people who have directly and indirectly contributed to the session on digital architecture. On the outset, I would like to thank our chief guest and resource person, Dr. Lisa Armstrong, for taking out her valuable time and out of her busy schedule and sharing her opinions and findings. We are really enlightened by your knowledge and your presence. The way you explained the topic was exemplary. I hope that the audience attending the session would have found it beneficial and insightful in many ways. Thank you so much again.
Okay, not a problem.
Thank you, Lisa. We'll interact a little later. Okay.
Am I getting any present, like some Indian sweets or something coming my way?
All right. All right.
No? Okay. Okay, thank you everybody for listening.
Thank you. Yeah.
Bye-bye.
Bye. Rejo, next session, please.
Before proceeding to the next session, I would like to make a small announcement. If you have any questions during the session, please put them down in the chat box. I would now like to invite Professor Imran Ali Mirza, Assistant Professor, Computer Engineering Department, System Manager, DBIT, to introduce our keynote speaker, Dr. Ashish Ghosh. Over to you, sir.
Hello, am I audible? Rejo, am I audible?
Yes, sir.
Thank you. With those interesting sessions on digital agriculture, I take privilege to introduce Dr. Ashish Ghosh, who triggered his career as an electronic engineer from 1983 to 1987. Professor Ashish Ghosh switched on to computer science during his master's, 1987 to 89, and finally to artificial intelligence during his PhD, 1993. Completing postdoctoral research in Japan, 1995 to 1996, Sir joined as a faculty member at ISI, 1997. Now a full professor and contributing immensely to the field of artificial intelligence, machine learning, video analysis, and data science. Sir has published more than 250 research articles on these subjects and has an H index of 44. For his pioneering contribution in computational intelligence and image analysis, Sir has earned Young Scientist Award from Indian Science Congress 1992, Young Scientist Medal from INSA 1995, and Young Associateship of Indian Academy of Sciences 1997. He is a fellow of the West Bengal Academy of Science and Technology 2015, the National Academy of Sciences NASI 2019, and the International Association for Patent Recognition IAPR. For his excellent service to IEEE, he received IEEE GRSS Regional Leader Award 2019. Sir has visited various academic institutions in connection with conducting collaborative research projects and delivered lectures across the globe, including countries like China, Germany, Hong Kong, Italy, Japan, Poland, Portugal, South Korea, Thailand, Netherlands, UK, and US. He has served as a plenary keynote speaker in many international conferences in India and abroad. To upgrade and nurture the engineering community, he disseminated seminars, lectures, and conducted several workshops and short-term courses in different parts of the country on upcoming topics of AI, machine learning, and data science. As a principal investigator and a co-PI, he completed 18 projects of national and international eminence, funded by the Government of India, European Commission, Indo-Italy, and Indo-US Forum for Science and Technology. He is a member of the co-founding team that established the National Center for Computing Research at Indian Statistical Institute, Kolkata in 2004 with funding from the Department of Science and Technology, Government of India. He acted as in charge of this center for a decade and has been recognized as an associate institute of ISI during 2005 to 2019. He also served as the head of a well-known machine intelligence unit of ISI during his tenure 2013-14, and he's serving his next term 2019 to 2020-21. He's currently leading the Data Science Research Consortium project as a theme coordinator to manage a number of projects assigned to different reputed Indian institutes under ICPS program of DST. He is a principal investigator of the Technical Hub of Data Science established at Indian Statistical Institute, Kolkata. With a funding of 100 crores, he is the associate editor of several international journals like IEEE, JSTAR, IET, Journal of Computer Vision, CAAI, Transactions on Intelligence Technology, published from IET and Sadhana, Journal of Banking and Financial Technology, and series editor of Communications in Computer and Information Science, CCIS, Springer Nature. Over to you, Dr. Ghosh.
Thank you so much, Amir, for your kind invitation, as well as this long introduction. Maybe I will just share my screen first. Very good afternoon to all the participants here. So maybe you are listening a couple of lectures on these topics, maybe more details. So I am given roughly an hour or so. In this hour, what I will try to do personally is, rather than telling you something very advanced, I'll try to give you something very basic, which should help you prepare yourself for doing kind of academic research. So that would be a conceptual or fundamental difference of this talk from the other talks. So it should have a different flavor. So what I will do is I'll try to move the journey like this. I'll just first try to define what is learning, what is machine learning. Why do you actually need machine learning for this sort of jobs? Maybe all of you know nowadays that everywhere this machine learning is being applied. Almost all fields, start from remote sensing data analysis to financial market analysis to designing computer programs, designing robots, weather prediction, weather forecasting, electronic circuitry design, wherever it is. There is almost every field where machine learning is getting its application. Why is that? What is the basic nature and characteristics of machine learning? Why people are interested in machine learning? These are the things I'm going to talk about. So that if you have a separate topic, separate problem of your own, you can think of applying machine learning for that particular issue. So I will not be actually giving you the details of what research we are doing using machine learning, nor what is the actual state of the art. What I will be giving it, I will tell you this is machine learning. These are the problems. These are the issues where machine learning can be applied. So let me first define what is learning. All of us know what is learning. Every day we are learning. But if I ask somebody, can you define learning? It's very difficult. Very complex to define what is meant by learning. Somebody will say, okay, acquisition of knowledge. Somebody will say my experience. Somebody will say this capacity, that capacity, my intelligence. So many definitions come up. Practically, it's very difficult to define. To give a little bit of formal definition. It says that acquisition of knowledge or skill through study, experience, or being taught. So what are you doing? You're trying to earn something. Say, for example, you are planning to go back to your home from your office. So what route are you going to take? It depends upon your previous experience, your previous knowledge. So this decision that yes, I will move or take this route today. Say for if you are starting at 5 p.m., you may take one route, and if you are starting at 7 p.m., you will take another route. So this decision comes from your previous experience, previous expertise, previous knowledge, previous data. So this process of acquiring the knowledge to take this decision for future is what is called learning. This is one of the very distinctive characteristics of intelligent behavior of us, the human being. Ability is possessed by humans, animals, plants, and many other things. So what actually we do in this learning, we try to find out basically kind of some rule, some regularity, some pattern, some characteristics. Anyone you can say. Yes, I try to find out the pattern. Okay, the pattern looks something like this. Okay, this route is congested from 5 to 7 p.m. So I will not take that route. So that's the pattern I discovered. That's the pattern I found out from my previous knowledge, previous data, previous experience. So that's what is learned. So like, for example, when I come back from my office, I start around 6:30 to 7. I never start around 5 p.m. because Kolkata traffic is highly congested between 5 and 6. So that's the kind of learning I had. So that's a real life case. In your life, you are learning. So this you can do for remotely sensed data also. This you can do for analyzing remotely sensed data. This you can do for forecasting weather. This you can apply for analyzing the stock markets. So basically what is learning is the ability of an agent or a human being to take in real data and update its parameters accordingly. So if you come to a mathematical perspective, so what are you actually doing? You are updating the parameters. Let's say you have model that, okay, this is the timing I will start. So the model was having some parameters. With passage of time, with data, what are you doing? You are changing these parameters. You are updating these parameters. So updating of these parameters is what is called learning. So if you have designed some system for your data analysis or the observatory data analysis or farming or weather prediction or say geospatial data, say Google Map, Google driving app. So what are you doing? What you are doing is basically from the previous data, you are trying to extract some information and use that as a generalization. If you are putting Google for Google as your driver, if there is a kind of red mark on a road, Google may divert you because it knows that the red mark means it's a congestion. From the satellite images, they found out that, okay, this place, there are plenty of cars. So they put a red mark. And since there is a red mark, it's better not to take that route. Just may take time. So some avoiding route, some other route. That is the intelligence. That is the pattern that you are discovering. That is the parameter updating. That, okay, the parameter was something like this. Now the parameter should be changed. Right? Let's say you want to find out the pollution level in air quality pollution. If you go to Delhi, it's very difficult, air pollution. So what are you doing? You are actually looking at the parameters, different parameters which are responsible for polluting the environment. So studying those parameters and making a decision is what is called learning, what is called machine learning. If learning is done by a man, we'll say it's human learning. If the learning is done by a machine, we'll say machine learning. So basically, this sort of capability of learning from data, from experience, from knowledge through a machine learning program is what is called machine learning. If you want to define it mathematically, the mathematical definition goes like this. you are improving on a task T with respect to a performance measure P for or based on an experience E. So you have three things. You have a task, you have a performance metric. So your performance metric should improve. If there is no improvement in the performance, you are not learning. The example that I gave, yes, you want to predict the pollution quality. So if with passage of time from previous data, previous knowledge, if the prediction quality, perfection of prediction is not improving, then there is no learning. If the perfection or prediction quality is improved with passage of time, with previous knowledge, with previous data, then we will say there is learning. Say, for example, nowadays this depression, they are predicted very nicely. In the Bay of Bengal, there is a depression now. So maybe around 3-4 days back, we got an alarm saying that, okay, Saturday, Sunday, there will be rain. Now, if you think of 10 years back, this sort of prediction was not good. But now the prediction is quite good. It should be more perfect. It should be hour basis. It should be minute basis. So this sort of analysis is actually being done by a machine from the previous data. And that is what is called machine learning. That yes, I have plenty of data for previous, say, depressions or cyclones or whatever it is. That okay, if this is the temperature level, this is the atmospheric pressure level, if the water height is something like this, or the water pressure is like this, or water current is in this direction, then there is a chance of depression. So that data, these instances, are actually being analyzed with some algorithms, some techniques. And these algorithms or techniques are nothing but machine learning algorithms. And as a machine learning scientist, your job would be to design these algorithms. For geospatial intelligence, you will design some algorithms dedicated for this particular type of data. Let's say we take a very simple example of handwritten character recognition. We can do that. So what we will do, we will train the machine with a set of data, for which I will say, okay, this is a handwritten 0. This is a handwritten 1. The machine will learn that this is a 0, this is a 1. With variation, deviation, different shapes, different types, different handwritten characters, and other things. So with all these variations, machine will learn. Machine will understand, okay, this is how a 0 looks like. And then if there is a postal code, there is a letter, it will scan and segregate this postal code, this pin codes, and then say, okay, this is 0 or this or this, accordingly, it will put into the box. This is spam filtering. It's a very good example of machine learning. All of us face this problem. Some of our mails are going to spam, and some spams are coming into our mails. So this means that the filtering is not proper, which means the machine learning algorithm that is being designed is not very good, very correct. So you have scope to modify this. You have scope to enhance this quality. So machine learning can have its application in spam filtering. You can enhance the quality. Whatever technique or tool is available today is not very perfect, very good. So maybe you need to have more knowledge, more data to analyze that. So these are different examples of machine learning. So what is then formally machine learning? It's nothing but programming a computer to optimize a certain performance criteria using example data or past experience. So basically, you are learning from the previous data. So if you have known rule, say for example, you want to sort 100 numbers, you do not need machine learning. You want to calculate the payroll, you don't need machine learning. You want to invert a matrix, you don't need machine learning. But you have data, plenty of data, where there is no such exact rule, and you are trying to discover some rule, then machine learning comes into picture. And this is why for this sort of data analytics, you call it geospatial data, you call it rainfall data, you call it weather prediction data, you call it precision farming, and whatever it is. So they are nothing but data. So you have some previous data from that previous data, you were discovering some pattern through certain processes or certain learning techniques or tools. And this set of learning techniques or tools are nothing but machine learning techniques. Note that the data is changing, your solution will change. Like the spam filtering I'm talking about. The spam filtering that you are using today, tomorrow you may not have that same spam filtering. The parameters will be completely changed. And that's why sometimes you will see that they will ask you to put it in the spam or non-spam. So that would be another training sample, another pattern from which the machine will learn or update its parameters. So the solution will change with time, or it is adaptive. Machine learning is almost always an adaptive system. So basically, when you have lots of data and you are trying to extract some information from that data, and then you can use machine learning. So if you think of geospatial data, what you have is data. If you think of farming, what you have is data. So for example, you want to find out the from this drone picture whether the crop has diseases. So what you will have? You will have a set of data where you will have the pictures or images of the crops which are non-corrupted, and you will have some pictures of corrupted. Some pictures of corrupted cultures, these fields, and some pictures where these plants are not corrupted. So from this picture set, which are corrupted and non-corrupted, you will find out with the help of machine learning tools certain characteristics. That okay, if the leaves look like this, then there is a disease. If the leaves does not look like this, then there is no disease. This is what is learning, nothing else. It's not really that much great on this. You don't have to commit things. So for machine learning programs, you will give some input data and the corresponding output. I'm referring to, okay, this is the plant which has disease. So the input corresponding output. This is the plant which does not have disease. This is the tree corrupted by something. This is the place where there was forest fire. This is the place where there was rainfall. This is the place where there was flood. So input and the corresponding output. This association you actually learn through a machine learning algorithm. So this programming and the standard programming that you do in your assignment for sorting numbers or calculating payroll or finding out the inverse of a matrix are completely different. So in this case, for standard programs, you will have a set of tools, techniques, and the data, no output, and output will be generated. But for the machine learning cases, you will give the data and the corresponding output. This together actually is going to tell you this is the rule, this is the technique. So for any and every data, you can apply it. It's not necessary that
Dr. Ghosh, your slides are not changing. Are you changing slide? Yes,
Yes, I'm changing.
No, it is not changing since so many. So that's
my goodness. Let me then reshare it.
Yeah, please reshare it. Sir. Yeah, it's now changed. Now it's changed.
Okay. So this is what is the basic difference and conceptual difference from machine learning with non-machine learning programs. So you have to be very careful about that. Okay, this is the program where machine learning is involved. This is the program where learning is not involved. Right? So for without machine learning program means we have very specific instruction, and machine learning programs means you have data, you have the corresponding output, and a set of parameters which needs to be optimized or updated with passage of time from this data set. For sorting numbers, you do not need to update any parameter. It is prefixed. Instruction set is completely fixed. Whatever may be the data. With incoming data, this logic does not change. But for machine learning program with incoming data, logic changes. So these are the conceptual differences. So look at this animation, which actually will define you what is machine learning. So this is a robot. This robot is being trained with certain amount of data. And this lady is trying to test whether the machine has learned properly or not. Right. So the lady is asking a couple of questions to this machine. Initially, some data was given to the machine, and the machine tried to learn something, update something. And this lady is going to ask certain questions. That is, whether these answers are available with the machines or not. Note that this is not searching. Searching is finding out the things exactly. Like Google search, it's not machine learning. If it finds out an exact match, information retrieval, not machine learning. If it finds out an exact match, it gives you the data. If it does not find out an exact match, it doesn't give you the data. But here, the things are different. It will extract some information from the data, which is or may not be explicitly available. That is what is machine learning. So this machine was trained with some images, and it is being asked certain questions. It is answering some questions. And as you note that until now, it has answered the questions very nicely. But maybe if the lady asks a little difficult question, the machine will not be in a position to answer it correctly. Okay. So the machine could not answer what else. What is the person doing in that red box? The machine cannot answer. So that shows the learning of the machine was not 100% correct. Some input was given to the machine learned something, but not very correct. That's exactly what is happening with our spam filter. Some input data is given to the machine learned something, but it's not 100% correct. Because of the fact that the input data did not consist of all varieties which should have been given. All samples, all types of samples should be given to the machine for its training. If that is not given, then the machine will not be in a position to learn. Now you see how this learning goes. What does this do? This lady gives us much more images, some more pictures, some more input. And the machine updates its brain. And this updating is learning. And this updating should enhance its performance. That is what is the issue. The updating should enhance the performance. If there is no updating in the performance, if there is no improvement in the performance, then I will say the machine is not learning. Now, the lady asks some more questions. Right? And the machine answers maybe almost all of them correctly. Previously, it failed to answer a couple of questions. Now it is successful to answer some more questions. May not be again 100%. It's very difficult to get 100% accuracy. But it would be something more than what it had. So this parameter updating, which went on inside the brain of the machine, is what is machine learning. If you are listening to me, if you are listening to other speakers, and if you are learning something, that shows some changes are going on in your brain. Some modifications are going on. So in future, this would be helpful for you to answer some question with respect to the topic of machine learning or data science or geospatial science or geospatial intelligence or earth data analysis or whatever it is. So if that enhancement is not there, then there is no learning. So whenever you will be trying to use machine learning, keep this in mind that your algorithm, your tool that you are designing should improve its performance with passage of time and with new data. Your system should be designed in such a fashion. If your system is not doing that, if your system is giving you a consistent performance, same performance, with even giving more data, quality data, then possibly there was not much quality in your program, in your algorithm, in your tool, in your technique. And nowadays, almost every field of science, not only science, you see e-commerce, they're using machine learning. They're trying to extract the buying pattern of customers from the previous data. And that extraction of that pattern is what is machine learning, what is the job of machine learning. So machine learning has been used to almost all places, almost all places nowadays. Okay, so let me give you a very realistic or formal definition of machine learning. Is about designing algorithms that allow the computers to learn from experience and data. It has to learn from experience and data. It is not rule-based. There is no fixed rule. The rules will be generated. If there are rule-based system, then it is usually referred to as something what is called rule-based system. Okay, you can go to a doctor. Doctor looks at your symptoms and prescribes the medicine. That's rule-based. So machine learning systems are not 100% rule-based. They learn the rules, they modify the rules, they extract the rules, they polish the rules. So basically, you will have to have plenty of data and a rough idea that, okay, there could be certain rules. Then you apply tools and machine learning to extract these rules, whatever may be the data. You can apply it for designing apps. You can use it for predicting rainfall. You can use it for predicting crop diseases. You can use it for Mars mission, Moon mission, whatever it is, any and every place. So this is what is machine learning. How will you say that whether your program is learning or not? Mostly we measure by 3 characteristics. Either it enhances its performance. Enhances its performance means, okay, let's say I know I have trained the computer with some images to classify, say, trees and water bodies, or water bodies and concrete structures. So it should do for trees also. Enhancement of the horizon. Or it should increase the accuracy. If it is trees and concrete structure only, then it should increase the accuracy. Or it should increase the speed. Maybe it was previously taking 3 minutes, now it should take less time. If you see improvement in any one of these 3 characteristics, either it should enhance the breadth, or it should enhance the accuracy, or the speed, then you can claim that yes, you are learning, the machine is learning. So from this very general rule, general characteristics, it should be evident to you that machine learning should be applicable to almost all sorts of data. Almost all. So when you will be designing machine learning algorithm for your data, could be rainfall prediction, could be weather prediction, could be global warming, could be temperature prediction, could be depression prediction, or any problem. You should think of accuracy. You should think of the correctness of the solution and the program, solution quality, and the speed of performance. These 4 measurements you should keep in mind. Whenever you will be comparing your algorithm, that yes, my algorithm is performing better. So compare with at least with respect to these 4 performance measures. At least these 4, maybe more. I'm not saying these are all. So at least these 4. And try to test your algorithm on a big set of data, on different sets of data. And this is the reason why machine learning has become very popular nowadays. We have plenty of data available today. Everybody is generating data. Everybody is having a mobile phone and is generating data. Everywhere you see there are drones and generating data. Everywhere there are satellites and the data is coming up. So you have plenty of data. You have GPU machines, and you have certain machine learning tools or algorithms available. So you make a combination of all these 3. You have the facility to apply or use all these 3 things today. And this is the reason why machine learning is being applied to almost all fields of life today. You have data, you have machines, you have the algorithms. So what else is lacking? Nothing is lacking. So use them. for your job. So everywhere, every field, you see machine learning is being applied because of these three facts that yes, we are having data, we are having machines, and we are having the machine learning algorithms. So maybe for some places, we do not have the algorithm available. In those places only, we are trying to modify the existing algorithms or trying to use the existing algorithms or trying to design new algorithms. So that is why machine learning is getting its applicability to almost all fields. Now, it is just a general basic idea. Machine learning is basically a kind of subfield of artificial intelligence. And nowadays, the most popular field is deep learning. Everywhere people will be using deep learning. So deep learning is again a subset of machine learning where you use neural networks with so many layers. So deep learning is a small part of machine learning where the tools or techniques being exploited is artificial neural networks with so many layers, not 1 to 3 layers. If it is 1 to 3 layers, then it's not deep learning, that is shallow learning. That is under machine learning, but that is called shallow learning. So AI is the biggest field where people are trying to simulate the overall human brain architecture. A subpart of that is machine learning, where we try to do or extract the statistical regularities or patterns or characteristics or learn the rules. And deep learning is one subset where we use only machine learning, only neural networks to do the learning. We can use non-neural networks also for doing learning also. We can use, say, for example, decision trees. We can use support vector machines. We can use Bayesian rules. So these will be coming under non-deep, but all of them will be coming under machine learning. So AI is the biggest umbrella under which you have the smaller umbrella called machine learning, and under machine learning, you have deep learning. But machine learning is very popular for designing algorithms. Now let us see how actually we design machine learning algorithms for kind of data analytics, maybe your data for remote sensing. Okay, so usually what we have is the total data is divided into 3 parts. One is called the training data, one is called the validation data, one is called the test data. So this training and validation is possible if I have the previous data with known knowledge. On this data, usually referred to as supervised data, labeled data. This is used for supervision. So some data with known output is known as training data, and we train the system. We generate the model. We generate the algorithm from our basic intuition using that data. And that part is what is learning. Okay, so say for example, this part of the data is being used to train the system. This blue part. Then I validate the system with this part. So validation means something like checking whether the system has been trained properly or not. In the first phase, training phase, we do not check. We just try to train. Okay, this is the input, this is the output. Machine should learn. This is the input, this is the output. Machine should learn. This is the temperature, this is the pressure, this is the atmospheric condition, this is the vapor concentration. There was rain. So learn this. This is the temperature, this is the vapor concentration, this is the pressure, this is the latitude, longitude. There was rain. Learn this data. So this was done in the training phase. Now I give, this is the location, this is the temperature, this is the pressure, this is the vapor concentration. The system tells me whether there should be rain or not. But I have the data, I know whether there was rain or not. I validate this, I check, cross-check. If the prediction of the machine was correct, we do nothing. If the prediction of the machine was not correct, I go back and retrain the system. So this is what is the most important job you have to do, this training and retraining or validation with the data and data. So new data comes, You validate and retrain. New data comes, you validate and retrain, and the performance improves. So it's not that one day you have trained the system and you will get the best performance. That happens with you also. If you study one subject today and after a long time, if you try to answer some questions, you cannot do it. So at a regular interval, you have to retrain yourself, brush up. That's retraining or validate. So the same thing we do in case of machine learning. And then what comes is basically the unknown data. And that is what is referred to as the test data. If something unknown comes, we predict. Some spatial location, temperature, vapor concentration, pressure, atmospheric condition, and some other parameters, whatever it is. Then we predict whether there will be rain or not. That's exactly what we are doing today. That is, there was some characteristics changes in the Bay of Bengal, and they predicted, okay, there will be a depression, on so on and so forth, that, and this will move according to this path, which is crossing Kolkata today now. We are having plenty of rain now. So this was well predicted from the previous training and validated data with this new data. So this data is the test data. And depending on the accuracy of the prediction, in future, next time onwards, this data will also be used as a training data for training purpose or validation purpose. So if we have this sort of data, we say it's a kind of supervised learning. We are supervising the whole thing. Everything is supervised. Because input and output I know, and we supervise whether the machine is properly learning or not. There can be certain situations where you really do not have that output data available. You do not know, you have no data. Say, let's say, for example, some data is coming from Mars. We do not know what is there. But for looking at the characteristics, we can group them. That this is one type of objects present in the Mars. This is another type of objects present in the Mars. Those types of objects may or may not be present on the Earth. If they are present on the Earth and we know what is that, then we can say, okay, water is there. But if we do not know, it doesn't match with the objects present in the world, we cannot say something. We say, okay, this is the group I have got. And this is what is called unsupervised learning, or what is popularly known as clustering. So if you have training data, you do classification. If you do not have training data, you go for clustering. And if you have something in between, you have a very small number of training data, and you have plenty of unlabeled data without output, then you use something what is called a semi-supervised learning. And this is very common in some cases where you want to find out the change. Say there was a forest fire in one place, but previously there was very small amount of data, maybe just a few samples, and those few samples were not sufficient to train the system properly. So what you do is you use this unlabeled data and the available level data, mix up these two together to train the system, which will not be as good as the trained system or supervised system, but will not be as bad as the unsupervised. So it will give you a performance something in between supervised and unsupervised. So these are the three modes of learning we have depending on the type of the data available. Mind that it's not your choice. It depends upon the type of the data you have. If you have a good set of data, if you have plenty of data properly available, do go for supervised. Don't go for unsupervised. But if you do not have, then what do? You are forced to go for unlabeled. So any one of these three techniques you can use. And there is a fourth technique where sometimes you may be forced to take something. Like when you play a video game, you do not know what is the final output. Either you get some reward or you get some punishment, and based on that you move. That's what is called reinforcement learning. It's forcing you to do something. That award is a kind of lucrative thing for you to do something. But whatever steps you will be taking may not be good for you because you do not know the output. So that is something what is called a kind of reinforcement. It's reinforcing you to do something. So any one of these 4 types of learning could be applicable to your system. When you design a system, you can use supervised, you can use unsupervised, you can use semi-supervised, and you can use reinforcement. Right? So for supervised case, there is a teacher, there is a supervisor. The supervisor is telling it, okay, this is this, this is this, this is this. So let us take this example. On the left-hand side, we have a set of pictures of water bodies. All these pictures are actually having mostly water bodies. And on the right-hand side of all we have is a kind of land cover. All of them. So different types of land covers. So this is one class, this is another class. This is told by the teacher or the supervisor. And the machine learns, okay, these are the features of water bodies. These are the features of land covers. So this is the supervision. This is how you design your system. This is how your system learns. And then these unknown patterns come, these unknown images come. So these are what is called training samples on top. And on the bottom side, what you have is a kind of test samples, unknown samples. And the machine tries to match this image, this unknown image, with the existing training samples. And wherever it finds the closest, it says it is that. So as you can see, the left side image, it will have a closer match with these grasses. So it will say it's a kind of land cover. But for the rightmost image, it will have a close match with the water bodies, with existing images of the water bodies. So it will say it's water body. So this is how we train a supervised system. Let us take an example for unsupervised case, where you are to make inference from data of which you do not know what is the level could be. There is no teacher, nobody is telling you. It's something like reading yourself. You read yourself and you learn it. You find out a model on your own. That model may be good, model may be bad, model may be correct, model may be incorrect. You can have one model, I can have another model. So if it is an unsupervised learning or clustering, you can have plenty of solutions. Maybe all of them are correct, maybe none of them are correct. So it's very difficult. So I will say that unsupervised learning is more difficult, more costly, and more unreliable than supervised learning. So if you have some levels, if you have some data with known levels, you know the output, then do go for supervised case or semi-supervised case. Don't go for unsupervised. Unsupervised may be applicable only to the places where you need to group and group only without knowing what is it. Right? Say for example, all these 3 left images, they look very similar. So they will come under one group. On the rightmost side, they will come under another group. Right. So this green color would be one of the important features which will tell you, okay, these 3 are similar. But what is it? That's not going to be predicted. This dry tree or green tree, the machine is not going to tell you. This is the name I have given just to show you. Machine is going to tell you, okay, on the left-hand side, you have one group. On the right-hand side, there is another group. Whether it's a tree or it's a dry tree or it's a green tree, nothing. The machine is not going to tell you. The machine is just simply going to tell you, this is one group, this is another group. That's all. Nothing more than that. So if you do use your knowledge for supervision. Now let's say on the one person looks at these 3 pictures and says, okay, it's a kind of green trees and dry trees. Another person can say, this is a kind of forest and this is a kind of desert, because dry trees are available in desert. So this solution is also correct. this solution is also correct. Both are correct. Actually, you do not know. So clustering is difficult. If you have small number of training patterns with known data, then possibly you go for semi-supervised. In semi-supervised, what do? You initially use the supervised mode with that small set of data, then find out the level using this small set of data, and then use that new levels where you have 100% confidence to retrain the system. So you have a small set of data, use that for training, predict some levels, use high confident levels to retrain the system. That's the basic theme of semi-supervised learning. So depending on the type of data available with you, you can use supervised, semi-supervised, or unsupervised learning. Okay. Now there will be a question that why should I go for that? The situation forces it. Getting training data is very costly. The training data should be very partial, very accurate. You have to have a very good domain knowledge, which is not always available. So that is why you need to use unlevel data also. And in many places, unlevel data is very useful to get the insight. This may not give the 100% insight, but it is going to give you very much a kind of very good information. Right? So now let us take a little bit more concrete examples for how to apply this on your data, or observability data. Okay. Now you should know this, I have already told you. Usually this data is very big data or huge data, so you need a lot of memory. You need a set of training data, which actually will help you to generalize the issues. And you need to have as less number of parameters as possible. Because if you have more parameters, you will need more data to set good values of those parameters. And every time, this parameter value will be changed. So different types of classifiers are available. It could be pixel-based, it could be object-based, it could be statistical, it could be machine learning-based, it can be statistical learning-based, hard classifier, soft classifier. Many models have come up, but all of them do use the same principle. There will be certain set for training the system, then a part for validating it, and then the last part for testing. Okay, so for example, I want to classify the land covers. You take a picture of Mumbai and you want to predict where is the water body, where is the concrete structure, where is IIT Bombay, or where is the Don Bosco University, and where is the stadium, where is the airport, and whatever it is. So each of them is a kind of type. So what you will do is you will have a large number of pictures of Mumbai, and you will extract some patterns, and you will tell the machine, okay, this is a concrete body. You will take a pixel from a house. You will take a pixel from maybe the runway or from the roads or whatever it is. You will say that, okay, this is a concrete structure, this is a concrete structure, this is a concrete structure. And these pixel values or feature values the machine will learn. Okay, if the in a spectrum 1 or band 1, the pixel values are this. If the pixel values are this in band 2 or in band 3 and band 4, then this is a concrete structure. This rule machine extracts. You don't tell. So these types of land covers. So for this problem, what you will have to do is you will have to tell that, okay, these are the number of parameters, these are the features, and this is a type. These are different types or levels or land covers. Then the machine will turn, and in future it will say, okay, if I have picked up a particular pixel from a position and the characteristics of this pixel matches with the characteristics of the water body, they will say, okay, this is the water body. So if now part of that you see Arabian Sea, if you look at, then possibly those pixels will have certain characteristics and it will say, okay, it's a water body. Or if it is a runway, let's say a long road, it will say it's a road. So what information you are going to use, what characteristics you are going to use is up to you. How many features you will be using, how many bands you will be using is dependent upon the type of the data available with you. So it's not that, say for example, these many bands are available. Okay. So what you will do is for all these bands, you will have some pixel values. So use those pixel values to say that, okay, our water body has a pixel value of x1 for band number B1, x2 for band number B2, x3 for band number B3, xn for band number Bn. This will be discovered by the algorithm, by the machine. You are not telling the machine, and that algorithm which learns these characteristics is called a machine. That's why the word learning, it is learning from the data. It's not that you have told. If you would have told it, this would become rule-based, not machine learning based. Right? Let's say I have different classes, say forest or sand or built-up area or cultivated land or water land. So in the spectrum, they will have different position. So which means that in different bands, they will have different pixel values. So say in the band 1, some pixel value, and band 2, some pixel value tells me it is a kind of forest or it is a kind of sand. So all sun pixels will have similar pixel values in band 1 and similar pixel value in band 2, and which will be different from the pixel value of a forest in these bands. And those characteristics are used as discriminating feature for classifying the land covers. So any number of land covers you can classify. It's not that I will have to tell you that, okay, for 3 classes you do this, for 5 classes you do this. It's applicable for n classes. It depends upon your data. Now I'm talking about land cover. You will not classify into land covers. You will classify into 2, rain or non-rain, forest and non-forest. Depends upon your purpose. Road and non-road. Road and airport, runway. Both are concrete, mind this. Roads are concrete, airport is concrete. But one is airport, one is concrete, one is runway. How do you distinguish? Roads are usually smaller, narrow compared to runway. Roads are usually not as straight as a runway. So these characteristics or features need to be exploited from the values. That is what you learn. So these concepts are being used to predict, say, the buildings. So this is a building, this is a building, this is a building. See, all these red blocks are buildings. From these images, it was discovered that these are the building positions, which is pretty correct. Very good. Now, depends upon what is the resolution of your image, depends upon what are the features you are using. So, as a researcher, as a good worker, or a student, your job would be to design those sort of good, extract good features, good characteristics, or modify the algorithm. Not rather using it blindly. I have used BGGNet, I have used XMate, or I have used base classifier without understanding. That would not. That's not going to work. You will have to do check. Okay, this is the road. You see, all these reds are roads. So all roads will have same characteristics. So what characteristics are going to be more useful for road? That is what you need to discover. But these are the features. You should tell the machine, so these are the characteristics or features, and machine will extract from all this data. You are not going to do it pixel by pixel, but that intuition is going to be given by you. So you can design it. You can decide. Now, when you go for this, you will have to be very careful. Say, for example, you want to find something called change detection. Change detection is what? Let's say there was a flood in rainy season, there was no flood. So one part was no flood in winter and flood at the other time. So there was a change. Now, if you want to find out the change, all the images should be 100% registered. Correspondence among all the pixels have to be established. It's a very critical issue. So this needs to be done beforehand if you want to detect changes. So these are the things you should learn as an academician, as a scientist, as a researcher. And what is my problem? Where am I going to use machine learning? How am I going to use machine learning? Am I going to use it for vegetation classification? Or for green land? Or water bodies? What? So each of them will have its own spectral characteristics, spectral features. And that is what needs to be exploited. That is what needs to be extracted out. So what I'm trying to tell you is a couple of examples, but the basic principle that yes, pollution level, how do you measure? What is the level of SO2? What is the level of NO2? What is the level of carbon dioxide and what? All this together. Right? So nowadays this IoT is coming up, use them. Different sensors that is going to give you data. Sensors are nothing, they're going to give you the data and then you will be analyzing the data using machine learning. Okay. So this way, if you go on, any and every field, you will see that there is data. And you analyze that data using some tools called machine learning. You design some algorithms, some techniques called machine learning. You can use it for flood prediction, you can use earthquake prediction, you can use it for tsunami prediction, all of them. But do remember that the same technique, same parameter set may not be applicable. Maybe the same classification technique would be applicable, but not the same type. May not be same set. And that is what you need to understand. That is what is research. So if you are interested in doing a kind of research in geoinformatics, then do find out what is your geoinformatics data, what data you have, and clear the problem very sincerely that this is the problem I want to solve. This is the problem that has not been solved. And how can I cast that problem in the form of a classification problem or a clustering problem or a semi-supervised learning problem or a reinforcement learning problem? And if you can cast that, then the remaining part is very easy, very simple. Some of my students and colleagues, and they are trying to do something what is called change detection. Say a picture of Kolkata was taken 10 years back and picture of Kolkata is taken today, properly aligned. In some places we are saying, okay, there was some greenery, there was some kind of trees, vegetation, and now there is some big concrete structures. What are those? These new academic institutes coming up. Mostly the private engineering colleges. So that's what is called the thing. Himalayas, this landslide prediction, rainfall prediction I am referring to always. So this way, if you look at, you will see that in each and every field, you will have data and you will have your algorithm applicable to them. So I did not concentrate on any of these specific fields. Rather, what I tried to tell you is these are the principles of machine learning. Depending on your data, your application domain, you redesign or design or use any of the machine learning tools or machine learning algorithms. So maybe I will stop here. Thank you. Thank you so much for listening to me very sincerely for last 1 hour or so. Thank you so much.
Thank you, sir. If there are any questions, you can take them up now.
Sir, I have one question, sir. See, when we talk about the new age of machine learning, I'm talking about deep learning, all things are there right now. So again, looking into this satellite image processing and different level of things when comes in picture there. So it is really having a difficulty, to have it. One side is a data is a problem. The other side is that again the right algorithm to a right kind of data also another problems all the time students are facing over there. So how they will look into that?
See, that is what is the most important issue or most critical issue of research. So what you need to do is, first, the student should study the literature very sincerely, very carefully. Like how did the previous authors or researchers handle this data? So from that literature survey, the students will get a rough idea, rough rule. That's okay. The rainfall prediction, these are the characteristics. These are the features. So what are the features? Like some of the features I am talking about, say temperature, atmospheric pressure, and vapor concentration. Another feature is more useful is the level, the height. Where is that vapor pressure concentrated? So these are the characteristics. These did not come up in one day. Through studies and studies and studies, people discovered this. So if the student wants to discover all this in one day, he or she will not be able to do it. So first job is to study the literature very sincerely, that what exists, how did they handle, then what are the bottlenecks they faced, and then solve that issue. That these are the things they have already solved. So I don't know, have to do any research on that. And these are the issues unsolved. So let me spend some time on this, and how can I solve this? That is the most important. Rather, I mean, I will say that don't jump onto anything and everything and run in a VGG net. That is going to give you something garbage. I have a very interesting slide where it is proved that a giraffe of a zoological garden and a clown of a circus are classified into the same class. And it is, if you think it is, you will feel it because the kind of, what is it called, as texture that the giraffe has and the kind of texture this that clown's shirt has, they're very similar. They're very similar. So these things have to be very much careful. The students have to be very much careful. Everybody has to be very much careful. So what characteristics or what feature of this spectral level would be useful for me to classify my job? That needs to be discovered. That is the greatest challenge for this. And there is no one-word solution to this. It needs experience, it needs domain knowledge, it needs time.
So there's a question in the chat. What is the difference between validation and testing data? Could you elaborate more on that?
Okay. Validation data is the set of data for which I know the input and the corresponding output. I know that, okay, this is the input and this should have been the output, right? Output is this, I know. But I did not use this for training the system. So this I am using for validating the system. I'm giving the system this data. I'm checking whether the output that the system is giving me and the output that it should have given me, whether they are the same or not. If not, I will say the machine has not learned properly. Let me retrain with this data also. Test data, I do not know the output. It's something completely unknown to me. It has come to me and I will have to predict what should be its level. Does it help?
Yes, thank you.
Let me give a very critical example I mostly use for our students. Say something like, I give you an assignment for which I know the output. You come up with a solution. I check and tell, okay, no, the output is not good. It's not correct. Your program is not correct. You go back and correct it. I'm not penalizing you. But you think of semester, I have put some question and you have to give me the answer. No validation will be available. If there is no perfect prediction, you will lose. So test data is that semester exam. And validation data is with your kind of assignment and other things. It's something like this.
Thank you so much, sir, for that stimulating session. I would like to now call upon Mr. Joel Jomachin to present the token of appreciation.
Thank you. Thank you so much to Bombay section for that.
Thank you very much, sir, for joining with us and giving insight of the session.
So hello, a lovely and a warm afternoon to everyone present here and to you, Dr. Ashish Josh. On behalf of the IEEE GRSS Bombay Chapter and the entire organizing symposium team, I would like to gladly take this opportunity to spread my most sincere thanks to all those who have contributed to this session on machine learning and remotely sensed data analysis. I'd like to thank our esteemed guest, Dr. Ashish Ghosh, for having a talk with us and sharing with us his findings and opinions today. We've been really enlightened by your knowledge, presence, and how you explain machine learning in such an easy and approachable way. I'm sure that our audience attending would have found this session really beneficial and essential and insightful in many ways. I would also like to take this occurrence to thank the entire committee as well as the audience for representing their valuable views and making the session a really good experience. Thank you so much, sir.
Thank you. Thank you so much.
Sir. Thank you very much.
All the members of Bombay section.
Thank you,
let us
sir.
have more questions. Thank you.
Thank you, sir.
Yeah. Can I leave now?
Yes, sir. Yes.
Okay. Thank you. Thank you, Amina.
Next up, we have a research and development presentation session, which will be coordinated by Dr. Ujjwala Bangale. She's the web coordinator, IEEE GRSS Bombay Chapter. She is an associate professor at KJ Somaiya. She has completed her PhD from IIT Bombay in the domain of mining massive remote sensing data of disasters using HPC approaches. Over to you, ma'am. Ma'am, you're muted.
Sorry, extremely sorry. Yeah, thanks for the kind introduction. Good afternoon, dear all. I welcome all the participants for this research and development presentation session in the geospatial domain. I welcome the students and researchers who will be presenting their ongoing work in the geospatial domain. I also take opportunity to welcome our judges, Dr. Prakash and Dr. Ujjwala Bangale, who have shared their valuable time with us today. So yeah, Dr. Prakash, he did his bachelor's in electronics and communication engineering. He later pursued the master's in remote sensing studies from Andhra University, Visakhapatnam, after which he joined as a teaching associate in JNTU, Kakinada. He pursued his doctoral studies in geospatial technologies from Center of Studies in Resource Engineering, IIT Bombay. After finishing his doctoral studies, he joined as a project consultant at World Resource Institute, India. His research area includes machine learning, geospatial technologies, spatial modeling in the domain adoption. So presently, he's aspiring for the postdoctoral studies. So thanks a lot, sir, for joining us today.
Thank you. Thank you so much.
So other judge is Dr. Ujjwala Bharambe. So Dr. Ujjwala Bharambe is an assistant professor of computer engineering at Thadomal Shahane Engineering College, Mumbai. She received the BTech and master's in engineering degree in information technology and computer engineering from Mumbai University, and then a PhD degree from IIT Bombay in 2019. She has over 18 of rich teaching experience in computer science. Her research focuses on probabilistic graphical models, semantic technology, multi-objective optimization, natural language processing, and information retrieval. So thanks a lot, madam, for joining with us today. Okay.
Thank you.
Yeah. So just to inform the judges about the diversity of participation in this presentation session, we have some presentations where the ongoing work is at undergraduate level, master level, and PhD level. So kind request to consider this diversity while judging the work. And then presenters, make a note that we already been delayed for this particular session. So the maximum time you'll get 7 minutes to present your work, followed by the question answer session of 5 minutes. And then IEEE GRSS Bombay Chapter has declared 3 prizes for this event. And these prizes will be declared in today's concluding session. Okay. So that's it from my end. Hand over to host again.
Thank you, ma'am. So moving right towards the presentations. The first presentation is being presented by Ms. Vaishali Kavadekar on the topic Lilac classification from Don Bosco Institute of Technology. This presentation is done at master level. Ms. Vaishali?
Yeah, I'll just share my screen.
Yeah, sure.
Graduate, it's not master, it's a PhD level, in fact.
Okay. So this is a PhD level work on lilac classification by Vaishali.
All right.
Hope my screen is visible.
Yeah.
Okay. Okay, respected dignitaries and all my fellow participants. Just give me a second. Good afternoon to everyone. Myself, Vaishali Kavadekar, and I'm working in Don Bosco Institute of Technology as assistant professor. And my topic for research is assessment of urban land transformation and its impact on urban microclimate using machine learning techniques. Yeah, so the introduction. The surface of the earth is rapidly changing. As we all know that the surface of the earth is rapidly changing, maybe due to some of the natural reasons or maybe due to some of the human intervention. So the natural reasons are such as the earthquake, floods, droughts, and so on. But more effect is due to human intervention, such as due to overpopulation, urbanization, industrialization. Due to this, there is a lots of degradation is there in the environmental resources. Like what we can say that due to this urbanization and this kind of overpopulation, there is a natural degradation is there. As we can say that there is a deforestation is there, vegetation index is getting degraded, water degradation is there, and so many other effects are there. So there are a direct impact onto the societal and environmental health is there. Now, what kind of a societal health problems are there? Due to this kind of a degradation, one side the degradation is there and there is a direct effect onto the climate. So because of that, there is a respiratory problems are there. Not only the respiratory problem, but there are various types of the diseases are there, such as the cancers and maybe a birth defects are there. So this kind of health issues are possible due to this kind of a natural resource degradation. Whereas the environmental health is there, that due to this kind of urbanization or increasing population, there is a degradation in the resources such as the deforestation, water degradation, and vegetation indexes. So when we are talking about one side, there is a degradation and one side there is the urbanization. So we can say that the direct impact is there, that is a land transformation. The land is transforming from one form into the other form. So there is a future need to study this kind of a land transformation and its effect onto the societal and environmental health. So due to this, there is a lack of studies in this area, so that the city planners are facing lots of challenges when they are designing this kind of a smart cities. So there is a requirement to create this kind of a model which will be helpful for the decision maker to take a right decision at right time. So when we are talking about the effect of urbanization on natural resources, as we had already discussed that degradation of various resources, because of this degradation, there is a direct impact is there onto the land surface. So that land surface or the urban land is day by day it becoming a heat island. So that the term comes, that is a SUHI, that is a surface urban heat island. So urban island is not only the island, it becomes a heat island day by day. So that there is a need to create a prediction model which will be helpful to identify this kind of a urban heat island, or we can say the hotspots, and predict the future hotspots. Okay. So as we all know that there is an enormous amount of data is available, which can be captured through satellite images. There are various satellite data is available. Out of that, few data sets is open source, that is everyone can access it. Some are we need to purchase it. So just a minute. Yeah. So when we are talking about this kind of a satellite data, why can't we use the satellite data to gather the or to identify the information from this data, so that the land transformation or land use, land cover changes is one of the major identification we can perform using this land transformation studied with the help of remote sensing data or a satellite data. So with the help of this study, we can identify the changes which has happened in the land use and land cover in the urban areas. Yeah. So when we are talking about urban heat island, here we can see that this is the rural area and this is the urban area. In rural areas, the land is a green land, whether it is a vegetation, whether it is a grassland, whether it is a mangroves or whatever. So this is the green land is there. So the heat which is absorbed by this green land is less. Second thing, because of this green land, there is a water, there is a greater cooling effect is there due to evapotranspiration. That is called as evaporation and transpiration. That the plant or a green plant is what we can say that emits the water droplets, and because of this water droplet which is emitted by this green plant creates a cooling environment around in that surroundings. The second main reason is there, that is a rainfall. So there, because there is a more amount of soil is there, the greater ground storage of rainfall is possible in this urban in this rural areas. Whereas when we are talking about the urban areas, lots of concrete and construction buildings are there which can retain the heat. So more heat will get absorbed in this construction. Second thing is there, due to these constructions and concrete road, there is a runoff. That is the rainfall which occurs. There is a less ground storage is happen due to this kind of a concrete structures. Next is there is a less green land is there, so there is a no cooling effect. So there is a no natural cooling effect. There is no transpiration or transpiration in this region. So this is the direct impact is there, that the urban heat island is more hotter, we can say, compared to the rural areas. Now, some kind of adverse effects are there due to this kind of temperature difference into the urban areas and the rural areas. The first effect, that is the increasing energy consumption. So if the area is more heat is there, obviously there will be a more energy consumption is there. Elevated emission of air pollutant and greenhouse gases. We need to compromise with the health and our comfort. There will be the water quality is getting degraded. Now, so the urbanization and direct impact onto the degradation of the natural resources. The main reason is the population. So this study says that the report shows that the global urban population 751 million to 4.2 billion in 2018, and for 55% of the world population is staying in the urban areas. The global proportion of the urban population is expected to be 68% by 2050. When we are talking about the India, 460 million people will be shifted to urban areas by 2050. So that the figure shows that day by day, the population in the urban areas is going on increasing. And there is a need to create some kind of a model which can be identify the land transformation and its cascading effect onto the heat island. So the statement of the problem is the land surface temperature of the urban metropolitan region is always greater than the rural spaces. This temperature difference and heat waves generated in urban region has a direct impact onto the environmental health and human health. There is a future need to identify this urban heat island or hotspots in the metropolitan region and predict the future hotspot in the particular region so that the decision maker can take a right decision at right time. So in the proposed research, a model can be developed to predict the future urban heat island is that hotspot by accessing the rate of urban land transformation and its effect onto the urban microclimate. Now the study area is India, Mumbai, Maharashtra, Mumbai region. So as we all know that this is the Mumbai region, which is developing towards the suburb, Mumbai suburb, then Navi Mumbai is Thane, then it is already expanded towards the Bhiwandi, Kalyan and so on. So here we can see that the areas, urban area is day by day, it is increasing. So obviously the built up land is also day by day, it will be increasing. Now, the data set, as we said that lots of satellite data are available, some are free, some are paid version. Out of that, the US government has, this is a publicly available data set that is the Earth Explorer USGS GOV. So there are various Landsat, there are various.
Yeah, presenters are requested to stick to the timeline. So please try to.
Yes, ma'am. Yes, ma'am. Yeah, so there are various Landsat images are available. Out of that, the Landsat 8 is the latest images. With the help of Landsat 8, I'm trying to identify the various land types. That is the agricultural land, built-up land, grassland, water bodies, and wetland. Out of that, built-up land is due to urbanization, whereas the agricultural, grass, water, and wetland all are the natural resources. When we are talking about the classification of this land use land cover changes, we are using some kind of a machine learning techniques, or the researchers had already used machine learning techniques such as unsupervised, supervised, and semi-supervised techniques. So in my research, I'm going to use a supervised machine learning techniques, and with the help of that, I'm trying to identify the normal vegetation index, normal water index, normal soil adjustment vegetation index, and then normalized differential built-up index. And for this type of a classification, there are techniques are there. The researchers have already worked with it. Out of that, the maximum likelihood classifier and random forest classifier is one of the popular technique which gives a better result in these cases. So maybe this kind of a classifications result will be there. That here I showed you the data about the 1992, 2002, and 2011. That is a 10 years gap is there between these images, and you can clearly see here that the red color is the urban areas. And over a period of time, the urban area is going on increasing, whereas the grassland and forest land is going on decreasing. So the blue color is the water bodies. So here you can see that the water bodies are decreasing over a period of time. So this will be the model, that is the Landsat 8 images. Need to perform some kind of a pre-processing. There are different bands are there, right from band 1 to band 8. Out of that, the optical band, that is band 2, 3, 4, we are using for land use land cover classification. Here we are performing the classification. We are identifying the NDVI and NDBI, that is a built up land and vegetation index. And then we are performing the change detection. At the other hand, with the same images, there are different band is there. That is a thermal band, that is a band 10 and band 11. With the help of thermal band, we are trying to identify the land surface temperature for that particular images. And then here we'll get the urban heat island or non-urban heat island delineation And here we'll get a classification, and with the help of classification, its direct impact onto the UHI, and we'll try to create the correlation between these two. Once we'll perform this kind of a correlation, based on that correlation, we'll predict that what will be the future urban heat island effect, or what will be the future hotspots in particular area or in particular city. So the conclusion is the spatiotemporal variation in the surface of the land. One of the major impact is the urban land becomes a heat island day by day. The situation will be worsening if this spatiotemporal variation continues. A model is required to identify the current and predict the future hotspots in the urban region. Government official or NGOs can take a proper decision at right time and right decision at right time, so that reducing the greenhouse gases, increasing the vegetation index, diversing the population density, or to avoid the adverse effect of human and environmental health. So this is the aim behind my research. And these are some of the references. Thank you.
The judges, do you have any questions?
Yeah, thank you, Ms. Vaishali. I have one suggestion. Like this urban land use land cover, this approach appears to be a simple classification approach by different, machine learning techniques.
Yes.
So in your presentation, you were mentioning about the prediction part, I think that's what I understood from your initial introduction.
Sir.
So, but you were showing what was already there. Okay, so one thing which you can do is how you can use some regression analysis to predict, how the spread can happen, and if you can show that as an animation, how the growth can be 10 years or 20 years down the line. I think that will add some value to that work. Okay. Okay, sure. Thank you. Yeah, it's a nice
So this land use land cover is one module. And then based on that module, we are going to, in the second module is the thermal analysis. And based on that, we are going to perform the prediction.
Okay. Sure. Okay. Thank you so much.
Dr. Ujjwala, you have any questions?
I think Madam is experiencing some issues in the line. I think let's move with the next presentation.
Yes, ma'am. Sorry.
We'll move to the next presentation. I think Dr. Ujjwala is facing some.
Thank you.
So the next presentation is by Mr. Ajit Kumar on the title, A Hybrid Approach to Retrieve the Soil Measure Moisture from the SAR Images. It's from Media Arts Science and Management Science College, Bede. The work is done at a PhD level. Mr. Ajit Kumar?
Yes. I'm sharing my screen.
Yeah, sure.
Okay. Is there my screen?
Yeah, it's
visible. Okay. Thank you. Good afternoon to everybody. Today I am going to present a work which is funded by ISRO SAT Ahmedabad. The work is a hybrid approach to retrieve the soil moisture from the SAR images. In this, actually, we are going to retrieve the data of the geophysical parameter of the soil by using SAR images. For this work, we have used the study area of Bede, right? In this, we have selected some geographical area by means of which we can collect the field data as well as SAR data. On the basis of our requirement, we have collected 50 samples from each sample site right? And then again, the SAR images from the Sentinel-1 data. After that, we have processed the data.
Sanjit, your presentation is not moving.
Not moving. Okay.
You are presenting the PPT screen.
Is there any movement?
No.
So can you stop this share and restart it?
Okay.
I have to present the presentation screen.
So you need to share the presentation.
Is there?
Sir, you stop this and share the presentation mode.
Okay.
So you can use the F5 key on the keyboard.
Okay. Is there any movement?
No, sir.
Okay. Once again,
it will present it and then start sharing.
Yes. Is there? I have shared my screen.
So have you shared the entire screen?
Yes.
Okay, so now can be seen. You can move ahead with the presentation.
Can you see my screen?
Yes,
now?
sir. Yes, sir.
Okay.
Yes, sir.
Okay. Is there any movement?
Yes, sir. It's visible. You can.
Okay. We have selected 8 districts actually. For the sample sites, we have collected 50 samples from each site, and corresponding we have downloaded the SAR images from the particular slide. Then after we go for the processing of SAR data as well as for lab experiment. In the lab experiment, we have found the soil moisture from the sample data, and again we have retrieved the data from the SAR images. The retrieval of those data is based on the previous method which is given in the literature, and this table shows that we have selected the different sites for the different samples, right? Then we are using the different method of processing, in which first we have selected the raw images from the Sentinel-1 satellite. Then after go for geo registration and determine the backscattering coefficient, which is known as sigma naught. After that, removing the speckle noise and vegetable correction, then we calculate the sigma naught images and implement the semi-empirical model such as OH model and MDB model. After that, we retrieve the soil moisture from the SAR images. In this, we have found the many equations from which we have selected some equations, and inversion of that equation is used to implement the hybrid model. Actually, hybrid model is the concept to use 2 different models for the sake of simplicity. By using this fusion, we can overcome some physical parameters which is very difficult to measure at the field site. For this fusion, we have used O model and MDB model. These are the some inversion equations which is from the modified diverse model, which is known as MDB model, given by Baghdadi et al. In 2016. Then after the inversion of this model, we have implemented both the models with the help of NV software. And after that, these equations are used to calculate the retrieval values of soil moisture and other surface parameters. You can see at the screen, we have details of ground samples calculations, and we have SAR image calculations. From these calculations, you can see the compatibility of the image values as well as field values, right? After that, we have used the regression model to find the compatibility of the soil samples, lab testing, as well as the data which is taken from the SAR images. These are the some snaps of the graphical user interface which we have implemented or developed during the research. In this, we have implemented first the retrieval from OH model, then inversion of OH model. Then after, we have implemented MDB model and inversion of MDB model. From this, both the data is fused, and then we can get the value of retrieved soil moisture and dielectric constant from the field. This is the advantage of our hybrid model. Yes. Thank you. Any question is there?
Hello.
Yes.
Hello, sir.
Yes,
Am I audible?
Yes, ma'am.
So, sir, you said that you have applied two model, basically OH model and MDB model. So,
MDB model, yes.
yeah.
Sure.
So, sir, can you just tell us that what are the advantages and disadvantages of these models, so that you require to, use the combination of both one?
Actually, O model is given for the full pole data, and DBIT model is also given for the full pole data. Full pole data, it means we have VV, VH, HV, and HH polarization. But in Baghdadi's model, they have implemented the modified DBIT model, which can be implemented to the two-band data also. But in that model, they required the physical parameters like surface roughness and soil texture. And O model also uses those parameters, right? In O model, they have been defined two parameters, which is P and Q. P is called copolarization and Q is called cross polarization. Both are very, very, you can say, good models, but the surface roughness and the soil texture is very, very difficult to measure in their critical or complexity is there, you can say, or and we can't able to find the exact value of those parameters. So that's why I use these two models and surplus the requirement of soil texture and surface roughness.
Okay, sir. Sir, and you also mentioned that you use regression technique to compare the actual lab report and the data which you got it from. So, can you comment anything on the accuracy point of view of your model?
Yes, sir. Actually, first I have implemented O model properly, then MDB model properly, and we get the retrieval data for the same lab experiment, and then after fuse those models and make a hybrid model. And this you can see here the Excel sheet of the calculations, right? In this we have a sample which we have collected from the ground, as well as which we have tested in the lab. Again, the process data, the sigma naught images, and the fuse models data are also available, which is taken from the SAR data. After comparison, we have if we compare those models, then our hybrid model gives the 80% to 85% accuracy. It means you can say 80 to 90% accuracies are there.
Okay, sir. Sir, it is just a suggestion. It would be better if you can just provide a table of, maybe the accuracy of O model and then the MDB model and maybe the hybrid model of O and MDB model which you are proposing. So it would have been very easy for us to understand.
Yes.
Okay. Thank you, sir.
Actually, I have those comparison data also, but I have not taken in this PPT.
Presentation.
And
Okay.
yes, ma'am. Again, from your suggestion, I would like to add those things also.
Okay. Sir, one more thing in this particular graph, if you can go back, these are the this graph, same graph. So if you can see the right hand side, these 2 points are there which are very far.
Yes.
Yeah. So those are outliers, or I mean, why?
Actually, some data are taken. I think some one or two data are false data, which we have taken in this model for comparing the accurate tendency of the soil moisture. So that's why some data, some 1 or 2 points are lagging, or you can say discard from the line, straight line.
Okay. Thank you, sir. That's all from my side.
Okay, thank you.
Sir, can you hear me?
Yes, sir. Yes.
Okay.
Please.
So thank you for this presentation. So I have one question, like how big is the area which you've considered for this study? How large is this area?
This area is 3,000 to 5,000 meters square.
3,000 to 5,000 meters square.
Yes, after that we have divided into the small grids. Then we have taken the sample.
Okay. So you went to the field and collected with certain instruments, is it?
Yes.
The soil moisture. Okay.
Soil moisture, yes.
So if your model is not season dependent, so that means if it can calculate, accuracies like what you said. So is it possible to generate a kind of a soil moisture map on a weekly basis, or on a, or on how frequently can we, generate the soil map which you have obtained through this model?
Sir, actually, this model is restricted to bare soils. And if you want to generate those data, then this experiment can be extended with the help of IoT. If we use the regular data from the IoT and then model those data with this, those data is modeled with the help of hybrid model. Then after we can say this may give some accurate data in the regular interval for every site.
Okay, for how many days of interval can you generate a map like this?
Actually, sir, Sentinel-1 data, I have used Sentinel-1 data, which is taken regularly after 12 days from one site.
Okay. The reason why I'm asking is because this can be one area of thought. So if you can generate this soil moisture maps for every 10 or 12 days, probably that can help to do some, irrigation mitigation management, so that's what I had in mind. Okay.
Yes, you can do that, sir. For that, we have collected the data from 2nd of August 2019, 20th July 2019, 8th July 2019, 21 August to, June 2019. So we can generate those data also, but this experiment is restricted to bare soil only. We need to extend this experiment with the regular data, and we have to fuse the IoT method also, so that we can increase the efficiency of this model.
Okay, sure. Thank you,
Yes.
Mr.
Welcome.
Rajat. Yeah.
So we can move on to the next presentation. Thank you, Mr. Ajit Kumar.
Welcome, sir. Thank you, sir.
So the next presentation is again a PhD level presentation by Mr. Vijal Jain. The title of the presentation is A Novel Technique for Spectable Reduction in SAR Images for Evaluating Classification Accuracy. He's from Usha Mittal Institute of Technology, SNDT University. Sorry, it's Miss Vijal Jain.
Yeah, it's okay.
You can share your screen.
Yeah, I'll just try. Yeah, I hope it is visible.
Yes.
Okay, thank you. Very good afternoon, everyone. So the topic of my research is a novel technique for speckle reduction in SAR images for evaluating its classification accuracy. And I'm Vijal Jain. So before just starting with the presentation, I'll just give a quick introduction of what exactly is a SAR image. So basically, SAR is a coherent imaging technology that is capable of producing high resolution images of the Earth's surface. So it has the ability to operate at night and in adverse weather conditions, and hence it overcomes the limitations of optical and infrared systems. So basically, SAR has various applications in the remote sensing domain, but the SAR images are contaminated by multiplicative noise, which is known as a speckle. Okay, so basically, SAR images are formed by processing the returns from the radar pulses, and these pulses are not coherent in phase, due to which because of the roughness of the Earth's surface, these pulses are basically not coherent in phase, and hence the combined effect of these pulses in a single cell, they lead to a speckle noise. So that is where, I mean, the main objective of the research comes into picture. That is, I'm trying to develop an effective filtering method to reduce the speckle noise with less loss of edge information. So basically, the speckle noise should also be eliminated while retaining all the edges and the fine points of the SAR image. So that is the idea of the research. So in the proposed system, I'm using two domains, that is the spatial domain as well as the frequency domain. So this is the proposed system. So the figure basically explains the proposed speckle suppression framework which is being developed. So a boxcar filter is used to suppress the noise components. So the reason to use boxcar filter is that it is easy to implement and gives a good smoothing effect. And in spite of its simplicity, the boxcar filter is still optimal and requires very less computational time. So I'm using two different mask sizes for the boxcar filter. On the original image, first, the boxcars of size 7x7, the window size will be 7x7. This is used to reduce the maximum noise. So the maximum noise will be eliminated by this particular filter, that is the 7x7 mask boxcar filter. So this step will result in an effective speckle suppression. But what happens is the homogeneous, like from the homogeneous areas, we can remove all the speckle noise, but the fine details will be blurred due to the non-selective averaging of the boxcar filter. So the original image is then transformed to the frequency domain using discrete Fourier transform, that is DFT. And how much amount of edges needs to be highlighted, and that can be controlled by tuning the cutoff frequency D0 while performing this high pass filter. So boxcar filter is then applied on the transformed image. So the resultant images are then added together to get the final speckle free image. So here in this particular proposed work, what we are doing is we are eliminating the maximum speckle noise by using the 7x7 boxcar filter, and then to regain back the edges and the fine details which were blurred by the boxcar filter, we are transforming it into the frequency domain, and then we are running a 3x3 boxcar filter, which is like a very small mass filter, and hence we make sure that the edges are not blurred over here. So to evaluate the performance of the proposed filter with the existing filters, these are some of the techniques which were taken into consideration. That is, first is the coefficient of variation, which will define the level of smoothness in the homogeneous areas. So the lower the value of the CV, that is a good indication of decrease in speckle. The next is equivalent number of looks. Again, this is just another indicator. So the higher the level of ENL, the better the performance of the filter. And the third one over here is the ratio image. And the last matrix which is considered is the ESI, that is the EdSave index. And ESI is used in both the horizontal and the vertical direction. So the data set which was considered for this particular, to apply this particular proposed work is the SAR data set, which is obtained by NASA JPL Caltech. It is an airborne data set, and it comprises of the C-band C-band image over the Flevoland Netherlands data set. So this is the result. So the first figure over here is the unfiltered SAR image. So we can see the small speckle noise which is there in the entire image. That is the first image. And then the next three images are that is a filtered image from the proposed framework, wherein we have tuned the D0 frequency to 2, 4, and 6. So this is giving this table basically will give the evaluation of the speckle filters, and we can see from the I mean, I'm comparing the boxcar filter, the leaf filter, the frost filter with the proposed filter, and we can see that the mean, the standard deviation, and the ENL, everything for the proposed filter is better than the existing boxcar filter, leaf filter, and the frost filter. So to also see whether this proposed filter works well for classification, like we already saw that the proposed filter was was working good enough to remove the speckle noise, but also as an application, from the application point of view, we just wanted to see whether
sorry to interrupt, but yeah, presenter, please follow the deadline when we are running out of time, so please
yes ma'am, definitely, yes. So the framework is basically divided into three parts over here. The first part is the speckle reduction framework, which is already explained. The second part is extracting the data samples for training and testing. And the last part is finally doing the image classification. So the Polsar data, which is converted into the equivalent T3 matrix. So this is the T3 matrix, T11, T22, T33, the diagonal elements basically. They are characterized by the multiplicative speckle noise. And the DFT framework is basically applied on T11, all the three channels, that is T11, T22, and T33. And on each of the channel, we have applied the DFT-based speckle reduction framework, which is already discussed in the earlier slide. And once we get the filtered T matrix, then we extract the training and testing samples from the filtered and the unfiltered data both. And then we finally do the classification process. So to study basically the effect of speckle filtering. So the aim over here is to study the effect of speckle filtering on classification accuracy. I'm considering leaf filter, the proposed filter, and no filtered data set. So the data set which is used for the classification is the SAR data set, which is obtained from LOS Pulsar 2. And this particular image covers a part of San Francisco, California in the USA. The size of the image is 5211 into 5564 pixels. And I'm working on three data. I mean, that is the study is basically for the work settlement and the forest classes, three classes basically. So these are the result. So the first result, that is the A part of the figure, is the unfiltered data. So the unfiltered image basically. The B part of it is the leaf filtered image. So the leaf filter is applied on the data set, and that's the result, the classification result. And the C part over here is the proposed filter, the proposed framework which is there. So this is the result from the proposed filter, the DFT based proposed filter. So we can see the classification accuracy. So for the water, settlement, as well as forest. So in the first over here, I'll just finally give the last table basically gives a comparison of all the three, that is water, settlement, forest, for unfiltered data, for the leaf filtered, and for the DFT based proposed filter. So we can see that for all the three classes, basically for the water, settlement, and forest, the DFT based framework gives a very good classification accuracy as compared to the unfiltered and leaf filtered data. The water class is anyways 100% the accuracy, but the settlement and forest regions are better predicted by the DFT based framework. So the comparison table finally, as we saw, the accuracy, classification accuracy of the proposed framework is 3.691% higher than the leaf filter, which is a renowned filter. And this is basically the conclusion. So to conclude, the framework helps significantly in reducing the noise, that is the speckle noise, and the combination of both spatial as well as the frequency domain together in one framework is helping us to reduce the speckle noise as well as preserve the edges and the point targets, etc. And the classification results also show the same thing, that is there is a better classification accuracy for the proposed framework. So and I've also compared the variance, ENL, SNR of the original image against the filtered image, and they all demonstrate promising results for the proposed filter. So these are some references. Thank you.
Thank you, Ms. Vijay.
Yeah.
The judges.
Thank you, Vijay. So, Vijay, you mentioned the starting that homogeneity play quite important role in overall, analysis. So, when you consider the data set, like for example, for settlement, have you observed any kind of, the characteristic from the perspective of homogeneity?
Ma'am, ma'am, actually homogeneous areas, like when boxcar filtered works on homogeneous areas, it works very good because since we do not have any edges, any point targets or anything like that, it can clearly remove the noise from those areas. But the problem comes when we have, point targets or some sort of an edges.
Like for example, for water area, obviously it will not create any problem
because
there will
so
be
that's
no
a
edges.
homogeneous area. So
Homogeneous area. So a settlement area is not a homogeneous area where you can see leaf filter and your other filter are almost giving the same value, 82, 81, 82, even the forest is 81, 82. And but if you see the settlement area, your proposal is giving 90, but for forest, which is little more complex, giving 84 to 85, we can say.
Yes, ma'am.
So if you want to boost these value, what could be the modification would you like to do?
Yes, ma'am. So the one thing is that this particular filter is just applied on one band till now. That is the C band. Yeah. So there is like the two other bands are yet left. Like I have not applied on the other two bands and combine the overall result. So it is just a C band data. So like L band and P band is yet remaining. So what I think is that, when we remove the span image, that is when I do it on all the three bands, apply the same filter on all the three bands, and then get a span image of all the three together, the accuracy would be much higher than the current accuracy what I'm getting for a single band.
Okay. And how many images you have considered, or what is your area size? I mean, regarding, can you describe a little bit of your data set? I mean, is it a generalized accuracy which you are talking, or it's with respect to certain specific?
So, ma'am, this particular data set is like from the satellite, which is the ELOS Pulsar 2 data satellite, and it covers the San Francisco area. So this is the San Francisco area. Like I've taken one part of the entire data set because it is like very huge image. That image is very, very big. So for processing it, like to get the processing speed a little faster, I've considered the size of the image as 5211 into 5564 pixels. Like this is my size from the entire big image of San Francisco, California. I've taken this particular size so that I can work on it. Yeah.
Okay. Thank you, Vijay.
Yeah. Hello, Vijay. Can you go to the slide where you have this flow chart?
Yes, sir.
The first one. Okay, yeah, thank you. So I have like one basic question. When you are saying you are reducing the speckle noise,
yes,
so I assume that speckle noise is also of high frequency, right?
Yes, sir.
But when you're passing that through a high pass filter, will not that speckle noise also pass through that filter?
Yes, sir, it will pass, and that is why once I'm passing it through the high pass filter, what I will get is all the edges, the point targets, like all the high frequency components basically, as well as the noise. But the noise which will be there will be towards the borders and components basically, and therefore we are applying the 3x3 boxcar filter even after that. So like once we get the inverse, like once I do the inverse Fourier transform and get the resultant image, which will consist of borders, point targets, as well as the noise, we are after that also applying again a boxcar filter. And this time the size of the mask of the box size filter is less on purpose, so that we do not fade away the boundaries and the point targets. We still have that, and then we eliminate the noise. So that's the point. That's
Okay.
idea.
Yeah, very nice. For your classification, what
Yes,
is the feature vector size? Like, what are all the features that you used?
So features, as in I have this particular thing I've done in the software, that is the NV software. So what we have done over here is the image data set I've pulled out, and from there I have cropped a part of the image such that I get all the three areas, that is the water, settlement, and forest. And then based on that, I have extracted all the the values, that is the coordinate values for each and everything. And based on that, then this classification is done. So like it's
Okay, like here you have 4 components, right? VH, HH, and
yes, HV and V.
H.
Yes.
Yeah. So you use all these 4 components as features, or in addition, or some other band
No, sir.
values you use?
All the 4 components, HV, VH, and V.
Okay. Sure. Yeah, it's a nice presentation. Thank you.
Thank you so much, sir. Yes.
Yeah.
Thank you, Ms.
Shall I
Vijay.
stop?
Yeah. Thank you, Ms. Vijay, for your wonderful presentation. For moving to the next presentation, a gentle reminder to all the upcoming presenters to make sure that you stick to the given duration, since we are running back with time. The next project is presented by a group of undergraduate students from Don Bosco Institute of Technology, titled Optimized Shelter Accommodation, presented by Ms. Esther Fernandez, Ms. Jobinsi Prince, and Ms. Athira Lonapen.
Good afternoon, all. I, Esther Fernandez, along with my teammates Athira Lonapan and Jobinsi Prince, final year computer engineering students of Don Bosco Institute of Technology, Mumbai, will be presenting the topic Optimized Shelter Accommodation. This project is under the guidance of Dr. Amaya Kumar Tripathi and in association with Fields Data, a Norwegian NGO for humanitarian needs. In India, the effects of global warming have an impact on several states, with Odisha being one of them, as told by Relief Web. But is there tech emerging to help these states? Yes, we know that IMD definitely helps with issuing warnings pre-disaster. But what about smaller communities which only rely on the government's planning? SciDevNet says that villages in India are yet untouched by technology. After doing a background study on Odisha, we found that Kendrapara, which is a coastal district, was the worst hit with cyclones, floods, and heavy rainfall. The government takes over the entire evacuation process by sending people to shelters and observes a zero death toll. But there are other problems which we will discuss further. We also did an understudy on what they should be called while they temporarily live in shelters. We read articles by the UN which say that populations displaced within a state due to natural disasters are called internally displaced population, or IDPs. Further in this presentation, we'll be referring to them as IDPs. So why have we chosen Kendrapada? The following graph was made using the latest 2020 data provided by Odisha State Disaster Management Authority. It shows the vulnerability of the population and animals exposed to cyclones. Here we can see that Kendrapada is the highest among the other districts.
So we spoke to few people from different domains, like the founder of Udayama NGO, Mr. Pradeep Mohapatra, project manager at OSDMA, that is the Odisha State Disaster Management Authority, Mrs. Martha, who works in IOM, that is International Organization for Migration, and recently we spoke to Dr. Josiah Kaplan, who works at UNICEF UK. So here we try to narrow down the problems and fixed upon the problem statement that we want to work on, which is optimizing allocation of internally displaced population to shelters depending on the available shelter capacity.
There was a lot of research work that went behind this fixing of the problem statement. As per OSDMA, that is Odisha State Disaster Management Authority, they stated that there are a total of 116 shelters and the total vulnerable population is 2,73,937. So the allocation in each shelter approximately comes down to 2,361. But there was a report by IIHS, that is Indian Institute for Human Settlements. They had surveyed the cyclone-prone zone, and as the government had stated that in each shelter, 2,000 to 3,000 people can be allocated. But when they interviewed the locals who actually went through the process, what they came to know is that even with 1,000 people, the shelters were overcapacitated. So the numbers lack transparency. We also had a talk with Gopal Barik, a research intern at OSDMA, who said that the shelters are usually overcrowded and there is no technology as such used for the allocation process. With respect to the scope of the project is limited to the state of Odisha and particularly to the district of Kendrapara. We have started with sub-district Patamundai, which has 10 multi-purpose cyclone shelters in 153 villages.
The proposed design, or you could say the solution to this whole problem, is as follows. We have a web interface which would have shelters and their capacities mapped onto, and users will be able to enter their source location and the number of people accompanying them, which would then be deducted from the capacity of the shelter, and the shortest route to that shelter would be displayed for the next user to be able to see the modified capacity. The architecture is as follows. We have the data collection, where we will find the location of each shelter and the area of each shelter, thus finding out the number of people who can be accommodated in each. We will then map the shelters using QGIS, that is Quantum GIS, and use a base map as OpenStreetMaps or OSM. And for route optimization, we will be using Python's OSM NX library. All of this will be available on a web user interface where the user can enter their location.
So the data collection process is divided into two steps. In the first step, from the list of shelters we obtained on the net, we have been searching for the coordinates and mapping them. For the second step, for knowing the area of the shelter, we have made a COBO form to be circulated among the shelter officials through Udayama NGO's founder, Mr. Pradeep. So this is the COBO form that will be circulating to the shelters. And to start implementing our idea, we first use dummy data set. To know the capacity, we first need the area, and from the SPEAR handbook, which has all the minimum standards to be followed while setting up camps, it was known that 3.5 square meter of living space per person is required. And so accordingly, using random numbers between 3,000 to 4,000 square feet area, we divided it by 3.5 to generate the capacity.
With respect to implementation, we started mapping the shelters along with the capacity on QGIS. We also tried finding the routes between the shelters, but yeah, we did face a challenge. The roadmap that we obtained online only had the highways and not the intricate lanes, because of which we couldn't join the source to the destination as is seen on the slide, which in this case, source was Singhagarh and the destination was Badaipada. So we couldn't join it because of the lack of roads. With the view of automating the process, we worked on an alternative because using QGIS as a separate software would make it difficult to automate the entire process. So we used volume library to visualize the shelter coordinates, which we obtained using geocoding, that is converting the address to the coordinates, and then map the capacity as well. We then used OSM NX Python package to analyze and visualize the road networks. And we aim to find the shortest route to all the shelters from the user location and compare it to find the nearest ones. But the problem of road network still was unresolved. So we tried out digitization. We initially considered 3 points, which represented 3 shelters. And these points formed a triangle. And for the purpose of testing out the model, we'll be choosing a user location from within this triangular area. So we vectorized the roads using the line feature and the borders using the polygon feature. And once we succeed with this roadmap, we'll expand it to the further areas.
Lastly, we'll be showing the constraints for the entire project using linear programming. We have input variables Dij, which shows the distance between the location of the IDP, that is the user, and the shelter. Qi, which is the space for the number of people required. Bj, which is the capacity left in the shelter. And C, finally, the shelter capacity. We have decision variables for the entire model, where Xij would be the path between the roads, or the routes you could say, 1 if it is being visited, or else 0. R would be the number of people in each shelter, and Pij would be the number of people required to be allocated from source I to destination J, which is the shelter. Our main goal is to minimize the total distance for the user, that is the IDP, to their nearest shelter. So we have Z, which is subjected to Xij or J or Ji equal to 1, which means that every person will be allocated only once. We will not be having subtours and roundabouts, and hence to eliminate the two, we have the following conditions. For maximum capacity constraints, we consider R, which is the number of people residing currently in the shelter, and Pij, who are the number of people required to be allocated in that shelter. The summation of these two will always be less than equal to C, which is the shelter capacity. And X values will always be either 0 or 1, which means that the edge is visited or not visited, which suggests the path is being visited or not. Finally, the whole model is subjected to non-negative variables, which means that R, that is the number of people in the shelter, will always be greater than equal to 0. There cannot be negative amount of people. And similarly for Pij, which means that the amount of people required to be allocated from I to J will be greater than equal to 0. Finally, we come to the case scenarios of capacities cases. The first case being sufficient capacity, where the number of people to be allocated in the nearest shelter is sufficient enough. And here we will directly allot these people to their nearest shelter. The second scenario is zero capacity, where the nearest shelter has no space left. That is so in that case, the IDPs will have to find the next nearest shelter and check these 3 cases again. For an insufficient capacity, that is, the capacity available in the nearest shelter is not enough to accommodate all the IDPs wanting to go in that shelter. In that case, we will allot these people in the nearest shelter until its capacity is full, that is, it has reached 0 and it can accommodate no more. And then we will allot the remaining IDPs to the next nearest shelter and then check these capacity constraints again.
So to conclude our project, the people would be accommodated to the shelters without any hassle. And since technology is involved, the process would be much faster. And despite the scope, it can be used for any other district if the data is available for the same. So these are few references that we used. Thank you.
Judges.
Hello. Hello, Esther and your team. It's a nice presentation. So I have a couple of questions. So can you go to that optimization equation which you have framed? The slide where, So, so this one, you have solved this as a linear equations, is it? So,
yes, sir.
Okay. So this formulation is your own model.
Actually, we've taken it from a reference, but they had used it for in context of what they were searching for, whereas we have used it in a form of for finding our nearest shelter. So we wanted to specify constraints for the entire model, saying that every person will be allocated only once, and we want to minimize the distance as such. So we use linear programming to define these constraints instead of just writing them down as lines.
Okay. So so how much would be a capacity for each shelter? The number of people?
So that depends upon the area of each shelter. So depending upon, we will be sending out forms actually to each shelter around in Kentapara region to find out the area, and then we will be getting the number of space required for each person as suggested by the Sphere Handbook, which is the international standards, is 3.5 square meter per person. So doing the math, you can find out how many people should actually be allocated in each shelter so as to avoid overcrowding in it and other problems.
Until we receive the actual data, we'll be going ahead with the dummy data and then replacing it when we receive the actual data.
Okay. Yeah. Why I was asking that is because I think your final target is to have a mobile app for this application, is it? So only then the users will be able to, geolocate themselves as quickly as they can. Is that so?
Yes, sir.
Okay. Were you able to deploy it as an app?
The implementation is still on, sir.
Okay, sure. Nice. Yeah, congratulations. Good. It's a nice presentation.
One of my basic question is this only the nearness or the distance is the only criteria for the allocation? Because when you want to allocate, there could be multiple criteria, the availability of resources and all. So at this moment, you are considering only one criteria, as per my understanding.
Yes, ma'am. To be honest, there would be two cases into consideration, that is the quality and the quantity. So quality as in the facilities as per the latrines or the water that would be supplied in that particular shelter. So considering the time constraint, we went for quantity first, that is the capacity. And the quality thing is a future scope that we have to incorporate with. This wouldn't be the ideal solution, that you're absolutely right, because we'll have to consider the facilities provided. So with the time constraints that we have, we'll be focusing on capacity first, and then as a future scope, we'll be considering the facilities. We did find in the Sphere Handbook about as to what are the minimum facilities required, the latrine, how many people should be sharing a latrine. We did compare that, but the actual data, that will take a little more time to receive. So we went on with the capacity.
Okay. There is just one suggestion for resource allocation. There are because this problem is basically a optimization problem. Okay. There are lots of alternative algorithms are available for resource allocations. So rather than directly using only linear programming model for allocation, you can use some ready-made optimization algorithm. You just need to design your problem, using those optimization algorithm. There are lots of libraries also nowadays available. Okay. So you can try with those libraries and you can model your problem, and then I think you will get little better result than traditional linear programming model.
Okay, sure, ma'am. We'll take your suggestion.
Thank you.
Consideration. Thank you.
Thank you. That was an amazing presentation. Moving on to the next project, which is a master's level project titled Decision Support System for Groundwater Governance by Mr. Tayyib Ali Syed from Don Bosco Institute of Technology, Mumbai.
I hope I'm audible.
Yes.
So I have very few slides. I will be showing a lot of demonstrations. So as you see, it's a decision support system for groundwater governance. So the problem which we face in groundwater governance is there is unplanned and rampant use of the groundwater, and there are rules by the government, but there are no systems which can track. So basically, whoever owns the land, the groundwater beneath that surface, he owns. So he can have any number of boreholes. Even if there is a restriction, we don't have system to track. So we want to make a system which is kind of crowdsourcing, like a Wikipedia model based system which can be used to know and track by the people for their level. So it can be deployed at a village level and a district level, taluka level, but basically people's involvement is there. So what we propose is a web-based solution. We have mobile apps also in future, and it should be very user-friendly in their local native language. So these are some of the requirements. Just to give you a basic understanding of groundwater, see the groundwater management, the latest study shows it should be done at the aquifer-based aquifer levels. Here, what we will be doing more about it, like based on the consumption level, we have planned to use aquifer level also. But the pandemic, we could not go into research on aquifer base. We have also chosen a study area which so scope is to make a decision support system. We are focusing on Manawar district from which I belong. So we won't have any problems of communication and data gathering. We will be having a lot of graphs, maps, charts, which will show the dynamic real-time data. Obviously, some data which we will try to go and collect. Some data we will have some volunteers. So those people who are enthusiasts in this particular area, they will contribute. That is what we see. And we will have some kind of verification method which avoid the problems with the data quality. And then finally, we will have some kind of prediction or some kind of decisions so that village at a village level, taluka level, people can decide what is happening. So we have covered a lot of systems. We have famous Andhra Pradesh government has done similar dashboard and some reports followed from groundwater survey and settled groundwater. So this is a web flow. People will come register. If they are registering as a volunteer, they will be able to add. There will be statistics. I'll show you all these things. And data collection can be through volunteers. It will be at a village level, at a taluka level. We have groundwater charge structures. We have calculation of how much artificially recharge and how much natural recharge is happening. Based on the groundwater availability and water level, you can even predict how the water allocation should be done, industrial irrigation or crop for the domestic purpose, etc. You would also be able to find out actually how many wells or wells have water and what is the milk using the heat maps, etc. So these are the technologies. So using Django framework, using some machine learning tools. So we are not focusing more now on machine learning tools. We want to make app first, and then once we start getting the data, at least for some pages, then we can work on the data and analysis. And obviously, one more, the scalability remains the challenge. We have to make this particular thing scalable so that we can accommodate a huge amount of data. So if we go to the demonstration. So first, this is the study. I'm referring this 3D Mapper website. this is the village called as the Sheep from Manala district. So we wanted to make a 3D map in animation software so that we can map the aquifers and we know exactly what is the elevation. So you can see this particular village is placed at such a level that there is elevation is like decreasing this side and this side, and there is a water. Then how it is. So you can see that the runoff from the village is high. So the other places there is a huge runoff from the village. So that is then demonstration of huge guys. So you see here, we wanted to do one more thing, simulation where there are schools and we want to find out if these schools implement recharge structures, then how much water we can capture from these schools. Then we have some borewells from map from the village, and we had taken the watershed data for this village so that we can find out where the recharge structures are. Then we have all the districts available in each one of all the villages. So such kind of analysis should be done for all the villages, and it should happen through a web interface. We have also watershed, so we know which are the villages which are coming under which watershed. We can do better analysis. We have a soil data also. So let me go to the dashboard. So we have, let's say we have selected this particular village from district. We have localization, language option here, population, average rainfall, then wells, inactive wells. So in the summer, the month wise, how many are active, inactive, pre-water, post-water levels, wells, you can see. Then it's a pie chart and all these graphs. So once this data is collected from the ground, you can see dynamically for your village. You have to sign up and go through this entire thing in your local language. Then we have a map, the same environment. You can filter, so we would place a shape file here so that you can see this manual district of the world. You can filter as per whichever. As you can see, there is no much data kept over here. We'll be adding all the data from one village. Then if you want to enter the data, so you have verified tab over here. All the administrators can verify whether this data is correct or not. And you can add here data, so you have a form here, you can add the rainfall data. So basically, once we do this thing, we want to show whether state of the village, groundwater state, is critical or overexploited or in a safe zone. Yeah, that's it. So make a dynamic model. So we have not worked much on the model, but we want to make a model which will adapt to the real time data and will tell you the signals. So which are the villages which are under critical severe, so that the government people or NGOs can take appropriate actions. So thank you. That's it.
Thank you, sir. So you mentioned in your slide that you're planning to also use regression analysis. So how are you planning and for what parameter you are planning for regression analysis?
So ma'am, see, what we had thought is from a village you have 100 wells, and we capture the usage, water usage, consumption data basically. So that's the numeric data. Then we have rainfall data also. And so if you have a population increase for next 10 years, then what will be the consumption? Or if you have certain crops based on the demand, water demand of these crops.
So basically, you wanted to predict the consumption water only. Overall,
we wanted to have classification also. Wells behaving similar patterns.
Okay. Okay. Thank you, sir.
Yeah, I have no questions, but this is a very nice presentation. Yeah.
Thank you, sir.
Yeah, great.
That was an amazing presentation. Moving to the next project, which is a PhD level project titled Urban Sprawl Monitoring Using Multi-Temporal Earth Observation Images by Dr. Dhanishri Kanade from Usha Mittal Institute of Technology.
Yes. Can I share my screen, sir?
Yes.
Is it visible?
Yeah, it's visible.
Okay. Good afternoon, everyone. I am Dhanishri Kanade, research scholar from the Usha Mittal Institute of Technology, SCDT Women's University. I am doing my PhD under the guidance of Dr. Sanjay Shitole. My topic for the PhD that sir has told right now, it was the urban sprawl monitoring using multi-temporal Earth observation data. From that, one of the part that I have done studies on that today I want to present here. It is the urban area classification using protocol L-band allows to SAR data, which is the case study of the Chennai city, India. Moving ahead to introduction of the urban sprawl, it is nothing but the rapid expansion of the spatial extent of the cities and towns over the large expanses of the land in an uncontrolled way. Means today nobody is going to think about the whatever the wastage of the land we are going to do with the constructions which is going nowadays without any control of any government as well as anybody else authority. Many urban areas such as housing, commercial developments, residential buildings and roads are increasingly drastically day by day due to the increased population also. Increase that going to lead with the increased energy use, pollution and traffic congestion. And there is very little concern for the urban planning. What is that effect of this urbanization that I want to discuss here? The land use fragmentation is going to be happen due to this urbanization, and this leads to the loss of biodiversity. Also, we are having the loss of agricultural land as well as the green spaces and the natural land. And due to increasing population, there is need for more infrastructure, which can cause the increase in the infrastructure cost also. Also, the longer travel times are increasing, and that is also leading to the automobile trips and cost of travels also increasing, which all resulting in the greater environmental pollution and which is going to degrade the urban ecosystem. So for this, how the urban area is the main problem for me is that it's a crucial task to study the influence of the urban area expansion, such as built up areas, open spaces, water bodies, etc., using remotely sensed data. Because I'm going to use the SAR data or mainly the Earth observation data for my research work. In that, it is very difficult to use this remotely sensed data because of the influence of the expansions. There are different types of expansions such as built up areas, open space, water bodies. So due to this heterogeneous structure, exactly what we can pick up as a urban area, that is mainly a research problem in nowadays. Urbanization is the fast growing concentration of the population, mostly in the metropolitan areas of and cities in India as well as abroad also with the environmental changes. So in my presentation, in my research work, I'm going to focus the Indian city, Chennai. Remote sensing imagery has been used by the recent researchers to describe the spatial structure of the urban environments and characterize the pattern of the urban morphology. As the urban structure are changing, we are having different characterized patterns as well as the morphology also changing. So it is a very much huge task, or you can say the challenging task to classify that various urban structures, and we have the exact mapping of that. It's a difficult problem for us. So in this study, we can classify the urban areas, or you can say the SAR data using supervised as well as the unsupervised classification. So in this today's work, I'm going to showcase the supervised classification. So satellite imagery classification methods can be of two types, supervised and unsupervised. In the unsupervised classification, we are going to collect the samples which are based on the classification already done, and we are going to take that training samples. Hold on. Sorry for the inconvenience. Sorry, sir. In supervised classification, training samples are selected, and based on these samples, classification is done. And these samples play as the key role, because on basis of that, we are going to divide, or we are going to classify the regions which are getting pixel by pixel. And in the unsupervised classification, which is going to generate the clusters based upon the similar structural characteristics, and is going to map with that characteristics, so that the unsupervised way they are going to classify the entire region. And each cluster is classifying without providing the training sample on its own. So the overall which is the methodology for my classification is, I'm having the quadrupole L-band allows to satellite data. On that data SAR, data pre-processing is done. In that adiabatic calibration is done. Generation of the polarimetric coherency T3 matrix is generated. After that, refine leaf filter is done using 5x5 window size. And after that, I have obtained the terrain corrected backscatter values. And after that, the classification work is applied over there. And that subset of the selected area is done. Means the data set is the entire image. From that, I have selected two subsets, and it is trained with the two basic classes, urban and non-urban, because my focus is only to characterize or to classify the urban area. So that's why I have selected only two classes, urban and non-urban, and then two models, that is the Vishal supervised classification, and in comparison with that, SVM classification I have carried out, and that both the classification accuracies have been checked, and the mapping is done between the two classes, urban and non-urban, and that entire quantitative analysis and the comparison is done at the end. For this study area, one of the metropolitan cities of India, that is Chennai, is taken as the study area for its urban expansion. Here, there are two land regions I have taken with the heterogeneous land uses, which is having high rise, high density, and medium rise, low density of the urban area, that is the city Chennai, is taken over here in the study. The image or the data is a fully polarimetric data having the L band, allows to synthetic aperture radar data, which was acquired on 20th May 2016, used for this classification study. So this is the entire image. So entire input image is having the very high resolution with the 15,204 rows by 10,888 columns. So this data I have divided into two land regions of 1,000 by 1,000 size, that is 1,000 rows by 1,000 columns. And both the classification methods have been applied on each data sets, and results have been produced with the two classes, urban and non-urban. So the first classification method is the Wishart supervised classification method. It is nothing but the interactive process for calculating the distance measure between each pixel coherency matrix and its respective cluster means, using maximum likelihood classifier, which is the main thing in the Wishart classification. Means in that we are going to check neighboring distances with the maximum likelihood classifier, and each and every pixel is classified into that classes. So this algorithm is based on the distance measure, and in that way the entire image is going to be classified, and at the end performance is measured with the help of confusion matrix.
Sorry to disturb, but can you please stick to the timeline?
Yes, ma'am.
Yes, you can jump to the
yes, ma'am. Yes. So these are the experimental results. So you can see the image A and E are my input sets, or you can see the two data sets which I have taken for the consideration. And after that, B and F are the training clusters, that is the common for both the images. And then I have classified that into this two SVM as well as the Wishart. Means C and E are the SVM classified results, and E and H are the Wishart classified results. So this comparison I can do with the help of this performance matrix that we call as the confusion matrix, and that algorithm is there, and as well as the SVM Wishart, and urban and non-urban classes are there. So if you observe, with the help of SVM classification, we are having the 85.81% of pixels have been classified, whereas in the Wishart we are having the 81.32 for the first subset. In the same way, for the another subset, we are having 86.31 of the SVM classified pixel, whereas it is in the 84.73% for the Wishart. So as we can conclude is that in this study, there are as compared with the Wishart supervised classification algorithm, SVM outperform, and it can be seen with this confusion matrices. So classifying the urban area into the non-urban areas, SVM performs better. So I can say in this particular experimentation and my research work, with the help of strong radar backscatter values, SVM classification algorithm performs better as compared with the Wishart. And this L-band frequency gives the strong backscatter values. So the acceptable classification accuracy is achieved for the both the experimental sites. So these are some of the references which I have used. Thank you. Hello.
Yes, judges.
Yeah. So no question in particular, but see the way the thing was implemented is normal classification approaches. But what you can also try is propose your own, application specific to this purpose. So I think that will be, a way of improvising. Okay.
Yes, sir. Sir, one more thing I want to add is that I have just done this one of the experimentation for my research work, but I'm going to plan to take the temporal data. It is there in my thesis title. So temporal data I'm going to collect. This is one of the data sample from the 2016. I can have the data for the 2005, then 10, then 15 and 20. So I can show how the urban area is growing over the decades or over the time series. And that, that I'm going to plot after this particular work.
Okay, thank you.
Thank you, sir.
Yeah, so Dhanashri, but do you think that if you are taking temporal data, the SVM will be the good algorithm for classification?
No, I have not predicted over here for the in comparison with the rest of the machine learning algorithm, because I'm going to explore other machine learning algorithm also. This was one of the module from my research that I have taken the SVM, and over the SVM next my future work will be I'm just going to compare with the rest of the machine learning algorithm, and mainly the random forest I'm going to focus on what are the results with that, so that I can more precisely say about the classification with the machine learning.
Okay. You can even try the XGBoost, which is the new algorithm which has variation of random forest.
Yes, ma'am, definitely.
Okay.
Yes, ma'am.
Thank
Thank you
you
for solution. Yes, thank you, ma'am.
Thank you. That was an amazing presentation. Moving to the next project, which is an undergraduate level project titled Landslide Prediction Using Quantum Machine Learning Approach by Ms. Neha Satish, Ms. Saloni Dotre, and Mr. Karan Doshi from Don Bosco Institute of Technology.
Is this visible?
Yeah.
Yep. So good afternoon. I'm Sneha Satish, and we are from Don Bosco from the Department of Computer Engineering. And my group members are Saloni and Karan. So landslides considered one of the major natural hazards causing loss of lives and property and degradation of the environment. Because future events cannot be predicted with certainty, management decisions are made under conditions of uncertainty. Currently, there are about 66 million people in Asia that live in landslide-prone areas. So managing this risk involves a multi-step process centered on identification, characterization, and prediction of landslides. So our goal is to propose a prediction method to predict the existence of landslides using quantum machine learning. So this can be very challenging because there are several factors that have to be considered. So the prediction method will be formulated to capture the significant features from the training model process. This is the plan for our project. So first we'll be collecting the data using both quantum machine learning algorithms as well as quantum machine learning algorithms, and then putting the quantum into the IBM quantum simulator, and then we will be comparing both of these. Our goal here is to show that the quantum ML algorithms perform much better than the classical ML algorithms. The architecture here consists of 3 steps. The data collection. So we'll be collecting the data from the Geological Survey of India, selecting a few parameters, pre-processing and training the data. After that, we'll be using the classical ML algorithm. Here we'll be using the SVM as support vector machine. It gives us a higher accuracy compared to the other ML algorithms. And then we'll be converting this classical data to quantum data, applying the quantum machine learning and comparing the results which we have got from the machine learning algorithms. Saloni, on to you.
So working on the data set, we referred to this website and collected the monthly data of only Maharashtra region from 2008 to 2020. Next slide. So when we had the data set, we were working on this. So initially we had the, sorry, the presentation went off.
1 second.
Okay, so initially we had this set of data set. The rainfall values were in millimeters, and this was the monthly data set. Let it go again. Sorry for the interruptions. Moving on. So, and the other data set was the boundary region of Maharashtra. Moving on, next slide. So once we run this, the data which we collected, we worked on it and we plotted a map where we could see that the Konkan region is highly affected by the rainfall. So our project is basically to find out landslides that are occurring due to rainfall. So now we know that the Konkan region is highly affected. Now targeting, okay, next slide. Okay, next slide. This is the side of the Geological Survey of India. So the problems with the data which we faced was once that the data was not tabular, not in the tabular format, and we had a report of it, and most of the landslides that were occurring was due to debris. Now, the landslides that were occurring due to debris could also be affected because of the after effects of the rainfall. So we didn't have the proper data set for the landslides which occur due to rainfall. The ones that you can see in that picture were the extracted which we made from analyzing these reports. Next slide. Then now that we see that the Konkan region is affected, the other factors that we wanted to consider was the soil and humidity. Next. So the factors that trigger the landslide are as rainfall, temperature, humidity, wind speed, and soil type. So next slide. Now, while we were doing a literature survey, we found out that the support vector machine algorithm runs better on predicting the data of landslides. And hence we are choosing that as our classical ML algorithm for comparing it with quantum machine learning algorithm. Next slide. So the quantum IBM quantum interface is sort of you work with the gates, and in a quantum world, the data is represented as in the form of superposition of zeros and one. So here is we get a higher probability of the prediction being accurate. Next slide. So these are the references and data sets and charts. So one more thing I would like to tell that recently we were working on this and we found out that there is a quantum machine algorithm of this SVM, which is quantum enhanced supervised support vector machine algorithm. So we are going to work on the algorithms of quantum composer, and then we are going to compare the results with the classical ones. We are expecting the quantum data predictions to work better than the classical ones. So this is our idea. If you have any questions and suggestions, we can start.
Yes. Thank you for that presentation. So I have one basic question. Like when you say it is a quantum algorithm, so in what way is it comparable to the traditional approaches? Is it in terms of speed, or is it in terms of the quantity of data that you are using? So how is it different from classical approaches?
All right. So now in classical world, we have bits as 0 and 1. They are distinct. But in when you come to a quantum computer, we have qubits. Qubits in that one position can be taken as 0 and 1 both in superposition state. And so this is how the quantum world works. As we know about the Schrodinger's experiment, cat experiment, the cat is both alive and dead at the same time, unless we measure it. So once we measure it, it falls down to either 0 or 1. So in that, we can get, so like comparing classical and quantum, the we can achieve maximum speed and accuracy both. That is the benefit of quantum computers.
Okay, so have you refer any literature where it has been said that the SVM or other machine learning algorithm performs better with the quantum version?
No, ma'am. Like there was like while we were working on this, we didn't like there were a few, but they had made their own algorithms, and the version of the IBM they didn't work necessarily on IBM quantum simulator or the computer. So they had only theoretical ideas about it. So we didn't find any paper which was working on a simulator or like this. But
Okay.
yes, there were a few which had a CNN version of quantum computer.
Okay. Okay. Thank you.
So moving on to the next presentation, this is the final presentation of today. It is a project titled Comparative Analysis Deep Learning Framework by Ms. Diksha Gautam Kumar from Saraswati College of Engineering.
Thank you. Can I share my screen?
Yeah, sure.
Kindly give me confirmation my screen is visible.
Yeah, it is visible.
All right. Good evening, everyone. Myself, Diksha Gautam Kumar. Today, I'll be presenting a part of a research from my PhD. So, talking about remote sensing image classification. So with the advent of technology, the remote sensing images have become, the quantity and the quality of remote sensing images have increased like anything. Now there is a very rich, I can say a big source, a huge source of images which is available to us nowadays very easily, and we need to explore it. And that is the need for a remote sensing image classification. When we talk about remote sensing image classification, there are various applications of this. We can use image classification for hazard identification, environment monitoring, vegetation monitoring, drawing the change map, city planning, road planning, and there are many other applications of classifying remote sensing images. So as I just said, that remote sensing technology is increasing, and because of which we have a huge source of images available, we need to explore them, and that is the objective behind this research. So over a period of time, it has been proved that deep learning networks can give better result as compared to other techniques when we are dealing with remote sensing images. Whether we talk about identification, detection, or classification of remote sensing images, deep learning algorithms have proved to give better results. Now, in today's seminar, I present a comparative analysis, a survey on various deep learning networks which are used recently for remote sensing images. All the networks, all the frameworks which I have chosen today are based on UNet. All the networks are improvement over one over another. So we will start with the first algorithm, UNet. UNet algorithm is again a advancement, you can say, in CNN. We all know that in CNN we have convolution layers, then we have pooling layers, then we have a repetition of convolution pooling. Finally, we have a flattening layer. But there's one problem which has been seen in CNN. In CNN, if we go deeper, if we increase the number of layers, at some point of time, the accuracy will keep on increasing, and then we will reach a point where accuracy will become stable. Still, it will not change, and after that, it will start dropping. That means the performance will degrade after some times if we will go on increasing the layers, if we will go on making the network more deep. So these are the algorithms which prevent that loss. So basically, as the name says, UNet, it is called UNet because it has this structure of U. So UNet was mainly built for segmentation in medical images, but UNet can work very well with remote sensing images also. So in UNet architecture, UNet framework, we have two paths. This is called the left path or the shrinking path. This is called the right path or the expanding path. This left path is a normal convolution path. We will have an input image. To that input image, we will apply convolution. When we will apply convolution to that image, we know that when we apply convolution to an image, let's say I have an image of size 8x8 and I apply a convolution filter of 3x3. We know that there would be dimensionality reduction. The result which would be obtained after convolving the input image, the dimensions would be reduced. As you can see in this case also, I took in this case, an input image was taken, the convolutions were applied, the dimensions were 572 cross 572. After applying convolution, it has started decreasing. Now it came down to 284 cross 284. Further applying the second layer of convolution, it will come further down. So the dimensionality, the features, the hyperparameters will keep on reducing. Now, in a normal CNN scenario, this becomes a problem because at every step we are losing some contextual information. So to overcome this problem, UNet was designed. UNet first applies convolution. After applying convolution, it starts applying upsampling. So in convolution, the dimensionality reduction is happening. After that, it applies upsampling. And when UNet applies upsampling, it does not only applies upsampling, but it takes the information from the previous layer and copies it to the next layer. So what happens when we come over here, we apply upsampling, then we will take this block, copy it over here. Then we will have one final block, which would be then again upsampling would be applied. When we will apply upsampling over here, then again we will take this block which is dashed, and copy it here, and then consider this entire block and apply upsampling, and then we will go on upsampling. So by this, UNet is able to preserve the information which can be lost in a normal CNN framework because of dimensionality reduction. So I'll just to maintain the time, I'll not go into detail. It applies max pooling, ReLU activation, and 3x3 convolution filters. Next to this was upgradation or I can say enhancement in UNet, which was attention unit. We know in an image, when we have an image, not every part of the image is important to us. There are certain region of interest in the image. Maybe the left-hand corners, the right-hand corners are not much of interest to us. So what an attention unit does is it only extracts the region of interest with the help of attention gates. So it will not take the entire image as a whole, but it will apply the attention gates to extract the region of interest, and then it will apply the unit architecture on that. So in comparing attention unit to the UNet, the previous one, in attention unit, we are applying this attention gate. This attention gate. This attention gate will act like a filter, and then it will move ahead. Next in series is ResNet, residual network. Now this is also a very beautiful architecture, a very beautiful framework. So we, since the beginning, we are talking about that the information gets, there's a loss of information. As we increase the number of layers, the problem of vanishing gradient will become predominant. It will have a major impact on the results. The information gets lost. There's dimensionality reduction. There is a loss of comprehensive information. So what ResNet does, it takes the data from the, let's say if this is the input layer, this is the input, it will take the input and it will copy it at some point after the two layers. So in this case, as we can see, this is normal convolution pooling layers. The input from here would be taken and it would be added to the output of second convolution layer. Then again, the same convolution pooling would happen, and the input from here would be added again to the output of fourth convolution layer, and so on. So again, by doing this, ResNet will make sure that the important information is not lost, and it will prevent the loss of vanishing gradient. And with like this is again, we use skip connections. So this is an example of skip connections. In a normal scenario, the functions of, if fx is the activation function, the output hx would be dependent on fx. But in ResNet scenarios, the output would be activation function plus x. What is this x? This x is the input which we have taken from the previous layers, as it is shown over here. So in a normal scenario where we don't have the residual networks, it is hx equal to fx. But in a residual network, the output would be the activation function plus the value from the previous layer. By this, we are preserving the loss of information. Then here comes the last framework which I'll be discussing, would be a DenseNet. DenseNet, again, we have seen that there's an information loss in the previous three frameworks. There's a problem of vanishing gradient happening. So again, DenseNet addresses that problem. So let's start from the very beginning. This is a normal CNN architecture where I have an image. I will apply various filters of convolution, pooling, and so on. What ResNet does, input layer, convolution, pooling, but the input would be added to the later results. The output of here would be added to the input of the next layer. That's how ResNet works. But ResNet is providing skip connection of only one step. That means this input would be added only to the next level. It can be just the next level, or it can skip this and come directly over here. So still there was some loss of information happening. Still there was some problem of gradient descent happening. So the DenseNet comes up with a solution in which it will take input and it will copy that same input to all the steps. ResNet is copying this input at only on the next level. What DenseNet does, DenseNet will take this input and copy it to all the next levels. Then it will take input from here and copy it to all next levels. Because of this concatenation happening, we will not face, or we will minimize the problem of gradient descent in case of DenseNet. So DenseNet basically works on the collective knowledge from all the previous layers, because of which it is able to give a better results. So in this survey, I have tried to cover the frameworks, the algorithms which are based on UNet and its variants, how they are solving the problem. UNet is a very powerful deep learning framework which has shown great results in remote sensing image classification. And as a part of my research, we are having a plan to develop a hybrid framework for remote sensing image classification. These are the few references. Thank you.
Judges?
Yeah, so I have one comment to make. The presentation you made is nice. And one of the advantages of the unit is that it can also perform well with less number of training samples. And that is one area in which you can also work on. So with that, thank you for the presentation. Yeah.
Yes, no question from my side. Thank you.
Thank you. We would be declaring the results of the prizes of the best presentations during the valedictory section towards the end of today's event. I would now like to call upon Ms. Grizel Fernandez to express our thanks and present the token of appreciation to the judges.
I, on behalf of the entire IEEE GRSS Bombay Chapter and the entire symposium organizing team, would like to appreciate the contribution of those who worked really hard to make this session happen. I would also like to thank all the presenters who shared their observations and findings with us. I would like to express my sincere thanks to our esteemed judges who took their time out of their busy schedule to be present with us here today. I would also like to thank our event coordinator, Dr. Ujjwala Bangale, for letting the session carry on smoothly. Thank you everyone for being a part of the session.
Thank you.
Thank you.
So after those amazing and stunning presentations, we have yet another interesting session. I would now like to invite Dr. Saifuddin Syed, Secretary IEEE GRSS Bombay Chapter, to introduce our next speaker, Dr. Surya Durba. Over to you, sir.
Graduates are joined.
Yes, sir. He has joined. Yeah. Good afternoon, sir.
Good afternoon, Durga sir.
I hope you are able to hear me.
Yes, sir. Yes.
Great.
Saifuddin sir, are you there? Okay, let me introduce to Professor Durga sir. Shall I proceed? Graduates, shall I proceed?
Yes, sir.
Yes, sir.
Yeah. So Professor Durga sir is a professor in the CSRE, Indian Institute of Technology, Bombay. Before joining IIT Bombay, he worked as an assistant research professor at the Center for Advanced Vehicular System and Geosystem Research Institute, GRI, and also held an adjunct faculty position with the Electrical and Computer Engineering Department at Mississippi State University, MSU. Earlier, he worked as a scientist at Indian Institute of Remote Sensing, that's IRS, ISRO, Government of India. He received the Bachelor's of Engineering degree from the Civil Engineering and MTech degree in the Remote Sensing from both Andhra University in India in 1994 and 1997, respectively, and PhD from the Computer Engineering from the Mississippi State University, MSU, that is in USA. In 2006 at MSU, he researched and developed image information mining tool for content-based knowledge retrieval from remote sensing imagery and retrieval of biophysical variables from the multi-angle satellite data. He has published over 80 peer-reviewed articles, served on program committee of several international conferences, including SSKI, SSTDM, and IGRS, co-chaired sessions at various conferences, and invited speaker for HPC, Geospatial Technologies, and IoT training programs in various institutes. He is a manuscript reviewer for IEEE, Elsevier, Springer, and other high-impact journals. He organized the Distributed and Embedded High Performance Computing International Symposium at IIT Bombay in 2016. And he received the Excellence in Teaching Award at IIT Bombay and the NVIDIA Innovation Award in 2016 for his work in the image information mining and high performance computing. Also, he received the State Pride Faculty and Outstanding Research Award earlier at MSU. MSU is the Mississippi State University. So, Diba sir, it's time now your session starts from here now. Thank you, sir.
Thank you, Dr. Amya Tripathi, for the introduction. Also good to see Dr. Prakash and Dr. Ujjwala, my own students, coming up in their careers, being guest of honors at Symposia makes me really feel proud of them. So I'm going to begin sharing my screen. Can I share?
Yes.
You can.
Yes, sir. You can.
Okay. So I hope you're all able to see this.
Yes, sir.
Screen. I'll just go into the play mode, slideshow. So this is a work we've done over the years along with my PhD students. Basically, our lab is interested in understanding how to do this rapid monitoring of disasters. The Geocomputational IoT Research Lab at IIT Bombay, CSRE, is where we work on developing these kinds of systems. So a lot of our work has got geospatial data as our main focus. So, share again. Stop. Slides are not moving. So, just give a minute. Let me just.
Yes, sir. Sir, can we help you? You can send us slide. We can run from here also.
Okay. It's sort of okay. Let's do it this way. What about now?
Yes, sir, we can see.
Yes, sir. Yes, sir.
I just made a PDF. So I'm going to talk about computational challenges.
It's not moving.
Lights are not moving. I think I better send it to you. Okay. Some issue with slides not moving. Even the PDF is not moving.
So you can send the PDF to us. We will share it.
Yeah. Okay, now I just share the desktop. Everything is there on the desktop.
Is
Yeah,
it now?
it's moving. Yes, it's moving now.
Moving now? Okay, good.
Yeah.
Okay. Let's do it this way.
Okay, sir.
So I'm going to talk about I think you're able to see this, right?
Yes, yes.
It's working, sir.
Okay, good. So I'm going to talk about big computational data. How do you handle it? Especially from a data that is from disasters. So we call it the big crisis data. So crisis data access and then processing and then analysis is a very huge problem. As was recently understood in the earthquake that happened in Nepal, there was data from 18 sensors had to be processed in a very small amount of time, and then they had to send whatever understanding they have and to these rapid forces that are there on the ground, NDRF and other people, and tell them what happened where. So, but then this is not an easy problem to solve because of the big data characteristics like volume, velocity, and variety. And then our goal is to work on this big data and then finally give situational awareness. Situational awareness not only to the people who are helping, but also to the people. They want to understand where they stand at this point of time. So as the time passes, every 1 hour, they want to know now what? Now where do we stand? So that is the kind of a background in which we want to develop technologies for rapid processing for various kinds of crisis data, be it earthquake or floods or any kind of even human-made disasters. So why big data? Just because everybody is working on big data, why we should work with big data? We have been working with small data for a very long time now, and successfully we are able to solve a lot of problems. Why suddenly everybody has to work on a big data? What is that we understand when we have big data? So as you can see here, small data is good, but then our insights may be different when we have small data. What is a non-linear process, we may tend to think about it as a linear form and develop models for it. But as the data becomes bigger and bigger, the actual the actual function begins to appear. What is the form of it? So these nonlinear relationships will become apparent, and then the way we tackle the problem will be different. So that is the reason why we want to work with big data. It's not that small data problems are no longer there, nor small data problems are useful to solve anymore or helpful in our daily lives. Still very much there. A lot of our work is only on small data, but then the bigger data helps us to work on bigger, larger problems where we have previously not been able to understand the complexity of the problem. So that's where we begin this one. Sorry, it got stuck. Are you able to hear me?
Yes, sir, we're able to hear, but your slides are not moving, sir.
Good. Yeah, okay.
That's fine now.
Yeah, something is having some network issue, I guess. So I'm going to talk about various challenges that are there in working with rapid monitoring. So one is automatic damaged area identification. So normally after an earthquake has happened, we would want to know how much area is damaged. We want to exactly tell this to whoever the agencies are to make an assessment. Overall assessment in terms of economic loss, for example. Flooded areas, how much area is flooded? And we want to know what are all the different classes that were flooded. I mean, in terms of vegetation or buildings or roads, what kind of infrastructure. And then search and retrieve relevant image content from multiple sensors data. So if that is the case, we have the problem of trying to capture a class or detect a class of interest. Normally what we do is we do this segmentation and then do this feature extraction. And these days we are not doing feature extraction, we learn deep learning and all that thing, which does the feature extraction by itself. But the problem is that we are unable to understand the kind of way we're understanding the higher understanding of the concepts that the user has in mind. User is thinking something else, the image is telling something else. User is thinking in terms of an agriculture field, a water body, or a flooded vegetation, a damaged building. That's what user is thinking. But the image is showing in terms of a texture or a color change or a shape change. So there are primitive features, there's a primitive features which are very at low level. User doesn't care about them. User is always interested in higher conjecture. User is understand. So there is a gap between this user understanding and then what the image is telling us. So there is an insufficient power of these low level features. So it is very difficult to do these things. So we need to look at semantics. So semantics, so I'm going to talk a little bit on how to understand this. So for example, look at a class like this, a semantic class called agriculture. So given an archive of images, you can go ahead and then search the archive and bring out a class called an agriculture. And this is a search on the content of the image rather than the metadata of the image. So this is not easy because you're trying to understand a particular low-level representation of a particular segment in an image and then relating it to the higher understanding. So if you apply that to a disaster kind of a situation where you've got an archive of images coming from various sensors quickly, this archive is getting filled with various sensors about this flood that is unfolding. You don't want to sit there and then try to do an interpretation saying, oh, this is agriculture area that's flooded, this is the urban area flooded and all. It's going to take a lot of time, a lot of analysts has to sit, a lot of effort. What if you just feed it to a system and system automatically searches? So you can just say, show me all flooded flashlands in urban area with floods. So it has to search automatically and then give me the results. This is a rapid way of retrieving what we need. But then computationally, this is very difficult because there are so many sub-processes that are happening within this system. So that is one of the computational challenge is to be able to extract these low-level features itself is a big problem from an archive that is, let's say, 10 GB, 20 GB kind of a thing. And then make all these images that are there in the archive ready for querying. So a lot of things need to be done. Each and every process is computation intensive. So that is a challenge. And then finally link it to the semantic class, the user's understanding. So challenge 2 is when we are trying to work with data that is small. But challenge 1 is made difficult because of positive labeled samples. So if I just want to detect flooded areas or damaged buildings, not possible, because always you don't have the labeled samples. As you all must have already realized this when you're doing deep learning. Deep learning is a very hungry for a lot of training data. You can't work with small data sets. But then during disasters or those kinds of phenomena where it is not accessible, it is dangerous to go there, or you may not have ways to fetch this training data, you will have to work with small training samples. But then we still need to have good predictive classification models. So the challenge 2 is, how do we transfer what we understand earlier to what we know with the limited amount of samples that we had. So if you look at on the left side, you see the separate models like agriculture, flooded vegetation, marshlands. This is normal machine learning. This is what normal deep learning or anything traditional machine learning that we do is build separate models, or a combination of this, a multi-class or a binary classification, doesn't matter. But we're building separate models for each and then running it on unseen data sets. But on the other side, if you see, if you understand forest and agriculture and swamps, if you understand and take the knowledge from it, can we derive a new class called flooded vegetation? If you understand swamps, marshlands, and lakes, there's some commonality between these classes. And then can I derive a new class called waterlogged areas or earthquake hit urban areas, buildings, bridges, streets, and then take the knowledge from it. And maybe tomorrow there are urban areas destroyed, maybe by human conflicts. Yeah, someone bombed that area. Maybe it looks like exactly like it looks more or less like an earthquake hit area, right? But already we understand how an earthquake hit urban areas look like. We understand buildings, we understand bridges, streets. Can we take that knowledge and transfer it? And then if you look at the harmful algal blooms, chlorophyll, chemical spills, if you extract that knowledge, maybe a new class called oil spills could be learned from it. So if you are trying to look at a new class called flooded agriculture, we don't know which classes actually will help in understanding, the prior understanding of which classes will help us in transferring it to a new class called flooded agriculture. Some may help, some may actually make it worse. They may be negative. They act as a negative samples. So we cannot just randomly take whatever we want. So prior understanding is important. So we need to understand the domain, understand how they are linked together, and then see if we can transfer this knowledge. What's the advantage? Advantage is that even if we have a very few samples of an earthquake hit area, this is a Nepal pre-earthquake imagery, and you can see post-earthquake imagery. What's going to happen is we can adapt what we know before to what happened right now from a source domain to a target domain. So if we don't do that and just use whatever small samples we have, for example, 12 samples or something here, we will not be able to achieve good accuracies. But if we are able to do that, I'm not going to do what are the methods to do this and all, but if you are able to do this transfer learning, even with very small samples, as small as 2 samples, still you get about 60% accuracy. So this is an example for floods. Srinagar pre-flood imagery and post-flood imagery. You'll be able to see that Without any adaptation, if you do the same thing either with SVMs or deep learning or any of these things, the results will be almost similar. But if you have done transfer learning, if you did domain adaptation from one domain to the other, pre to post floods, understanding which classes help in increasing the classification accuracy. Not all of them may work. Some classes may work. So here, for example, buildings and river samples are used. You'd be able to get a higher accuracy. So the next thing we want to understand is we need to capture contextual information from a disaster standpoint. We want to retrieve flooded urban areas in a geographical area X from imagery from sensor Y. So what is the current status of the information? What are the evacuation areas? What did people do in the past? How are people responding? All these things are very important and need to be given timely. So challenge 2 may only enable to identify affected areas like we have seen in the previous slide, but it doesn't give any other information. Fine, there is a destroyed building here, there is a flooded area there, but someone will ask, there is a flooded building here around this. Is there a road on the right side that is still accessible that we can move people? Or this hospital area is flooded, can we move this patient so that, is there a road on the north side that is only partially flooded, or is it totally open right now that I can move people? So the spatial context is not known. Maybe what we have done in the last 2 challenges is enough to tell us how much the area of the flood, area of the disaster is there, but it is not actually helpful for the people. So what do we need to understand? What is the context in which neighborhood? Contextual knowledge is, therefore, understand not only the affected areas, but all the spatial context of the neighborhood areas. It's important. Start again. Just let's wait for 2 minutes. Let's see. Okay. So understanding spatial context of disaster affected areas. So suppose I want to know, retrieve all images from an archive of satellite X, which has buildings surrounded by the flooded area, and provide me also the details nearby hospitals. So this is the kind of scenario I'm looking at. Can we able to do that? So we have got some spatial context like surrounded by, nearby, those kinds of things. So currently the systems that are there are unable to do this. They cannot give us a spatial context, especially retrieving them from an image itself. Maybe you can do a GIS database can help you do these queries, but then that's a long route to take because we don't have that much time to do this. Any information you give after a certain amount of time during emergency, it's wasted information. So we have to do the spatial relationships and do all these things. So there is a architecture that we developed. I'm not going to go into that, but a new way of storing data so that it is amenable to developing this kind of query, a triple stores. And then we developed a big knowledge graph called a spatial semantic graph. Based upon it, you can ask several kinds of queries and real time it can retrieve it. So I'm going to skip this in the interest of time. So what we did was we did both topological relationships, and then, for example, how 2 objects are related with each other, right? Tangential proper part, non-tangential proper part, disconnected, externally disconnected, all kinds of relationships, plus the directional relationships. We want to also say that there is a road on the northeast side that is still accessible, or this building is surrounded by this thing, but there is another infrastructure on the west side that is not. So to be able to quantify that, these different directional relationships were taken, and then whether it's a strong east, weak east, all of them were quantified together, and then developed this system. So retrieve all images from a repository, from a satellite sensor called ALI, flooded, stagnated in some areas, or retrieve all the images captured by ALI which contains built-up regions. So these are all just simple queries, which I showed in very early on in the challenge 1. Here there are no special queries. So let's look at what they are at the very basic level. And if you search for like this, all that are flooded, it will show that areas that are flooded, not a problem. But then we want to add a little bit more complexity to it. Now we are talking about something that is adjacent to a river. Show all areas, built up areas, but then they are adjacent to a river. So what we are saying basically is externally connected. And then we are also talking about this, and also have stagnated floodwater, built up all kinds of special relationships we're integrating into the querying. So something in the real world, this is what we are looking for, and then what these images are going to show when we search based upon this. So like this, there are several queries we have developed. And then this is a query related to the topological and directional. So you're talking about built up adjacent to river, and then something is west of the stagnated flood water. So both in terms of topology as well as direction. So this is a sketch that shows what we are looking at. So in the interface that we developed, user can also draw a sketch saying, okay, this is the kind of configuration of these special objects. Search the archive and bring me those objects, those images. So it's going to do that, right? And then this is a query related to the directional only, industrial areas that are like this. And then we can search images. So a very recent work that taken this one a step further is how do we caption this caption these images from a disaster standpoint. So earlier we said, okay, you can understand the context, the special thing, but it would be very nice to just feed an image and you get a caption saying, okay, there is a road, there are accessible buildings along the road, there are flooded buildings to the west in each direction of the road, there's a traffic on the road, and there are stranded vehicles to the west direction of the road, and there is a flooded vegetation to the west and east direction of the road. So we are actually doing an image captioning of a flooded scene or a disaster scene automatically, taking into consideration both the content-based retrieval and the spatial context, topological, directional, and then added on top of it the grounded natural scene description. We call this the SEM-RSSU framework. So this is another example of a remote sensing scene of a disaster flooded area, and then the grounded mappings. So there are flooded buildings spread across the scene, stranded vehicles, and all this. So I'm not going to go into how we did this, but there's a paper that's available. You can just search, I can point you to that. So challenge 4, even if we address this challenge 1, 2, 3, that is fine. But if you don't give it timely, this information, it is useless. Right? There is a expiry date or time for each of this information. After that, it's useless. So we need to process this all very rapidly. So you need to do big data analytics. You can use cluster architectures. You can use GPUs. So where are the issues to take up this one? How do you speed up this process? So we have identified areas where this takes a lot of time. So there is an offline module, there are online modules in these systems that we're developing. For example, feature extraction takes a lot of time. So for example, a mean shift segmentation algorithm has a complexity involved. There is a texture feature calculation, there's a complexity involved. We want to understand each and every process and then see how it is working on a CPU, or how much time it takes on a CPU versus how much time it does on a GPU. So here we look at a segmentation algorithm, and this is a texture feature extraction, and then what is the time it takes as the number of regions, the segmented regions in the image is increasing. So we find that it takes a lot of time. We cannot afford to have systems that takes that much time. We need to hasten this up, make it very quick. So we take the help of a GPU. So I think by now a lot of you are already aware of GPUs, graphic processing units, and then how they work, how a part of your computation is delegated onto a GPU, and how it's able to send you back the information. So because of the high number of processors, so we got a system at IIT Bombay where we have got K40s and then about 2,800 processors we have per card. Like that, we bought about 7 cards. And then we are able to do a lot of processing. So based upon it, we did a lot of experiments on this. And then we are able to find out how much time it takes on a GPU versus a normal CPU, where as the image size is increasing, what is the speed up? And we have found significant speed ups happening when you are doing a GPU. As the image size is increasing, CPU no longer is able to catch up with it. So some of the experiments on mean shift segmentation algorithm on various kinds of GPUs, very primitive Tesla C2075 or GTS 450, a lot of on your laptops, you have this kind of GPUs. And then we use a very high performing parallel computation Geo HPC cluster that we have. You can see that from about 3 hours, we reduce it to 24 seconds. So that's a lot of achievement. And then we take all these things and then look at the different kinds of disaster, oil spill disasters, and how do you speed up this process when oil spill disaster. And then we developed a framework how to detect oil spills on large multispectral images using in a GPU environment. So we can see that there's a lot of performance improvements on a GPU as the image size has increased. We have got about 220x faster as compared to the CPU version for a particular operation, a morphological operation. Like that, each operation has to be tested and then the overall performance to be tested before we make a decision on to move what on a GPU. So with that, I end my talk. I'll be glad to take questions. So I hope I'm able to finish it in 45 minutes. Or...
Yes, sir. Thank you very much, sir.
Sure.
A lot of questions could be there in the particularly for the high performance computing concern. So one question that particularly, sir, in fact, the many student and the people from I'm talking about across Mumbai, they are facing is that because of lack of resources over there, so they are unable to perform certain things, even though whether it's a geospatial or even in ordinary sense also to use to go for a high performance computing. So what you suggest in such case, that one, how can we proceed with this?
Yeah. See, what I would suggest is start baby steps. One is to use very small GPU cards that are available on your own laptops. Don't worry about big one. When we started, we started with the C2705, very small GPU system. We didn't have anything big a few years back. And then what we did was trying to understand how do you actually do this CUDA programming? How do you take these images and then do all this pre-processing and get it into the GPU framework? That is most important to understand. It is not important whether you have now proved that this algorithm works fantastic in a GPU over a CPU. You don't need to prove anything. First thing is to be able to get into that CUDA framework, because that learning curve is very high, and I have seen many students drop off in between because of not being able to cope up with the way of programming the GPUs using CUDA. So that is where you need to spend maximum amount of time. And then try to understand, take a simple image, do a filtering operation, do a neighborhood operations, see how it works. That will be your gentle introduction into this. GPU programming. You don't need to buy anything new. The small cards are there. That is enough for you to get started. Okay.
Okay. So.
Yes, someone was.
Yeah, there's a question in the chat.
Yeah, you can use. Yeah, I mean, yeah, you can use the GPU provided by Google Colab. Only problem is that you're not writing any CUDA code a lot of times. If you are learning this deep learning model and delegating a GPU to do it, it is doing all that behind the scenes. And then you claim that you may claim that I have used a GPU, but you don't know anything about a GPU. Don't do that way. Okay, that is not a good way to work with a GPU. That is only when you are running a deep learning model, you need more computational power. So you delegate a GPU to it, and then it will do for you. But you don't know how the actual chunks of information from your deep learning model is delegated onto the GPU, how the processors are doing. The low-level programming, that understanding you will never gain. Kernel development, you may not know. Okay, so that is not the which you are working with. Google Colab is not the GPU programming you want to work with. Start with the GPU on your own laptops, right? Or get a card. It's not so costly, 3,000-4,000 or 6,000 maybe. You can get a small card, get a GPU. You may not see very fantastic things. If you want to do, even don't want to do that, get the Jetson Nano. It's a embedded device. Costs around 10,000, 11,000 rupees. You can do all GPU programming. You can do all CUDA programming. You can develop embedded devices. We are doing a lot of work in that area also. That is enough for you. A lot of innovation you can bring in by doing this. You can develop high performance computing based embedded devices. That's another way to work with. Okay, but certainly if you're a computer science student or interested in high performance computing, you should, this is the time to learn and be an expert in this area. You have to have this skill. All right.
Thank you, sir, for that detailed session on the computational challenges in disaster monitoring. I would now like to call upon Ms. Mansi.
I have one more question.
Okay. Yeah. Yes.
So, sir, when we talk about all this kind of the geospatial data, or even if anything on geospatial computing is concerned, so do you think that if you look for a parallel programming or parallel algorithm to be used, then it will be more beneficial than what now we have been using sequential algorithm?
So that's a good question, but then it is not always the case. Not all algorithms are naturally fit to run on a parallel computer. Right? And then there are also trade-offs when you're performing certain kind of operations. For example, you're doing NDVI, a ratio-based algorithm, versus an approach where you're applying a filter, you're doing convolution or those kinds of things. There is not much gain you're going to have when you're doing a ratio-based approach on a parallel computer. So things that are inherently sequential process may not, you're only forcing it to be run it on a parallel computer, gains are not much. A truly parallel kind of a problem. For example, you have got an image, you have got a neighborhood of a 9x9 window, you have to move around. It's a parallel processing. So first thing is analyze your algorithm. See which chunks of that is amenable for parallel processing. Where are your loops? Can you delegate them? So that is important. So analysis of the algorithm is important. All serial algorithms or the algorithms that you have right now. See which portions can be parallelized. Not everything can be parallelized. And sometimes some of them are, it is better to run in the serial form than on the parallel computer.
Okay, sir. Sure. So many times, sir, we have been talking about this, the MapReduce and particularly big data point of view is we talk about that, right? Of course, the data. If you think about that one, that the particularly for remote sensing data, sir, obviously the data is in that map or Terra or a little more on that also, right? So then when we talk about this, nowadays the business people are talking about the big data, those kind of proprietary software and all things are there. So this has been not designed particularly for, sometimes I feel, of course, and many of them I'm using also, these particularly for the geospatial technologies are concerned. See, those things we talk about data in this map, we talk about a commercial purpose. Those are again, what we have been, talking about commercial use of business purpose over there. But when comes a research and remote sensing and talking about and remote sensing images or any kind of hyperspectral image, something we're talking about. So how we will go with this big data technology or whatever we talk about nowadays?
Right. See, first thing is I wouldn't use any commercial software for research. The very first important thing is develop everything from your own scratch up. That's the only way to learn. There is no other way. That's the hard way to learn, is to start programming. At least use R, those kinds of environments, use Python. So many libraries are available these days. It is not necessary to use any of these commercial softwares to do your work. So especially for students, I would encourage them to do something from scratch. When I started, I used to write C programs with for filtering on a DOS machine. That's how we started. We didn't have any of these things. No RAS image, nor NV, nothing. So we know how to do matrix manipulation. What is a matrix? How do you read it? How do you take an image? How do you apply filters? How do you do atmosphere corrections? All algorithms implemented in C. That is the way to learn these things. Yeah.
But unfortunately, sir, then this Python comes in the picture, then people are hesitant to do the C or C++ or Java. So they will switch on everything to Python because of so many libraries available over there.
Yeah, that is what is happening. So the fundamentals are getting eroded. The foundation is what is not so strong these days. But then it is our job to make sure it happens. So if the mentor insists that no, you have to do it this way, they'll have to do it.
Okay. Thank you, sir.
Sure, most welcome.
Thanks a lot, sir. There was Ujjwala here. So
Hi.
yeah, so by now I think everyone must have understood that what level of guidance we must have received during each stage of our PhD. So actually it made a really great difference in our professional life as well, sir. Thanks a lot. So
most welcome. Very happy.
Always keep on inspiring us, starting from the work ethics to can say discipline, integrity, everything he has taught us. Thanks a lot, sir.
Most welcome. Wish you all the very best. Yeah.
Thanks.
But two Ujjwala here, not only one.
Yes.
Your two students were there.
Yes. So we three are in fact. So
yeah, Prakash also there. Yeah.
So Prakash is also there. So both Ujjwala and
great.
And other side, this Sangeeta Chaudhary madam. Then
hello, sir. Good evening, sir. Gurba sir.
Good evening, all torch bearers of the future.
Then one more
spreading around a lot of knowledge. I'm really very proud of them.
One more, sir. Sangeeta Misra is there.
Okay.
Sangeeta Misra, madam, are you there?
Yes, sir. Good evening, sir.
Good evening.
Good evening.
So all these are from CSRE. We are here in this same chapter. We are all these things. Yeah.
Yeah. You're all the ones who are making CSRE so proud.
Thank you, sir.
Thanks.
Thank you so much, sir.
Rizal, continue, please.
Sure. All right, then I'll catch up. Bye-bye.
Yes.
Just a moment, no, sir.
Sure.
Yeah. Wait for me. Would be sharing the moment, right?
Yes, that Rizal will take care.
Yeah. I now would call upon Ms. Mansi Anakpurkar to deliver the word of thanks.
So on behalf of the IEEE GRSS Bombay Chapter and the entire symposium organizing team, I would like to thank Dr. Surya Durba for this wonderful session. I personally found it very helpful with the way we proceeded with the presentation. I was excited that what was the next challenge coming up in the next slide and how the system is getting better with every challenge. Also, I'm sure all of us would like to know more about the implementation of the system and would really research about your papers. So thank you so much, sir, for this informative session. And thank you everyone else for attending the session.
Most welcome. All the very best.
Thank you.
Coming up, we have a panel discussion on geospatial technology applications, the present and the future. We are privileged to have a wonderful panelist with diverse and a very impressive knowledge base. I would now like to invite Dr. Sangeeta Chaudhary, Vice Chair, IEEE GRSS Bombay Chapter, to introduce our panelists for the session.
If
Over to
people
you,
have
ma'am.
joined, let's see also that.
Yeah,
Grace,
we need to check.
yeah, Grajo, have you checked people have joined?
I'll just check again.
Because we have informed that we are running late, sir. We have informed them to join a little bit late. That's what we talk about that. We have to wait for a few minutes. Let me communicate them to join. Okay. Let me communicate them to join and we'll start. I think I'm not finding them here. We'll wait for a few minutes and a few minutes more, maybe 5 minutes more, so that we'll start.
Yeah. Amia sir, Sandhya Kiran ma'am had joined.
Join, yeah.
Yes.
Hello, ma'am.
Good evening, madam. Good evening, madam.
Good evening.
Yes, we met, I think, 2 years back, probably. Yes, I'm
yes.
All right, all right.
Good evening, ma'am.
So, Sangeeta, madam, I'm trying to communicate. Yes,
yeah, others I could not see in the list.
Yeah, I'll ask them to join.
Good evening. I'm Dr. Dheeraj Singh. I've joined.
Yes, sir. Good evening, sir.
Yeah.
Good evening. Yes, Dheeraj. Yes, I. So, Sangeeta, ma'am, I'm just communicating and contacting others to.
Yes.
Yeah. Okay, ma'am.
Yeah. Good evening, Dheeraj sir, and welcome to the panel.
Rejo, Dr. Pradeep join. PK Nandu sir join.
Sir Avik sir is here, Dheeraj sir is here, Sandhya ma'am is here. Dr. Pradeep is left to join.
And then Dr. Naresh.
I think he's also there's one Mahesh in the participant list.
Dr. Naresh Kumar.
Yes, he's there.
There, I have joined.
Yes. Good evening, Dr. Naresh sir.
Good evening.
Good evening, sir. And Dr. Pradipta Nanda is there. Sandhya madam there. Naresh Kumar. Avik sir joined. Rejo.
Yes, sir, he's there in the participant list. Dr. Avik.
I just talked to him.
So Dr. Pratipta is here.
Okay. Again, I'll ask to start to join quickly. Good evening, Dr. PK Nanda sir.
Yeah, good evening, Professor Zibadi. Good evening. Yes, good evening, everybody.
I'll call Dr. Avik sir, just a minute. Rejo, yeah.
Yes.
Rejo, yeah. I think Sari is joining, so you can.
Yes, Avik sir, yes, sir.
Yes. Sorry for the delay.
Yes, sir. Good evening, sir.
Good evening.
Good evening, Dr. Bhattacharya, Professor Bhattacharya. Yeah.
Good evening, sir. How are you?
Yeah, fine. Cyclone is passing and there is rain here.
It was raining here some time back, but now it's again sunny.
Yeah.
So we'll start.
Yes, yes.
Yes, we can start.
Am I audible?
Yeah.
Keep it loud, you speak, Rizal.
Yeah, okay.
Yeah.
So we have a panel discussion right now on geospatial technology applications, the present and the future. We are privileged to have a wonderful panelist with a diverse and a very impressive knowledge base. I would now like to invite Dr. Sangeeta Chaudhary, Vice Chair, IEEE GRSS Bombay Chapter, to introduce our panelists for the session. Over to you, ma'am.
Yeah, thank you so much. Good evening to one and all. To the panel discussion on geospatial technology applications, present and future. So I welcome all the panelists on the panel discussion. To introduce with, to start with Dr. Avik Bhattacharya. He is a founding chairperson of IEEE GRSS Bombay Chapter. Then we have Dr. Pradipta Nanda. So Dr. Pradipta Kumar Nanda graduated from VSS University of Technology in Electrical Engineering in 1984 and obtained master's degree from NIT Rourkela in 1989 and obtained his PhD from IIT Bombay in 1996 in the area of computer vision. He has served more than 21 years at NIT Rourkela, and during his career at NIT, he has contributed to the growth of the department and institute as well. He was the principal investigator at the Center of Excellence on Industrial Electronics and Robotics. Beside, he has developed an image and video processing research lab, real-time and embedded system lab, communication and signal processing lab at NIT. Currently, he is a Pro-Vice Chancellor of Shiksha Anusandhan University, Bhubaneswar, Odisha, and formerly he was the Dean R&D of Shiksha Anusandhan University. He is also the member of Board of Management of Shiksha Anusandhan University, Bhubaneswar. He has supervised many PhD and MTech students in his career. He has completed several AICT and MHRD sponsored projects and running collaborative project with Center for Soft Computing, ISI Kolkata. He has 90 plus papers on his name in various international journals and invited talks in the conferences, workshop, summer and winter schools, and have served as program chair member at various conferences. He is a recipient of Bharat Jyoti Award from Indian International Friendship Society, and he has also received Odisha Technocrat Award from Evergreen Forum of Odisha. He is a reviewer of many standard reputed journals. He is a fellow of IEEE, IET, IET, and life member of IST. His research interests include image processing and analysis, biomedical image analysis, video tracking, image, computer vision, soft computing, and their application. I welcome you, sir, on the panel. Moving ahead, we have Dr. G. Sandhya Kiran. So she is currently head and professor at Department of Botany, the Maharaja Sayajirao University of Baroda. She has completed PhD in botany and she has a postdoctorate from ISU USA. She has taken postdoctoral training in remote sensing and GIS at Department of Geography, Geology and Anthropology, Indiana State University, USA in 95 and 96. She has many awards on her name. She's awarded Haridwar Gold Medal for standing first at her MSc at Baroda University. She awarded Boy Scouts Fellowship by DST for carrying out research in the field of application of remote sensing and environment studies. She also awarded with UGC Research Award from UGC this thing for carrying out the research in the field of wasteland characterization using remote sensing. And also in 2010, she awarded with ICQE SMS Award, Excellence Award for her best paper, that is Urban Environment Quality Assessment using satellite data and geographical information system. And she also bagged one award, that is Gargi Award at Baroda in 2016. She has completed many projects and ongoing projects she is working on. She has published more than 50 research papers in reputed conferences and journals and 3 book chapters. Her area of interest is plant ecology, plant physiology, remote sensing and GIS, and biodiversity, agriculture, sustainable developments, etc. I welcome you, ma'am, on the panel. Moving ahead, we have Dr. Naresh Kumar. So Dr. Naresh Kumar received the master degree in physics from Usmania University, Hyderabad, and masters in computer science and engineering from BITS, Mesra. He received PhD degree in computer science and engineering from Usmania University, Hyderabad. He has been with National Remote Sensing Center, Hyderabad from last 22 years. He has worked on end-to-end technologies pertaining to remote sensing, right from data acquisition till dissemination. His work on message-driven services for autonomous workflows resulted in a US patent. He was one of the core designer of Bhuvan EO portal of ISRO. He was deputed to various international ground stations to facilitate the acquisition and processing of Indian remote sensing satellite data. Also, he had developed many innovative products and services at NRSC, and at present he is with the program planning and evaluation group spearheading the innovation and knowledge exchange program. He has authored more than 40 publications in the area of computational intelligence, biomedical health informatics, climate science, SAR, and hyperspectral hyperspectral data analysis. He is a fellow IET, elected in 2013. He is also a senior member IEEE ACM member, and he is having a professional membership of many more societies. He received Team Excellence Award for Development and Realization of Bhuvan Indian EO Visualization from ISRO in 2009, and Team Achievement Award for Bhuvan Web Development from Astronomical Society of India in 2011. He also received an ISRO Team Excellence Award for realization of integrated multi-mission ground segment for Earth observation satellite. So his present research include but not limited to target detection, optimization, and physics-aware AI. I welcome you, sir, on the panel. And finally, we have Dr. Dheeraj Kumar Singh with us. Dr. Dheeraj Singh is currently working as Scientist F at Electronics and Radar Development Establishment, Bangalore. It is one of the premier laboratory of DRDO. He had joined EMI-EMC group at LRD in 2003 as Scientist B after completing his MTech at IIT BHU, Varanasi. He was instrumental in designing an analysis of the first indigenously built time domain antennas and sensors for simulators and nuclear electromagnetic pulse, meeting all the requirements of RS-105 specification and testing as per the standard. He received Young EMC Engineers Award in 2011 from EMC Engineers Society of India. He pursued his PhD from IIT Kharagpur. He is working in the area of time domain electromagnetic, computational electromagnetic, antenna designing for shortwave radars, SAR development for EMI-EMC evaluation. He has also designed and developed many UWB antennas for short-range radar through wall imaging and ground penetration radar application. He's now promoted to Scientist F and serving as a project director at Satellite Bone Synthetic Aperture Radar System for search and reconnaissance operation. And his area of interest is antenna design for space application, synthetic aperture radar system engineering. So I welcome you, sir, on the panel. So we have people from diverse background and with very good work in the remote sensing field. So I welcome you all on the panel. Moving ahead, Grejo, shall I share that PPT?
I'm sharing.
Yeah. Yeah. So moving ahead, I'll be starting with the first point for the discussion, that how do you see the geospatial technology adaptation in current application areas? So I first request Dr. Pradipta to give his opinion on this, and then we'll move to the next panelist.
Good evening, everybody. Yeah, it's my pleasure to be here with all the kind of the panelists as well as also the participant delegates. It's my also pleasure to share my thoughts with the kind of all the audience, and also the other panelists will join. In fact, the current scenario, we are moving towards this kind of adaptation, geospatial technology, in the sense that particularly the climate change has affected the globe, and as a result, we are concerned with the kind of the what about the ground related, like the agriculture, and also the other aspects, the urban area, change in urban area, and the deforestation. So these are some of the burning issues, and which is happening, and currently the world is focusing on this. this kind of as kind of the satellite data on kind of this kind of deforestation or kind of the agriculture or in a sense the atmosphere. We have been people have been working a lot, and how to handle the geospatial data, particularly the spatial resolution, the prediction, the kind of the analysis is one of the key area where we have to actually the current research is focusing. And it's not as straightforward to use a image analysis because it has multispectral, I think multi-band we have. In fact, single band is difficult to do, and people are going for multi-band analysis or multispectral analysis. And particularly the spatial features, we have to handle spatial features, and the resolution is one of the key issue in handling this. In a sense, the information you have to extract from the geospatial, the spatial information, so from the earth have to be, the resolution has to be accurate, the precision and the accuracy, you must focus on that. So resolution is a big issue. And as far as the geospatial technology is concerned, that we have to adopt the current science, current recent development of handling the high volume of data and different resolutions and also different spectral components. So how do we combine them to extract information? So different kind of feature analysis is taken care of. Machine learning is used, particularly the deep learning has been used extensively in recent past to solve some of the issues because the data is used and the spatial information is not in one band, is kind of spread across multiple bands. How do we extract and fuse the information from different bands is a question mark. So therefore, the people have started adopting the usual kind of the technology, and they modified it. A lot of research has been, I think, devoted in these directions, and this definitely will help us help our society in general, and also in fact, the particularly the GRSS society in particular, the group who is acting or actively involved in this kind of research, they need diverse kind of the field. So there should be a synergy of effort among the scientists from the kind of the technology, radar technology, kind of the microwave technology, and also the image analysis technology, vision technology, I think machine learning technology. So I think pattern recognition people, they should converge, all should converge to solve an issue because it is a multi-dimensional and multidisciplinary approach. So with this, I think I stop my whatever the thoughts here, sharing the thoughts, and I think other panelists will share them. Thank you.
Yeah, thank you, sir. Now I would like to take the opinion from Dr. Sandhya Kiran ma'am.
Thank you, Sangeeta. At the outset, I would first of all thank the GRSS, IEEE GRSS, both the chapters, Bombay as well as Calcutta, for considering me in this particular session for panel discussion, because I'm a little bit outfit for this, but still I've been working in this field since many years, and I look upon this geospatial technology as from application angle. For example, now since this question is there, like geospatial technology in adaptation, since yesterday's deliberations, we could see that we are trying to extract maximum information from the pixel, and we are trying to generate models for different particular areas. But how these particular equations or algorithms we generate, they are fitting to those areas, that is understood only if we validate. So no doubt this geospatial technology has brought out a real revolution in the field of understanding the natural resources. But at the same time, I feel that more stress has to be given on the validation of whatever algorithms we generate, how much different validation points we collect from the field, because field work is also equally important when we go for geospatial analysis. No doubt if we use different algorithms, we generate different models, but as I think first speaker, Dr. Pradeep has told us that we have to become more data specific. And if this data is directly from the ground, I think the things will work more precisely. So no, I would definitely say that the geospatial technology has brought out a revolution, but still if it has to give more precise results, we need to have more validation of the models or equations or algorithms we generate. That's what I personally feel. And Sangeeta, I just wanted to thank you and make a small correction that I am right now ex-head. Thank you.
Okay, yeah. Sorry for that. Yeah, thank you, ma'am. Now I would like to hear the opinions from Dr. Dheeraj Kumar Singh, sir.
Yeah, first of all, good evening, everyone. And I would like to thank the organizer to giving me an opportunity to share my views. Though the topic, what you call is geospatial intelligence, my area of work is on board. So we struggle to make the system so that it goes flies, and then there is another team which uses the data. Now, but then I can visualize this area as emerging is not only that civil work. I'll just try to add dimension from the other angle. Most of the when we talk about the satellite system or satellite based system, we think mostly about the civilian space applications. But then if you see the contemporary defense or the military application is growing enormous in a leaps and bounds, but that doesn't come into the news. And that's why people are not aware. We don't get publications also about some of the development happening in the military area. So most of the countries have their very vibrant military space programs. So in that context, what I'll say there, if I can divide this into two segments, one is onboard systems, onboard sensors or onboard payload, including from synthetic aperture radar or hyperspectral imaging or electro-optics. Then comes to the ground-based system. Now, most of my panelists will agree that making a sensor and putting it into the right orbit, it takes a good amount of time, and there is not a single lab. Multiple labs are associated with that, and that may not be a cup of tea for everybody doing research in the universities or every students everywhere. But then the best part now, the emergence is that you have wealth of data available, and how we can do the analysis and get the right information at the right time. Or how we can do the data fusion, how we can do the use the computational power available today, which was not available earlier. So those kind of, and then disseminate the information to the decision maker at the earliest. In the military requirement, the most important is nobody will ask you a suitable time frame. It is you have to give the information at the earliest. And you have seen the situation of Doklam and so many things happened just last year. Those kind of situation has just pushed us towards having not only one sensor, a cluster of sensors, and then you have cluster of sensors, and then cluster of then you want a faster revisit time. Means you don't want to wait for data of same place after 8 days, 9 days, like that. For that, you have to augment at the onboard. You put more satellites so that the revisit time is reduced. And then onboard, there are challenges in onboard. You have to decrease the revisit time. This is the order of time, and then you have to give the better resolutions, better resolution, better swath, so that you cover more area, cover the world at the fastest pace possible. And there, if the panelists may be very well aware, at the same time, it is a contradictory requirement. Both, then there are other challenges for the onboard synthetic aperture radar designer, how to meet both of them. But then when we go for a resolution, then the amount of data is huge. If just take an example of a 2-meter resolution for a synthetic aperture radar operating for 10 minutes, you will get a 1 terabyte of data available on board, and that has to be sent back, and then you decrypt, and then you form the image. So that is a wealth of means data is huge, and information can be derived in a multiple ways to present it to a very layman kind of user also. Because if you see SAR images, synthetic aperture images are not like an optical image. To make out something, it needs a lot of skill, and then definitely use of AI and ML will be another area. It can be used in a meaningful way, and so that we can disseminate the information in the best possible way, so the decision can be made and the action can be taken based on that decision. So here the reliability of the data, as well as the authenticity of your discrimination algorithm, is very, very important. And the timing, how much time you take to give the information out to the end user to make a decision, this becomes a very, very important. Whatever be the time of the day or night or cloudy or rainy, you have to work. That's why we need all kind of sensor, including synthetic aperture radar or optical or hyperspectral imaging. So this is my view on this.
Yeah, thank you, sir. I would like to invite Dr. Naresh Kumar, sir, for presenting his thoughts on this topic.
Yeah, let me congratulate the GRSS Bombay and Kolkata chapter. It's a really very coordinated effort on bringing out such a symposium on geospatial intelligence. And let me try to understand the question. So one end we are talking about geospatial technology, and the other end we are talking about the application arenas. What I understand from the geospatial technology is basically geolocation and the spatial extent, and how this the information that we associate with this particular location and extent, that would result in how best we can use it in different arenas. So that is the very basic level. What we have done is try to put in all the remote sensing imagery and try to interpret that imagery and then derive some thematic information out of those imagery, and then try to populate it into a geospatial portals. Okay, so initially we started with the visualization part, and then people have been using it for navigation purposes, and the very popular one is our Google Maps and such kind of technologies. We are well versed, and people are very hands-on. They are able to use it. Whereas coming into the complex, let us say the application areas, I would say I will divide these applications into three aspects. Let us say one is the societal applications, which may involve the agriculture, the different aspects of agriculture, like let us say the crops, the yield. It may be related to the droughts. And then we have the other applications like your forestry, biomass, and those applications. Then we have other societal applications like disasters and hydrology related aspects. So these are all some of these societal applications. Then the adaptation right now, the geospatial technology is up to the visualization level, is well adapted, I would say. Then when come to the defense and the other, I would like to talk about the blue economy. I think the adaptation is not that much. Basically, maybe due to as no confidentiality related thing, because high resolution imagery and all that we at earlier or now at present, I think they are not available. But the recent policies have been put forth. Maybe these high resolution imagery, to what extent we can put, and how it will drive the defense applications. Basically, their applications may related to finding a target, such as a tanker or even our boundaries. How do we try to say that somebody has crossed the boundary, or they are all virtual. See, all these boundaries are virtual. Even if you look at a parcel of land, if you try to see whether which parcel belongs to which farmer, there is still a big debate. So anyhow, the geospatial technology has been slowly being adopted, and then it has seen in the recent several government initiatives, the geospatial technology has come forth and was successful, like our Manrega and other programs. Geospatial technology is widely used. and in Swachh Bharat and all those government initiatives, geospatial technologies are used, and Bhuvan is a portal where we are showcasing all this data and the different resolutions, different scales, and all those things are available. Whereas the other arena is the blue economy, which I will just brief a little, which may involve the fisheries, which may involve the, let us say, the pollution related in the oceans, and identification of shipping vessels and such sort of thing. It is slowly being adopted, but I don't see a wide, there is some gap somewhere between potential fishing zones. We are giving some advisories, but at the geospatial scales, the availability of that and other kind of vessel detection and other things. Anyhow, this SAR and hyperspectral and other applications are anyhow we are taking up in these arenas. But whereas geospatial technology, I would purely say, is at the stage of visualization. And recently, I have seen some of the technologies like deep learning and AI being adopted for crop yield estimation and other applications in the agriculture arenas. And I think there is a huge potential. There's a huge potential for adoption of geospatial technologies in these arenas. I think over to you.
Yeah, thank you, sir. Now I would like to call upon Dr. Avik Bhattacharya, sir, to summarize this topic.
Thank you very much.
Avik, sir.
Yes, am I audible?
Yes, sir.
Okay, thank you very much. Yeah, it's thank you very much, first of all, for organizing this panel discussion, and on behalf of the GRSS Bombay Chapter and the founding chairperson, I really welcome all the eminent panelists over here. It has been, I mean, I'm just hearing, it's coming from a very different, the experts coming from different fields. I mean, some of us are coming from the academic background, and we have the eminent researchers coming from the two big labs, which we have, the DRDO and ISRO. And it's very nice to look into their perspective, how we utilize geospatial technology from different aspects. And just to summarize it, or what is a little bit about my thought, is that as we know today, geospatial technology, as has been mentioned by all eminent panelists, is of course a significant scientific find. Which is moving the possibility of humankind to a different level. But when we see that this technology is not new as such, it was there, but just that we are looking at it from a different perspective. And we have heard from Dr. Singh that we have sensor, and now they're acquiring data at very high rate, amount of data. So what it's becoming is that this use of geospatial technology is now becoming comparatively inexpensive with the expansion of data. And probably also it's coming out to be more simpler, because as we have heard from Professor Nanda and all, because of the computing facilities. So that's what it is coming to, because as I mentioned, it's not new and we have been all knowing it for. We also know, it's also been discussed that the basic list, as we normally see, when we open up any paper or any forum, we're talking about geospatial technologies, and has also been talked about by Dr. Naresh, and is that it encompasses, of course, remote sensing on one hand, GPS and GIS. Let's say three main things. And has been also mentioned that this remote sensing, we have active, passive, optical, and radar images, which are now becoming more and more popular. And experts are able to properly look into these images, able to find different kinds of targets, for example, as in SAR data. Also, and other people working in optical data, they are able to extract more information, which otherwise maybe 10 years ago was quite difficult to do that. Of course, one, we didn't have so much of data. Another thing also, lack of knowledge of what exactly to look for. Now we are able to find out. And what has been also mentioned that we are looking at applications in vast domains. because this is now coming that we are able to, like from the experts coming from DRDO, we are able to kind of point out atomic submarine to friends doing location exchange. I mean, this is the extent of it has become. I mean, people are using it to friends chatting and finding out location, to very, very niche field of finding out for defense application. So it's very, very vast. And I think that the eminent panelists we have over here, we come from the two backgrounds, and the next generation, I mean, as I mentioned, in the next generation, we are trying to teach the next generation of how to utilize them. First of all, the theory and the techniques of utilizing. Then there is a level, as mentioned, that we have to be able to find out or develop those sensors which actually will be able to capture those information, be it remote sensing, GPS, GIS, and many other newer technology. The next would be to extract meaningful information. Maybe it is utilizing the fundamental knowledge of our physics of what we have been doing, or going into the data learning, the learning methodology, which is nowadays advanced AI, has been mentioned by other panelists. So yes, it is actually vast. Well, we actually need to come from different backgrounds, and that the panelist over here comprises of, in order to, first of all, have to make those sensors and have those satellites or whatever equipments we are utilizing, acquire those data, and then trying to find out meaningful information. So in brief, the current application scenario and its adaptation of what is mentioned in the question says adaptation to current application scenarios. I would say that's really, really vast. And this is not the job of a single person to do that. But one thing we have to be very, very careful is that this should be inculcated to the young generation from the very beginning, and to make them aware of this technology, because this is so interdisciplinary in nature that we need people coming from different fields to tackle all these different stages of this problem. And I think that's the way to go, and that has been already nicely pointed out by all my colleagues in the panel. Thank you very much, Sangeeta.
Yeah, thank you, sir. Moving ahead, the next question. So already most of the panelists have already talked about the challenges in the various applications which they talked about, and also Dr. Dheeraj mentioned about what are the challenges at the SAR and all. So we are moving directly to the next question. Here I am combining two things together. How the geospatial technology is contributing in achieving sustainable development goals, and how do you see, or where do you see this geospatial technology in coming 5 years? So I would like to hear the opinions from Sandhya Kiran ma'am first.
Yeah. With respect to this question, I would say that geospatial technology has contributed a lot for sustainable management, because I myself have been carrying out for different projects for sustainability, in which we try to generate eco-sensitive zones for biodiversity areas, so and delineate certain sustainable areas which can be sustained for specific plant species. Also, we try to generate eco-city plan based on sustainability. So I think geospatial technology has contributed a lot. Only thing is its applicability at a administrative level is more important, because we find out so many good things and we try to implement it at management level. But yes, to a certain extent it's get implemented, but not completely. Like we had one project wherein we tried to bring out the different salinity patterns in a Khambat Taluka, and we could achieve a very good deal in maintaining those fields, because of the sea ingress, the crops immediately get completely vanished within a day. and if we don't identify specific plots with respect to salinity levels. So we could achieve that. And I think this, so many different projects we have seen, like in working plan inputs for forest and all these things has contributed a lot for sustainable management. But, and I told, what I feel is at present, what we are going for machine learning and different types of algorithms. And so I think we can still achieve more sustainability. Only thing is, as I told you in the beginning also, that I feel personally that to some extent, the validation of new things we are generating and applying it is not completely seen in the field. That's what I personally, because a lot algorithm generated for one location may not fit into the another location. So for we need to have a lot of data and field work for that. And in order to really, if you want to see that whatever machine learning techniques we are using, like recently only we have tried to find out the potential zones for water using plant species, wherein we could not achieve to that much extent because even the models did not work properly. So for that, I think something we should contribute. And of course, like yes, since last 2 days deliberation, I think I could see that if we like last lecture of Dr. Surya, wherein we have to face different challenges and we have to understand so many different factors associated with that. And I think if we do that, we can definitely achieve the sustainable development goals in the next 5 years. That's what I feel personally. Thank you.
Yeah, thank you, ma'am. Now we'd like to hear from Dr. Naresh Kumar, sir.
Okay. Now, what are the sustainable development goals we are right now working on? So basically, we looking at, let us say, clean water or groundwater, let us say, monitoring of the groundwater and having clean water, and how what is the kind of pollutants that are going into this water sources. Such type of monitoring is ongoing, and then we are using both geospatial technologies and gravity and other types of data to identify potential sources of groundwater and their contamination, and such types of studies are ongoing. And basically the next SDG, if you take, it is related to the clean energy aspect. And for this, we are trying to identify the solar energy, where wind and solar energy, where potential forms can be identified using geospatial technologies. And then we can promote that which are the zones or which are the areas where we can tap these energies, and then we can appropriately install these instruments, and all such activities can be progressed. The other one is the urban areas development and smart cities. These kinds of technologies such as your machine learning and deep learning are being used to identify, let us say, the growth, the urban sprawl, the type of buildings that are coming up. And basically in this also, we are looking at, let us say, to give you an example, if you are imaging a particular building or something, then what is the height of the building and other aspects, if you want to find out. This may be done through the identifying the shadows and all other aspects of the building, and then we try to compute the urban, the growth and the height and other aspects of the urban areas. So how do we manage the urban sprawl, and what are the techniques that can be developed? There is a lot of potential still with the newer and newer sensors that are coming up, such as the high resolution satellite imagery, and like Cartosat 2S and other satellites are there, where we are getting centimeter level data. Anyhow, globally also we have some very good sensors that are doing that. When we come to the food security aspect of that, a lot of work we are doing, especially with regard to the yield estimation, where we are using the deep learning technologies for yield estimation, as I told earlier as well. And also we are looking at the detection of pests and other crop related diseases using hyperspectral studies. And also we are looking at let us say the water bodies. If you come to hydrology, anyhow, drought is also a part of geospatial analysis is being done, and we are using the NDVI and other indices computed from the remote sensing imagery, and trying to study the time series and identify the drought, potential droughts and other things. That is related to the agriculture aspect. When we go to the identifying the hydrological droughts, we are also looking at the water bodies, how they are trying to grow or shrink, because there is some kind of a process involved. And there is also the nowadays you're looking at the snow melt and other aspects because of the climate warming. So these runoff and other aspects are also important for detecting the hydrological droughts. So these studies are ongoing, and especially we are using the ML-based techniques for detecting the water layer, their extents and spread. The other aspects of the SDG, I would say, let us say the disaster aspects, in event of flood and other things. We are depending heavily on the SAR imagery and for the extent of flood and its recession, how much of the area has come into the land, and what is the kind of extent of damage and other estimations we are doing it. And a very important other aspect is the landslides. So what triggers the landslide? How do we model that? And other aspects are being studied. In fact, if you look at geospatial data, one of the aspect is the time. One need to look at develop time series studies and also able to predict or forecast. So there we need to develop a lot of new technologies. I think there is a much way we have to go for attaining the SDGs. As and when the newer technologies are developed, we will be bridging the gap. Okay, thank you.
Yeah, thank you, sir. Now I would like to invite Dr. Dheeraj Singh, sir, to give his opinion on this.
Yeah, thank you. It was broadly well covered by Dr. Naresh, all the gamut of in the civil arena, like from the food security to the disaster management to crops and forest and biomass. I can just broadly divide into two aspects of that. See, in the next 5 years, what I'm seeing is there will be an enormous, because of the policy change of the government also, there is an enormous number of growth in both the segment, on the onboard segment and the ground segment of multiple remote sensing sensors. So what is happening now, you will see the kind of data which was like most of the people were not able to get the data to do a lot of studies and come out with a better model or better image analysis or data analysis or verifying their algorithm. Now I see in the another future, in coming 5 years, there will be wealth of data available, because now the government is promoting a lot of private sectors also to come up and work on various sensors and in all the kind of like either synthetic aperture radar or you say hyperspectral imaging, or because these are the area where not everybody puts their money, but then there will be a good ecosystem what we can foresee in the future, and then there will be a lot of data what to correlate your algorithm, to fine tune your algorithm for the onboard segment what I now described now. And the coming time, the hardware, whatever hardware will be available, they will be much faster, and then the algorithms, and then AI and the ML, the development models coming up. So they'll be such a robust model and robust algorithm will be there, so that the informations what we get out of the data will be much more meaningful and much more we can just take the decision based on those information without any hesitation at all. So that way I can see to achieve the sustainable development goal, next 5 years is very, very important. And from defense angle, I can say we can just achieve a sustainable development goal only when our borders are safe. So that is another area where you will see lot of like sensors flying and giving us information, so that we get the right information at the right time to take the decision, so that the intrusions and other things are also taken care, so that the country prospers in all the dimensions. Thank you.
Yeah, thank you, sir. Now I would like to invite Dr. Nanda to give his opinion and also summarize this third question.
Thank you, Dr. Sangeeta. Thanks all the panelists for, I think, Dr. Naresh and Dr. Sandhya, and Dr. Dheeraj Kumar. I think they have elaborated. I'll just share my thoughts first, and then I'll summarize. Actually, the UN mandate, United Nations mandate is there is 3 pillars of United Nations. One is, I think, peace and security, human rights, and sustainable development. These are the 3 issues. I think whole UN is, I think, divided, and there are many organizations like World Health Organization, WHO, kind of International Atomic Energy, could it be all the kind of UNESCO and all. So they have this mandate. One of the mandate is sustainable development, as rightly the question imposed, that it could be related to the food, kind of the related to agriculture, like we have to, I think, mitigate hunger in the whole total populations, like preserving water scarcity is a burning issue, and yes, energy is another issue which is related to the climate change and all. And because deforestation and the green cover, conserving the green cover is another issue which the kind of whole world is kind of debating or kind of moving to solve this. There is another issue because of the urbanization. There is a huge waste management issue. In a sense, if we see look at the data, we have huge waste, particularly the non-degradable waste like the plastic waste. And how do we handle those things? And because we are advancing at one stage of urbanization, and the other aspect is retarding the managing the waste. And because of that, the contamination happens, and the health is related to that. So we have health hazards, and when you are progressing in one direction, I think you are receding, I think digressing in other directions. So therefore, geospatial technology, or the kind of this kind of technology helping a lot in this. So I'll look at the peace and security also. Even though our we are thinking of a hunger-free world by UN, nevertheless we still see people in different countries, like whatever African continent and many other places, people do not have square meals, and there are a lot of unrest happening in different countries, and a lot of trespassing, a lot of kind of disturbance, diplomacy happens because of this kind of security or the peace, which is hampering security. Therefore, the National Security Council is there. So geospatial technology is helping to monitor, and it's also helping to sustain development as a trade. In a sense, the marine kind of the business or the marine science itself is a huge kind of contributing to the economy. And there are a lot of problems or issues arising there. And this geospatial technology is helping to curb those menaces which are happening in the marines of our whole world, the kind of the water body. As far as the water is concerned, as I think spelled by Dr. Naresh, that protecting or the conserving water is a big issue. I think there will be time that already people have felt because of the urbanizations. I think we had seen in Cape Town that depletion of water, and similar things will happen in other growing cities. So identifying what bodies, conserving them, preserving them, and where it is depleting, this kind of identification and prediction and protection definitely will help us in this. And geospatial technology, this kind of technology is helping us a lot while analyzing the availability, analyzing the situation and predicting the situation for future. And therefore, this is one of the very important areas. As far as the food is concerned, we have been advocating to have a hunger-free world, and agriculture is now taking a new step, and sustainable and smart agriculture is the buzzword of this today. And as far as the sustainable and whatever the smart and sustainable agriculture is there, geospatial technology is kind of a boon, and with this only I think things can happen. So therefore I think it is directly I think helping us. One of the goals mandated by UN, that's food and water. Energy is another issue. Even the fossil fuels are being going to be depleted soon. So identifying the alternate energy and handling them, and in fact relating them to the climatic change also is important. And therefore we move to a paradigm shift will happen in 2030. And in recent I think Glasgow conference, many leaders of the world proclaimed vows for that, to have zero emission countries. And to control that, to monitor that, geospatial technology will be of the great help. And as far as the climate change is concerned, the byproducts are multifold. Plethora of issues do exist, and preserving the green cover, forestation and deforestation is a big issue. So for which this kind of technology will help us, as we have seen. Yes, to prevent and to protect them, we need this kind of technology, analyzing data, protecting them, taking the law, taking the measurable, taking the strong measures to prevent this from the scrupulous people. So that will help. This geospatial technology will help a lot. And in essence, also the handling the disaster as spelled by my fellow panelists. The disaster management is a byproduct of disaster, is a byproduct of this climate change which is happening now. And handling those changes and predicting and making zero loss of life and saving the lives of the people, they are the geospatial technology helping us a lot, because the models have been proposed. The accuracy of the model, the prediction, all depends on this technology. Could it be sensor? Could it be analyzing the data with the machine learning or deep learning or whatever the image analysis technology? So these are the technology helping us to protect the earth for sustainable development. And as I suggested earlier, that waste management is another big issue which the whole humanity is bothered about. I think some of the nations have already, I think, working on this, how to protect, and people have already been our is because again of this. And the marine life, the kind of the whatever the flora and fauna that exists in the kind of the sea, they have to be protected. And the kind of the health hazards which are occurring due to misuse of this will also be protected by this geospatial technology. I think all aspects, could it be climate, could it be, now the biggest issue is the air also, which is a health hazard. In many cases, the biomedical waste management, biomedical or health hazards is a great issue, which also can be controlled by, can be monitored by this geospatial technology. So it has a lot of applications which have been shared by my fellow panelists. All the panelists, Dr. Grace Singh, also Dr. Sandhya Kiran and Dr. I think Naresh, all of them have shared that different aspects and different goals, sustainable goals. I think in every goal identified by the UN, mandate of the UN, their geospatial technology will be of huge. Maybe it needs a kind of a subsidiary kind of thing, is machine learning, kind of data handling, a big data analysis, could be sensor technology, could be device technology. All these are contributing to the special technology for sustainable development directly or indirectly. Most of them are directly contributing to it. Thank you for giving me opportunity to share my views.
Yeah, thank you so much, sir. I would like to thank all the panelists for sharing their views on the topic, that is geospatial technology applications, present and future. So indeed, here as we are moving towards, we have seen over the years, people have adapted use of geospatial technology. And nowadays you see even a layman can use geospatial technology with the help of mobile phones in hand, which was not possible earlier. And also, as rightly pointed by everyone, in the to actually achieve the sustainable development goal, geospatial technology is one of the very important, or it is playing a very crucial role in various SDGs like health, or maybe the clean water, sanitation, the energy, and the sustainable cities, as well as the climate action. And as Sandhya ma'am pointed out, that people are using geospatial technologies and in various applications, but they need to see that the precision, or the more precision should be precision is very, very important, and it should be actually taken into consideration when people are working on application. So obviously in coming 5 years or 10 years, we can see that geospatial technology will become an integral part of everyone's life. And of course, in every application arena, it is one of the, it is playing very important role at all places. So once again, from IEEE GRSS chapter, Mumbai chapter, I would like to thank each one of the panelists. Thank you all. Thank you very much. Over to you, Graju.
That was indeed a glimpse of how true collaboration looks like and how ideas can be amalgamated to form a completely new perspective when so many intellectual peoples join together. A hearty thanks to all our panelists and also our coordinator, Dr. Sangeeta Chaudhary, for making this panel discussion continue without any disruptions. I would now like to call upon Hayden Cordero to present the vote of thanks. Hayden?
Hear me, Raju? Hello?
Yeah, you can.
Good evening, everyone. It's my privilege to propose the vote of thanks on behalf of the IEEE GRSS and the IEEE GRSS Bombay Chapter and the entire symposium organizing team. I would like to thank each and every panelist present here for taking their time out of their really busy schedules and contributing to the discussion. We really believe that this session and discussion has been really informative and didactic. I would also like to thank Dr. Sangeeta for coordinating the simulating discussion, not forgetting the whole audience and the team behind the session. Once again, thank you all.
Thank you so much, Hayden. Now, without further delay, we'll go forward with our next session. Next up, we have a very thought-provoking session. And for that, I would like to invite Dr. Sushri Sangeeta Mishra, Women in Engineering Ambassador, IEEE GRSS Bombay Chapter, to introduce our next speaker, Dr. B.S. Dayasagar. Over to you, ma'am.
Wait a minute.
Yes,
thank
sir.
you, Avik sir. Thank you, Pradip Nanda sir. Thank you, Naresh sir. Thank you, Dheeraj sir. And thank you, Sandhya ma'am. Thank you for joining with us. It was a wonderful evening to seeing you all together at all. Thank you very much.
Yeah, thank you, Amir.
Thank you.
Pleasure to be there.
Yeah.
It's really nice meeting you, everyone, online. Thank you, and we will meet sometime in person as well. Thank you.
Yes, sir. Yes, sir. Thank you all.
Thank you, Professor. Thank you, everyone.
Sir, can I continue?
Yes, ma'am.
Good evening, everyone. Thank you so much, Grejo. It's indeed a great privilege to introduce Dr. Dayasagar. Dr. B.S. Dayasagar is a full professor of the System Science and Informatics Unit, SSIU, at the Indian Statistical Institute. Dr. Sagar received his MSc and PhD degrees in Geoengineering and Remote Sensing from the Faculty of Engineering, Andhra University, Visakhapatnam, India in 1991 and 1994 respectively. He is also the first head of the SSIU earlier. He worked in the College of Engineering, Andhra University and Center for Remote Sensing Image Processing, CRISP, the National University of Singapore in various positions during 1992 to 2001. He also served as Associate Professor and Researcher in the Faculty of Engineering and Technology, FET, in the Multimedia University, Malaysia, during 2001 to 2007. Dr. Sagar has made significant contributions to the field of geosciences, with special emphasis on the development of spatial algorithms meant for geopattern retrieval, analysis, reasoning, modeling, and visualization by using concepts of mathematical morphology and fractal geometry. He has published over 85 papers in journals and has authored or guest edited 11 books and special theme issues for different journals. He recently authored a book entitled Mathematical Morphology in Geomorphology and GIS Science by the CRC Press, Boca Raton in 2013. He recently co-edited 2 special issues on filtering and segmentation with mathematical morphology for IEEE Journal of Selected Topics in Signal Processing and Applied Earth Observation and Remote Sensing in India, for IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing. His recent book titled Handbook of Mathematical Geosciences, published by Springer Publishers in 2018, has crossed 8,50,000 downloads. He was elected as a member of New York Academy of Sciences in 1995, as a Fellow of Royal Geographical Society in 2000, as a Senior Member of IEEE Geoscience and Remote Sensing Society in 2003, as a Fellow of the Indian Geophysical Union in 2011. He is also a member of American Geophysical Union since 2004 and a life member of International Association for Mathematical Geosciences, IAMG. He was awarded the Dr. Balakrishna Memorial Award of Andhra Pradesh Academy of Sciences in 1995, the Krishnan Medal of the Indian Geophysical Union in 2002, the Georges Mathurin Award 2011 with lectureship of the IAMG, and the award of IAMG Certificate of Appreciation in 2018. He is also the founding chairman of Bangalore section of IEEE GRSS Chapter and has been recently appointed as an IEEE Geoscience and Remote Sensing Society Distinguished Lecturer for a 2-year period from 2020 to 2022. He is also on the editorial boards of Computers and Geosciences, Frontiers, Environmental Informatics, and Mathematical Geosciences. He is also the editor-in-chief of the Springer Publishers Encyclopedia of Mathematical Geosciences. And today, Dr. Dayasagar will be talking about mathematical morphology in processing and analysis of the digital elevation models. It's time to hear from you, sir. Over to you. Thank you.
Good evening, everyone. Amia, can you hear me?
Good evening, sir. Good evening, sir.
Thank you, Sushri. And I know you and you are quite familiar name.
Thank you, sir.
Yeah, so with all your permission, and I have given one, the popular topic which I have been talking at all DL talks across the globe. That is about mathematical morphology and processing and analysis of digital elevation models. But looking at the symposium title, and I have actually slightly changed the structure of my talk, and I'll try to wind it up within 45 minutes. Mostly I'll avoid the mathematical aspects of my talk, and I have given that at the end of all my slides as an appendix. And because the mathematical morphology that I have been using for the last 3 decades would take about at least some 10 to 15 hours of lectures to explain it in a way that the people will really understand. So that there is no point unnecessarily, squeezing the talk with a lot of mathematical jargon. And I'll try to see that if the people can start thinking intuitively what exactly intelligence that we really talk in terms of geospatial aspects. It's a nice topic, and it reminds me about a couple of my great friends. Like one of them was, I think we have been talking about geospatial intelligence, and we should actually talk about a lot about a person called by name Professor Waldo Tobler. I'm not sure whether there is any geographer in the entire audience. Waldo Tobler was I can say that he is the first person who has brought in a lot of mathematics and computations into geography and geographic information science. And he passed away a couple of years ago. Waldo Tobler, I remember that he sent me a CD with all his works of almost ranging for about 50 years of his works. And so very, very interestingly that he has introduced the first law of geography. The first law of geography is, we all know that, but we don't know that who is the person that who should be given the credit. Like Waldo Tobler, he mentioned first law of geography as nearer things are well correlated and farther things are less correlated. We know that which is a very popular law, and then but it is quantified very nicely by following spatial autocorrelation methods such as Moran's index. I think in all geospatial commercial softwares, and you will see the Moran's index computation, and it will tell about how good is the data, which is aggregated form or disaggregated form or randomness. And that was the paper written by P.A.P. Moran in late 60s. But its application, people had to wait for about 30 years because it's such a complicated statistics paper. But subsequently, about 25 years ago, people started looking at that carefully, and which has number of applications, which is of fundamental importance. Okay, and with that brief background, let me just share my screen and I'll see how I can sail through. Can you see the slides?
Yes, sir. Yes, sir.
Yes. So this is how with all your, so my sincere apologies, and I thought of sending a message to Amiya in the morning to tell him that the title is slightly changed, but I am sure that it is more appropriate than just talking about digital elevation model processing and analysis and the geospatial intelligence and mathematical morphology. And as I mentioned, and so Waldo Tobler also mentioned me in 2014 when he has looked at my book, and then he said, and he had some interaction with Georges Mathron. The Georges Mathron is the co-founder of the field of mathematical morphology, but he also mentioned that Georges Mathron could not meet Georges Mathron, but subsequently Adriel Rosenfeld, whom we consider as father of image processing, and he explained him a bit of mathematical morphology in his own style to see that Waldo Tobler understands it. And so that was another background information. So this topic, and so when I have looked at the symposium title as Geospatial Intelligence Symposium, and I have a kind of argument. Initially, I thought it is a definition, but I am not that big to really give any definition. But so this is an argument that the argument is to transform an objective. We have several objectives, and we start talking about various different spatial, geospatial, geographical information science, and which involves objects and fields, spatial objects and spatial fields. And you name in our remote sensing and geoscience community, and we have everything. We can broadly categorize them as spatial objects and spatial fields or spatial functions. To transform an objective into a functional or an executable form through mathematics for the sake of objectivity, natural intelligence precisely needs to be transformed into artificial intelligence. You can look at it. What is the objective? What is the mathematics? Why we use mathematics? Mathematics is to derive some kind of inferences, and which would follow objectivity. And so as a great man says that we may lie, but mathematics doesn't lie. And so at the end, whatever the results that we get, which we can actually generalize it. And that is where one should be, very confident to use a specific mathematics, which is really useful for his or her own research work in the long-term plans. So through mathematics, this is the transforming the natural intelligence into artificial intelligence requires mathematics. And of course, you require a kind of objective. What is that we are actually handling it? So to define these things and to just give a few kind of examples. And what is data in geospatial intelligence? All through we talk about spatial objects, specifically mapped units, which are noise free. Perhaps somebody in the panel discussion, he was talking about water bodies. I would say if you precisely isolate water bodies, you have water bodies and no water body region, and I would call those water bodies are spatial objects. And spatial fields, and all our remote sensing images and digital elevation models are spatial fields. And so obviously when you try to map your spatial fields and you want to bring it down to some kind of simplicity, and which are nothing but thematic maps or spatial objects. So what is the objective? Which two spatial objects? This is just an example. Objective, when the objective is like, we are actually trying to find out of so many spatial objects available on the screen, which two spatial objects are the best interacting, the interactions. And again, I have to go back to Waldo Tobler's arguments, and then his theories were very powerful, mostly in spatial econometrics and of course geography and spatial demography. Wherever you include the spatial aspect, and Waldo Tobler's works have to come into picture. If somebody is not using Waldo Tobler's work, and I would say that probably overnight somebody wants to become a geospatial scientist, and it's not that. And if we go back about 50-60 years ago, and we have to start from Waldo Tobler's work. And which two spatial objects are the best interacting, or how to detect a statistically important spatial object among a cluster of spatial objects. Just to give you a kind of intuitive understanding, all our the political units, like our 28 states, are like spatial objects. If someone asks you which is that state located strategically important location, and how do you find out? And if I tell you that you don't use any mathematics, don't use computers, and if you use your own expertise and then you try to find out, and perhaps this one, like that. And I would give you a clue. So which is this most strategic spatial object within a cluster of spatial objects? Perhaps you can think about like a traveling salesman, and you go to, with minimum energy expenditure, how you can reach to a spatial object, a specific spatial objects. In our case, it's a state in Indian map, and a specific state, and with minimum energy expenditure, anybody has to reach out to that particular state. And what is that state? And obviously it requires some kind of spatial optimization, right? And we will look at that. And then mathematics, as I'm so fond of the field of mathematical morphology, and I could see that how mathematical morphology could deal with or handle various different phases of geospatial intelligence. And I should also give the credit to one Professor Graham Lodwick, who used to sit in Curtin University of Technology in Western Australia, Perth. And he was the first one, I can say, that used mathematical morphology in geospatial intelligence. And that was in mid-90s. The natural intelligence, mostly through logical description by an expert. And so this argument of, the natural intelligence and artificial intelligence, which is great over the other one, and that discussion, let us not go into that. But artificial intelligence, such that the machines can understand and mimic natural intelligence. So for this, and if you go back, my argument has some basis. To transform an objective into a functional or executable form through mathematics for the sake of objectivity, natural intelligence precisely needs to be transformed into artificial intelligence. The next slide, and as just to tell you that these are the two co-founders of mathematical morphology. Beyond this, you don't see any mathematical equations related to mathematical morphology. If you're keen, and I would leave these slides with Professor Amia, and he can share with the audience. And at the end of the slides file, and you have some 15 to 20 slides I have put about, the basics of mathematical morphology and what to read, what not to, what to avoid, and those things. Broadly speaking, in math, we have different categories like binary mathematical morphology, precisely useful for dealing with spatial objects, and grayscale morphology, precisely useful for studying the spatial fields or spatial functions, or all our remotely sensed data like images, and graph mathematical morphology, which is gaining a lot of popularity to reduce the computational complexity, and then adaptive mathematical morphology. In morphology, we actually talk about investigating the data with another data, and the another data is precisely the probing rule, a query. How to define that particular probing rule to investigate your own data, whether it is, simple binary form or in a kind of, multi-level form, multi-valued form. So this also recently, if you are familiar with one of the mathematical fields, which has a lot of geometric sense, and many of our geospatial or remote sensing or geoscience problems, the way we handle, if you are using a specific mathematics, is entirely different. And that is where I suggest people to introduce, at least in their undergraduate graduate curriculum, about teaching a specific mathematics which is really useful for handling remote sensing, geoscience, and geospatial data sciences. This was an opinion piece which was published in December 2020 issue of IEEE GRSM. Somebody is interested to have a look at it. It's about 6 pages education article. So just to give you an overview of the talk, and so geospatial intelligence, a few cases, and what are those few cases? Spatial optimization. When you map the units, like water bodies are the mapped units, or watersheds within a river basin are the mapped units. And let us assume for the time being, all these mapped units are planar forms, compact spatial objects. And then you have to think about where the spatial optimization comes into picture and where the spatial interactions. So spatial interactions, which is very popular, again, which was initially the idea was given by Waldo Tobler. Looking at our Indian states of about 28 states, and if someone asks you which two states are interacting in the best possible way, which are those 2 states where the interactions are very feeble? The moment we talk about interactions, and we should go back to our, the high school physics about Newton's gravity model. And Newton's gravity model is very popular, and then which has been heavily applied in economics, mostly, theoretical economics. And so they call it as a social gravity model. But we all know that gravity model is a kind of symmetric model, and which is the force of interaction between object A to object B, and the force of interaction between object B to object A are the same. So that is where we say gravity model is symmetric. But thinking about social aspect and social sciences, in social sciences, we come across various different ways of finding out the interaction between the people, interaction between the groups, interaction between the states. I'm talking interaction between the states. And the moment I say that, and someone should ask me, in terms of what? The interaction in terms of what? So if I say that in terms of, let us say, land area cost, probably I'm talking about some kind of something related to trade. Land area cost, and there are 2 states, land mass area is the larger the area and higher the price, and smaller the area, lower the price, cost of the land, right? And so you have 28 states, and I want to find out, you give me a solution, and how is ith state is interacting with jth state, and how a jth state is interacting with ith state. So the modified gravity model tells the interactions are not symmetric and they are asymmetric, because mostly in gravity models we use the distance, where the distance from A to B is equivalent to B to A. But the moment we talk about spatial objects, it doesn't necessarily be the distances between A to B and B to A are the same. And because of the geometric variations and the aerial variations, and there are many other things. So that is where the spatial interactions and the gravity models are, well connected. And I'll show one. Mostly my case studies were some pictures only. I will show it. And then spatial representation of variables via cartograms. And we have a large number of variables coming into in our geographic information science. And so you talk about the population density as a variable, or crime rate as a variable, or agriculture yield as a variable. And if you're talking about state-wise variable data you have, but the moment we take the data, what do we do? And we'll put where the agriculture yield is very high, we put with some kind of, color or a hatching symbol. and where the agricultural yield is low, and we put it with a different hatching symbol. If we have 5 or 6 categories of agricultural yields for all 28 states, and we follow 5 different colors, and then we put a legend. So that is the way of representation, which are called choropleth map way of representation. But is there a way to represent in a different way? By using the computational geometry methods. And again, Waldo Tobler has introduced the concept of cartogram significantly. But somebody was explaining me, my great friend, one Mike Gassner, who has given a wonderful algorithm to generate cartograms, variable specific cartograms, and he said no, it dates back to almost 18th century, and the word cartogram was actually given. Those days and how they were represented, it's different, but it gained a lot of popularity after Waldo Tobler spoke about cartograms. And so these are like spatial interpolations and extrapolations. We have sparse data. Converting sparse data into dense data is a challenge. And an example, analogy I will give. Earlier, about 20-30 years ago, we have only 3-band data or a monochrome band. So now we have hundreds of bands. Now we are talking about, we don't want to handle all hundreds of bands to process and extract some information. We want to reduce the dimensionality. The dimensionality reduction problems have come into picture, and then that is where dense to sparse and sparse to dense. And you have very sparse contours, elevation contours, but you want to show that in a dense contour thing. And so that's where we have to use spatial interpolations and extrapolations. And spatial data classification and clustering. And if you have so many images in a database, how do you group them? We have K-means clustering and all those powerful methods. But and using some kind of morphology based distances between the spatial fields in the database, and you can actually group them, and which we call them as a ranks for pairs of images. And so you can each pair you can give a rank, and which is the best pair and which is the worst pair. The worst pair is always they're dissimilar to the ith image to jth image, and the best pair is almost, it's like my face to my own face. And so if you say what is the distance between my face to my own face, I would say this is the best pair I can define. Right. And then spatial data, DEM processing and analysis. But this portion, I would like to, I don't think the time would be sufficient. But that lecture I have given recently to the Brazilian chapter, and several other chapters I have given. They are all available in public domain, and one can have a look at those things. And then how the above studies would be useful, and then appendix as mathematical morphology, notation, sequence, and transformations, and all that we see. So this is what spatial objects we are talking, mapped units and spatial fields. Typically, the example of spatial field is a kind of DEM or a remotely sensed data. And there are 3 spatial objects. If I ask you, tell me which is that spatial object centrally located, such that from other objects, it is easy to reach out to that particular spatial object with minimum energy expenditure. So that gives, and people will say with a different thing, and I may say, oh, this is the best possible location it is located. And Amiya may say that, no, this is this, and he has his own logical reason. And so someone, Sushi, may say that this is the spatial object which is centrally located. But is there a way that we can actually show some kind of spatial optimization challenge here? And for that, what we do, we actually compute the distances between every object to every other object. And then we come out with, column-wise maxima values distances, and then the minimum of all the maxima values is the object which is centrally located, right? And to show those things, and so I will just go into, okay, this is PPT slide. 1 minute, and I will just change it to, yeah, this is anyway, so let me go further. And so this is just to give a kind of intuitive understanding. There are 10 streets or spatial objects, and so which is the most strategically located spatial object, and what we have done. And so they have such certain spatial relationships, and if you take the intersections of all these spatial objects, And this is how it is represented, but the intersections of all of the spatial objects is yielding an empty set, which would tell you that there is no overlaps, and probably like water bodies in our case. And these are some of the spatial relationships were given, but to show what are the distances, you have a spatial object AI and spatial object AJ. How do you compute the dilation distance? You compute the dilation distance, you keep dilating this by keeping this stationary for how many number of dilation cycles you will do it until this object is covered. What are the minimum number of dilation cycles? Dilation is a morphological operation. You expand the object, and so you dilate the object, and this is how when you dilate it, and all these green lines, this has taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 dilation cycles of this object has occupied this particular object. And then similarly, it has taken about 9 or 10 dilation cycles of this particular object to occupy this one. These are the minimum number of dilation cycles. And I would say the distance between AI to AJ is 12 dilation cycles, and distance between AJ to AA is about 9 dilation cycles. Of course, if you take minimum of these 2 dilation cycles, and you get the Hausdorff dilation distances, and those things let me just avoid. But let me go to the next slide, and you look at here, these are the 3 spatial objects I was talking. And if so how we compute, and from every object to every other object, we are keep on dilating with different cycles until it occupies the other object. And how we have performed this, and directional dilation distances we have computed from every object to every other object. You can see it by keep on changing the origin of the dilation structuring element with which we are actually dilating each object to find out the dilation distances. And so this is how we compute the dilation distances between A to B, B to C, and C to A and C to B, like that. You have a 3 by 3 matrix, and that tells you dilation distance interaction matrix, right? So I will stop that animation and I'll go further. You look at here and how we have employed the simple dilation distances. We have a remotely sensed data here. There, all these, the blue patches were water bodies, and we have isolated these water bodies, and then we have computed the dilation. There are 66 water bodies here. From every water body to every water body, dilation distance were computed. And then, so you look at this example. Before going into that, there are 3 objects here. Distance between x1 to x2, x1 to x3, x1 to x1 is the 0 distance. And you can see this particular table, and the column wise maximum value you compute. This is the maximum dilation distance from x1 to x1, x1 to x2, x1 to x3. Similarly, x2 to x1, x2 to x3, x2 to x4, and this is the maximum thing. So out of this, which is the minimum distance, minimum of all these maxima, is the strategically located object. That corresponding object, what is it? It is x2. X2 is the strategically located. In that fashion, for all these 66 water bodies, you have 66 by 66 dilation distance matrix, and out of which column wise maxima value compute. Minimum of all those 66 maxima values, column wise maxima values, will tell you which is that water body strategically located. And this is the spatial optimization problem. If someone tells you to create a spatial social policy, if the government says that we have 66 water bodies in this particular watershed in a river basin, and all water bodies are going to get dried up, and we have money to only protect 1 or 2 water bodies. Which are those 1 or 2 water bodies? The people living around these water bodies should not grumble, and they have to spend minimum energy to reach out to that water body to fetch the water for their livelihood, right? So under such circumstances, you have to have some kind of a spatial optimization based approaches to tell the government this is the scientifically viable and valid approach, and you follow. This is the water body strategically located, and its corresponding watershed is this one. And so this is corresponding influence zone of these water bodies is this. And we have done this exercise for both water bodies and their corresponding watersheds, right? And that is all about the spatial optimization. When I come to spatial interactions, and before showing the equations, let me show you I would say this is a kind of spatial system within which we have a subspatial system. And that subspatial system has about 28 states, the states of India. And then you have given, so each state with certain index. And then idea is, which are those two states are better interacting? And as I mentioned, I want to use the gravity model here. And the gravity model is just mx1 and mx2. These are the masses of x1 and x2, or xi and xj, divided by the distance between xi to xj squared. And you use some gravitational constant. And that would tell you the interaction between xi to xj and xj to xi is the same. So, but there is some more very important aspects. So what is that aspect? Location significance. Not all the states have highly at the important state. I would say Chhattisgarh and Madhya Pradesh are at the statistically important locations. But whereas when you see these exterior states and they are having, feeble importance, then you find out the location significance index for all 28 states based on the spatial optimization approach and what we have followed earlier in the computing the distances between every water body to every other water body. And you derive the location significance index for each state and use that location significance index within the gravity model. And so now you go back. And this is the classical gravity model and the Newton's gravity model. And we know that when we are talking about the spatial objects, we follow all these spatial relationships. And the location significance index, how do you compute? And we are taking the statistically important object or the state of India, and then we are dividing that with the maximum of all maxima. And then you are assigning that particular state with some location significance index. And use those location significance index, and you have the same parameters like mass of the xi and xj and the dilation distance square, and then product of the location significance index of xi and xj. And in turn, the force of interaction between I and j and I are different. So this is quite acceptable when you talk about the gravity model in the context of social sciences. See, when Singapore and Malaysia, and these are the two countries, and they do some kind of trade analysis for win-win situation. And you cannot say that the benefits that Singapore got is just like that, and the benefits of Malaysia is also similar to the benefits of what Singapore got. And there are some variations, and those variations should reflect in the gravity model when you employ a gravity model as the basis to find out the force of interaction between the states or continents or the spatial objects. And so that is where we introduce this particular location significance index. And then this dilation distance is not equivalent to xi to xj and xj to xi. And these are two dissimilar things, because we are dealing with these spatial objects which are highly dissimilar in their geometries. And then we keep computing the dilation distance interaction matrix and location significance interaction matrix. And this is the product of location significance of xi and xj for all the 28 states. And then mass, the product of the mass of xi and xj, mass is the probably land value we have used it. And then by taking all that, and we incorporate those things in the modified gravity model, and then you start computing what are the interactions and which are the two states having higher interactions. And we have followed which are the best interacting states, which are the least interacting states. And that one you can see again, the best interacting states are Orissa and Chhattisgarh, followed by Madhya Pradesh and Uttar Pradesh, and Uttar Pradesh and some other state here. And then, so this is how 5 best pairs were given on the top, and 5 worst pairs in terms of interaction were given at the bottom thing. And look at here, this is the initial things, and these are the best interacting pairs. And as you go to the end of the animation and you start seeing, let me go to the end, and then those states were actually farther from each other. And so, as I mentioned again, Waldo-Tobler's interaction theory, nearer things are well correlated and well interacted, and farther things are less correlated and less interacted. So this is the animation that you can always see it. And then the next one is about spatial representation of variables through cartograms. You look at here, this cartogram idea is don't use the colors and like choropleth maps. And assuming that there are 4 states here, Andhra Pradesh, Karnataka, Tamil Nadu, and Kerala. And Andhra Pradesh, I'm using a unified Andhra Pradesh. And assuming that the crime rate is very high in Kerala, followed by Karnataka, Tamil Nadu, and Andhra Pradesh. And you have to show them when the crime rate is very high in Kerala, that has to be shown much bigger, followed by Karnataka and Tamil Nadu, and then Andhra Pradesh. And we follow the flood propagation principle, and you have multiple water bodies. You allow each water body to propagate with different speeds. Higher the crime rate, you allow that particular state to propagate much faster from the minimal skeletal point. Minimal skeletal points are this. And how we computed, again, by following, we have computed the skeleton and we took the minimal skeletal point as the centroid. And for them, this is how we have generated. For different strengths of the variables for different states, we can generate cartograms, something similar to these 4 maps we have shown. And these 4 cartograms are with different variable strengths. And higher the variable strength, and you make sure that it is shown much bigger. And you can see it here. And these states are actually propagating with different speeds. And then this is also been used to convert the non-contiguous point-specific data to the contiguous zonal maps, and which is very much useful in the GIS. And you look at here for the population as the variable. And this is the simple US map, which we'll call it as equal area projection map. And so for population cartograms, there are various different approaches given by various different groups. And the most powerful approach until now is the Gusein, Jade, and Tikhonov. These are the Russian mathematicians given cartogram generations by using partial differential equations. But this approach, you look at here, this has protected the global shape and to the extent possible local shapes of each state and some adjacency relationships, providing global shape and with minimal errors and local shapes with minimal errors, and then adjacency relationship. California should be adjacent to these 2 things, these 2 states. And after generating the population cartogram, this looks like this. Higher the population, it has to be shown much bigger. Lower the population, it has to be shown much smaller. Assuming that California has a very low population, that has to be shown much smaller. And Nevada has very high population, and then that has to be shown much bigger. There is no analytical solution, but computationally it is possible. And the approach that we have followed is a weighted skeletonization by influence zones, right? So that was about the third point, that is spatial representation of variables via cartograms. And the spatial interpolations. And so these are all, the computationally very sound, and then a solid mathematics is behind. And this particular work, what you are seeing on the screen, is about generation of hierarchical median elements between the successive maps. And these are all epidemic maps, and 1896, 97, 98 bubonic plague, which affected Indian subcontinent. And we have only 11 maps, but can we, I would say this is a sparse data. And can we convert that sparse data into dense data? I want to know what are the interpolated maps between this map and this map. And so between the interpolations, it's a hierarchical way you generate until there is no further scope for you to insert one more interpolation. And that was the idea we followed, and where we have followed simple multi-scale erosions, multi-scale dilations, intersections, and unions. And then we started computing them hierarchically, the median elements between the source map and target map. If you take this is source and target, and you can generate this similar to this one. And if you take this as the source and this as the target, you can try generating the predicted map like this. And how observed and predicted are good, and in terms of distances, and we could validate it very nicely. and that was eventually it was published in IEEE Farming, right? And you look at here how this is with 164 possible interpolated maps that we have generated between the successive maps. There are only 11 maps here, and 11 plus 164 hierarchically generated median maps. We have put them in a kind of a sequence. And I'm sure that the audience would appreciate that there is a lot of computational intelligence involved here. And so what is the idea? We have followed simple morphological interpolations hierarchically. You require the spatial object data. Here the spatial objects are epidemic spread, right? And so I will stop this interpolation here, animation. And the algorithm is here, and that is about binary morphological interpolation. If you follow, you have a landscape A and landscape B, or landscape F and landscape G. And I would say that DEM-F and DEM-G, digital elevation models. And you know that DEM-F is about 100 years old of the DEM-G. But you don't have intermediary data, but you want to actually try predicting what should have been the intermediary data. So for that, what we do, we follow the grayscale morphological interpolations. We take infima of ith function and jth function, and suprema of ith function and jth function. Infima, supremas are nothing but point-wise minimum, point-wise maximum. And then infima between I and j would be dilated, keep expanding. This is typically the grayscale dilation. And n will tell you this is a scalar quantity. The size of the probing rule will keep increasing. And similarly, we follow the dual to dilation is the erosion. And then infima would be eroded. And then you take these two outputs, infima, and then for all the median function that you have computed between fi and fj for all n values, you take the suprema of all those outputs, you get a median function. What exactly it is, and there actually the illustrative matrix way of computations and representations are given. I don't want to take more time. And Amia, can I take another 5 minutes?
Yes, sir. Yes, sir.
Yeah, in another 5 minutes, I will happy to.
Yes.
So you look at here, this is a digital elevation model of, let us say, this is time t. And this is the same digital elevation model of about, let us say, after 10 years. There is structural, morphological, and topological changes have happened over a period of 10 years. But you don't have what exactly happened in between. You have two, source and target. This is the source and this is the target. So you can compute a kind of median function between source and target precisely by following this particular grayscale morphological median computation equations, right? And so we have, for everything there is a dual, and you can compute the median and you can compute the dual median. The dual medians and actual medians, they're very well related, but mathematically speaking, dual median is the exaggerated version of the actual median. And those things, if somebody is interested, they have to look at the papers that I've actually quoted here, which are published, right? So you have source and target, you have created one median function. Between source and median, you can create one more median function. Between median and the target, you can create one more median function. This goes in the fashion of 2 power n. Initially, you have 1, and at the second cycle of median computation hierarchy, you have 2 median functions. And at the third one, you have 4, and the fourth one, you have about 8. And this goes in that fashion until there is no further scope for you to compute one more median level. And then you put them in a kind of sequence, and you can say that about 10 years back DEM, or a period of 10 years, how it has been slowly metamorphosed. And this is the source and this is the target. In between, hierarchically, we could create so many median functions. And then you can see how they have actually this animation is not somehow working. Actually, these animations would show that how animation, this DEM has been slowly transformed into particular this DEM. And let me just go further. So that's about interpolations between either spatial object kind of map, that is the bubonic plague maps that I have shown, which are just black and white, or the functions and the spatial fields and like DEMs. And now you have 100 channels of hyperspectral data. You felt that one of the channels was missing, and can you really use this idea? I think one should really explore. And these morphological medians or morphological interpolations are so powerful because they are of nonlinear type. Many of the linear interpolations would show some kind of aliasing effects, but nonlinear interpolations are very soothing to your eyes, and the transition is very smooth. And you can, I will really encourage people to employ nonlinear interpolation techniques than the linear interpolation techniques. So shall I tell you what is the linear interpolation technique? Kriging. Kriging is a powerful linear interpolation proposed by Georges Matheron by putting the name Krieg. Krieg is the name of Danny Krieg. Danny Krieg's master's thesis was the motivation for Georges Matheron to give that idea of Krieging technique, which is a powerful geostatistical tool, which is available in all GIS packages. But Georges Matheron has put the name Krieging because the motivation has come from Danny Krieg. Danny Krieg was a mining engineer of from South Africa. Like then spatial data classification and clustering. I would quickly, this is a paper published in IEEE Transactions on Image Processing. And what are the things? And we have dilation distances between the spatial fields, not the spatial objects, which I have shown in animation form. And then erosion distances between I and jth image, and you have multiple images in the database. And so then you also compute a kind of a rank equation. You have infima, suprema between ith to jth images, and then their supremas are here. And if you take the ratio of this, and which would be ranging between 0 to 1. If it is 1, and specifically you are talking about I and jth images are the same. And then the distances, erosion and dilation distances, minimum of these two distances between ith to j is the numerator, and maximum of those two distances is the denominator. And then you take the product of these two ratios and you get a value. That value would tell you whether I and j are better ranked pair or worst ranked pair. And using those ideas, again, the spatial interactions are involved here, but not on the spatial objects, but on the spatial fields. And we have infima interaction matrix, suprema interaction matrix, dilation distance interaction matrix, and erosion distance interaction matrix. And finally, we computed ranks for all possible pairs. And that is based on this particular unified equation. And then I will show you, these are this DEM here, and I deliberately made it into 4 quadrants, and then quadrant 1, quadrant 2, or F11, F12, F13, F14. And between all possible quadrants, and we computed the ranks. Obviously, the quadrant 2 itself is the rank 1, which is the best pair, and all diagonal values are the best pairs, no doubt in that. And then on the other values, whichever is the highest value is the best pair. And in that way, look at here, and this is the DEM, the 4 quadrants of DEM, and they were shown, and which two quadrants are the best pairs. And that is the idea, and which can be done through, these are the 2 best pairs, and these are the 2 quadrants is the best pair, and this is the worst pair, and so which is based on the transfer pairs of images. And I am not going to go into the details of processing and analysis of digital elevation models, but we have published several books on these ideas, and one can go through it. And this is the book where most of the things that I have explained were there, and this is on mathematical morphology and geomorphology and geographic information science. You can look at here, these are the people who written a wonderful blurbs on that book, recommending it. One of the popular persons, we all know, the ISRI founder, Jacques Dangermond, has written that, wrote that since the initial birthing of computational geography and geographic information science over 50 years ago, The field of geography has been evolving with many contributions for both the academic and research side as well as the application world. I am happy to see the emergence of this particular book. This text further extends our understanding of geographic information science, how fundamental quantitative approaches can extend how we understand geography and our world. And thanks to Waldo Tobler, and there are many other people like Mike Goodchild and Mike Butty, and this is Professor Mike Butty, who is the founder of Center for Advanced Spatial Analysis in University College London. And Sir Alan Wilson was his colleague. And these are the people who know a lot of mathematics and they know a lot of technology. And they have realized the importance of bringing, you say, deep learning or artificial intelligence or mathematics or applied mathematics or computations. It's worth, attacking various problems, challenges available with, geographic research and geography as an academic field, right? So further, if somebody is interested to know about, every small aspect of these morphological operations, and they can go through some of the lectures given at NPTEL style in IIT Kharagpur, and they are here, and they are all available in public domain. And so further, and I would like to just skip on DEM processing and analysis. I will leave these slides probably with Amia, and if he wants, he can post those things for the audience to access and understand. It's not too difficult, and I don't need to really speak, and so this can really help other things like. So with this, probably I will end it. So let me thank IEEE Geoscience and Remote Sensing Society for giving me an opportunity to give DL talks, and to IEEE GRSS Bombay Chapter for hosting this. Thank you very much. If there are any questions, I am more than happy to answer.
Thank you, sir. I have some question. Of course, I think let others ask also. Some audience, some question, something there.
Yes.
Yes, one question is there in the chat box, sir. Shall we apply morphological interpolation method to regenerate missing data in case of hyperspectral remote sensing? So I think you have already explained this.
Yes, actually, we have not tried that, but I have been talking to my PhD students. But there was one article which is early access of IEEE Geoscience and Remote Sensing letters. That is like band selection using dilation distances. If you look at that band selection using dilation distances, which is in early access of IEEE GRSL, I think which should appear. I think our Professor Avik will decide when it should appear. And so which was accepted almost a year, about 7-8 months ago. And there we have given those ideas. What is dilation distance? How we can employ that in hyperspectral image context. But you say missing data, you look at the preceding data, preceding channel data and succeeding channel data, in between which you are telling that some channel is missing. You just try, and I think it should work. And if you want, probably I'll share those corresponding papers which were published in IEEE JSTARS, IEEE TIP, and IEEE TPAMI. These 3 papers would really fetch your interest more to think about. It is not just missing channel, and you have 50 images in the channel hyperspectral image cube, and you want to make it 100. So in successive channel images, you just blindly put one and then see what will happen, or remove alternate images in the cube, and then you generate, and then you find out what is removed, and then what is generated. You find out what is the similarity. Distance wise, if you have close to each other, and I can say that you got some success into employing the interpolations for generating or converting the sparse data into dense data.
Okay, thank you, sir. Any other question from the audience?
I have a little different question, sir. That is that how can a representative interpolation, maybe a contour map of any result or any medium, be prepared?
Which one, Amia? Can you just put the question once again?
How how can a representative interpolation, maybe a contour map of any result for any medium that can be prepared?
So if you, let us say you have, if you look at the topographic map, and mostly the contours, elevation contours are with 20-meter intervals. You see 20, 40, 60, 80, like that you see it.
Yes.
Suppose from the contours, contour map, you want to make it as a kind of digital elevation model. And between 20 and 40, you can create one median line. And between, you say that if it is a non-weighted median, you say that it is probably 30-meter elevation. And then between 20 and 30, you can generate one more interpolation line. You call that as 25. Between 30 and 40, you create one more, generate one more interpolated line. You call that as 35. So the sparse initially 20 and 40 contours, you could generate almost 3 additional interpolated lines, and then you can make it, the very sparse data into dense data. How that can be done is with a simple binary morphological interpolations. With simple binary morphological interpolations, and obviously when we look at our SRTM data, we are allowed to have probably 30-meter resolution data. By removing some spurious information noise, and if you compute the gradient, and you are supposed to get all contour outlines like gradient lines, and then between the successive gradients, if you can interpolate, and perhaps you may make out of 30-meter resolution digital elevation model, you may make 5-meter resolution digital elevation model. But these are all in a discussion sake, and I am putting it. But once somebody gets into that, it's a full-length PhD level problem.
Yes, yes.
Yeah.
Yes.
Yeah.
Thank you, sir. Thank you.
Yes, I think I took exactly the time, right? And
Yeah.
I didn't take more time. I think this is the first time I have been successful in making it into the thing, and every time, and they say 160 minutes. For Brazilian chapter, I took 100 minutes. And they were, later on, I realized in the chat box, they are discussing. Oh, did you tell Professor Sagar it is only 1 hour talk? 1 hour talk and 40 minutes interactive session they have put. I have killed their interactive section, but that is where I am. I have to be very careful and cautious.
Thank you, sir. Thank you.
Yeah, so Deepanvita, yes, she always attends my talks, and thank you, Deepanvita. She said, okay, I'll share all this.
Thank you, sir.
Yeah. Okay. So if there are no further questions, you are just feel free to write to me emails, and then
yes, sir.
Though I'm a bit lazy, and you can always call me, and my number is with Amia.
Yes, sir.
If there is any discussion required. Thank you. Thank you very much for your attention.
Yeah.
Thank you so much, sir. I would like to call upon Lebisha Nadar to present the token of appreciation to Dr. Daya Sagar.
Wow, thank you very much.
Good evening, all. It's my privilege to propose the vote of thanks on behalf of the IEEE GRSS Bombay Chapter and the entire symposium organizing team to acknowledge the contribution of those who have really worked hard to make this session happen. I would like to thank Dr. B.S. Daya Sagar for the time and efforts you took to give us a better understanding in geospatial intelligence and mathematical morphology. The way you put forth your explanations in simple words and the diagrammatic representations in each phase helped us understand things in a better way. I'm very confident our audience here have gained a lot from your insights. Thank you, everyone, for being a part of this session.
Thank you, Lebisha.
Thank you.
Thank you.
So shall we move on to the next session?
Yes, please.
Okay. So we now have our last talk for the day on the topic deep learning for airborne LiDAR point cloud analysis for remote sensing. The talk is by Dr. Jaya Nair from IIIT Bangalore. I would like to invite Dr. Firoz Sheikh, Associate Professor DBIT Mumbai, to introduce our speaker.
Yes, thank you. Thank you all. It's my privilege to introduce Dr. Jaya Nair for this title, Deep Learning for Airborne LiDAR Point Cloud Analysis for Remote Sensing Speaker's Biography. So Dr. Jaya Nair is currently a faculty member at the International Institute of Information Technology, Bangalore. She leads the Graphics Visualization Computing Lab and is one of the core team members of the eHealth Research Center at IIITB. Jaya has research interest in data visualization, scientific computing, computer graphics, and computational topology. She works on modeling data for effective visualization and identifying appropriate visualizations for complex data sets in data science workflows. She focuses on the data modeling using second order tensors, matrices, and networks for varied applications. Some of her recent work includes uncertainty analysis of the semantic classification of LiDAR point cloud, spatial and statistical analysis of population surveys, automated data extraction from chart images, and community detection in biological and brain automated data extraction from brain networks. Her work has been supported by grants from SERB, DST, GOK, Intel, IBM, to name a few. She is an STM member and IEEE member. Jaya is currently serving as an associate editor of IEEE on circuits and systems for video technology and the chair of the IEEE GRSS Bangalore section stage. Prior to joining IIIT Bangalore, she had worked as a scientific programmer at Endbot Incorporation, Austin, and as a research associate at Texas Advanced Computing Center, the University of Texas at Austin. Jaya has obtained her PhD in computer science from the University of California, Davis, after a BTech from IIT Madras and a MS from Mississippi State University. So now I invite Dr. Jaya Nair for her talk on the state title. Over to you, Dr. Jaya Nair, madam.
Okay, thank you so much for the introduction, Dr. Feroz, and thank you, Dr. Amia, for inviting me for this session. So I'm very happy to be here, and I understand all of you are like totally exhausted after 2 days long of worth of the symposium. So I'll try to keep my talk as interesting as possible and as short as possible as well. So I'm hoping I'm audible, and if I have network
Yes.
issues, please let
No,
me know.
you're audible fully. Yeah, very clear.
Okay, thank you so much. So I will just share my screen.
Yes.
It's actually a little bit intimidating or scary to follow after a giant like Professor Daya Sagar, but I will try to do my best with what I know. Okay, so this talk is on deep learning for airborne LiDAR point cloud analysis for remote sensing. Okay, so I will put out a disclaimer first. So a lot of our work has been in airborne LiDAR point cloud analysis, primarily for semantic classification. And deep learning is something that we are going to explore. So this is a study that we made towards how deep learning can be used. So these are my observations and findings. A lot of the work that we did in semantic classification, I will talk about, and how that leads to the deep learning aspect, I will talk about it. So without much ado, I will just start the talk. So the scope of the talk is primarily to check if we look at these modern techniques like machine learning, deep learning, some of it has, some of them have been very widely used for point cloud processing. So then the natural question, a very organic question to ask is, why not for airborne LiDAR? This is a quest to seeing how much of it is applicable to airborne LiDAR and what works and what does not work. So that is the idea here. So let me uh, go on to first explaining what airborne LiDAR point clouds are, because that is not something which everybody understands. It's not as popular as maybe SAR technology or hyperspectral satellite imaging technology, even for the geo technologists. So geospatial scientists. So I will talk about what airborne LiDAR point clouds are. In general, point clouds, when we talk about the bare minimum information that we have or the data that we have, is for every point that is used to represent the data of a geographical region, that point will have its positional coordinates. That's the XYZ coordinates. Now that's as simple as that. Most times for LiDAR point clouds, we will also have the intensity of the light that has been reflected by that particular point or the material that the point belongs to, right? So this is how the point cloud looks like. This looks like a painting, but this is not a painting. This is like we have, drawn or rendered using computer graphics and visualization every point in the point cloud, which has this XYZ coordinates. And additionally, this has been colored using the class information, as in, so there are classes as these red points are buildings and the green points are vegetation, the blue is road, and so on and so forth, right? So this particular data set is fairly big. So this is a Dales data set which was released in 2020. And this is a Canadian city, and that's a city of Surrey. And this data set was acquired by University of Ohio, Dayton, right? So this is a fairly large annotated point cloud that we have. So this is to just give you a gist of what this is all about. So the point cloud, the point density itself is 20 points per meter square. There are 8 semantic classes. When we say semantic classes, they just mean object classes. There are buildings, there are roads, there is low vegetation, poles, etc. Right? Now, this was an annotated data which was used for supervised learning. So there is there has been specifications for that as well. Okay, so just to talk about what airborne LiDAR itself is, the idea is that the LiDAR, that is the light detection and ranging sensor that we have, similar to radar sensor, right? What we have here is that sensor will emit light, which is essentially the laser beams, and when they are incident on an object in its path, it gets reflected. So it's simple optics there, and once it gets reflected, the time that the light beam, the laser beam, takes to come back to the receiver in the instrument is what is recorded, and that tells us the altitude of that particular point. So this is it. So the complexities are in how much, how one would design the flight path for the airplane. It has to be a low flying airplane. The weather has to be clear, etc. All of that has to work out for LiDAR to get good quality, to give good quality data sets. Now, of course, because it's geospatial data set, there is GPS involved to give us the appropriate latitude, longitude information, right? So this is how a point cloud would look. And what we really want to do is it's just a set of points, and it will just look like a dotted image. And what we want to do is really to make more sense of that data, right? So this is a colored point cloud. The color is based on whatever it is the classification. So this is particularly, usually the LiDAR point clouds, you would see this kind of coloring to indicate the height. Okay? Now, these are again other snapshots of how the point cloud itself would look. This is the input data with just the positional coordinates and the intensity with which the light returns back, right? So based on the material and its reflectance properties, you can sort of infer if it is an asphalt surface or a stainless steel surface or it's glass surface or it's organic surface like leaf and tree and all of that, right? So that we get some kind of information about the material properties of the point that has been visited by this laser beam or intersected by this laser beam, right? And this is what we usually have for the data set, and this is what we really want. Now, you must have also heard LiDAR in other contexts, right? So this is a terrestrial LiDAR data. Again, a point cloud. All of these are point clouds, right? This terrestrial LiDAR is not obtained from a low-flying aircraft. It is a terrestrially obtained data. So we have a vehicle that is carrying a LiDAR sensor, and it scans the objects on the floor, on the ground, right? So that is essentially a terrestrial LiDAR. Now, a lot of the computer vision related problems are coming from autonomous vehicle, autonomous driving. And these data sets are collected from a LiDAR that is installed in a autonomous vehicle, and that autonomous or driving, right? Driven vehicle, right? Now the reason and the if you can see the differences in the data set here, the data is from a LiDAR sensor that is rotating, and it does 360 degrees view of around the car because that is the requirement there, right? And we get this kind of data. So you see these circular patterns that just indicates that it has rotated and taken that many sample points and all of that. So these are actually sampling artifacts. You don't see these artifacts when you look at the airborne or the terrestrial LiDAR point cloud. Okay, so now quickly shifting to what we do with the airborne LiDAR point clouds. So we take the point clouds, we do a whole bunch of neighborhood selection. This is mainly for I'll mention what neighborhood selection itself is. And then this is from these information that we have from the input data and the neighborhood information that we gather, we extract a lot of features. We select a whole bunch of features, and then this runs into a supervised classifier like random forest classifier, etc. And depending on what this feature set has, we can run as many different classifiers as we want. And then we get the label 3D point cloud. And so this is a paper by Weinman and others in 2015, where they did an extensive experimental framework to figure out for ALS and TLS data point clouds, what are the kind of features that work the best for doing a very highly accurate supervised classification. So through this talk, I will not give you numbers in terms of accuracy and IOU and all of that, because here I just want to give you the gist of what it entails in terms of the semantic classification. So I'm going to talk more about the process, not really so much about the results. So the idea here is that this process is a well-established, well-oiled machinery, and a lot of people are working on this, and this gives very good results. So the random forest classifier has been the standard classifier that is used for this kind of classification, right? So let's look at why we need this neighborhood selection and all of that. So this is a spatial data set, and what we really want to do is we want to capture the spatial locality, as in, okay, I'm a point here. What are my neighboring points doing? Are they part of the same object that I am, or are they part of other objects? Right. So essentially, that information about the segmentation and the classification comes from where I am with respect to my neighborhood. So the spatial locality gives this information, and this information is fed in the form of say a number, a value, and it's fed in as a feature into the classifier, right? So most of these methodologies involve capturing local features. The idea is to preserve the spatial locality and use local neighborhood. We also capture height features because the primary task of many of these kind of analysis is to first figure out ground points, filter out ground points, and then figure out the non-ground points, etc. And for identifying ground points, the best feature is height features, as in the height itself will give you very good classification on whether it's a ground point or a non-ground point. Now, for classification, we have regularly used random forest classifier, and neural networks is something that has found its way through this now. So we will talk about this part towards the later half of the talk. The unsupervised classifiers, there have been use cases of k-means, expectation maximization, but more or less, if you look at most of the literature, random forest classifier is a clear winner, right? That is what is used. Now, let's look at what the local neighborhood is what I'm talking about, right? So what is that we want from the local neighborhood? So we want that if a point is surrounded by a whole set of points, those are its neighboring points, we want to first look at the shape of that local neighborhood. Now, the shape of the local neighborhood has two aspects. One is the neighborhood search. So who qualifies as a neighbor, right? So you want to find that out first. So for that, we use different kinds of neighborhood shapes and criteria, right? So here, if you look at, this is a spherical neighborhood, right? Now, we take a whole bunch of points which fall into that criterion of, say, a radius above from that particular concerned point that we are trying to compute the features for. Now, once we have this, these neighbors themselves don't really occupy the entire sphere that we use for the search. They form a shape of its own. So the idea is to identify the shape. Now, what is this information that we get from the shape? The shape will tell us if this point is going to lie on an edge here like this, or is it going to be a junction point, or is it going to be a surface point? Now, the question is, why is that important? So the reason why it's important is the composition of these line, surface, and point type, or this junction type features is going to tell me what object that point is going to belong to. So that is why it is a very good differentiating feature characteristic that can be used for the classifier. So that's the reason why this has been traditionally used. So the idea here is we need to figure out the shape of this neighborhood, right? Now, to figuring out the shape of the neighborhood, what we do is we compute this thing called a local geometric descriptor, which I'll describe in a little bit. And then it's actually a matrix, and that matrix we do eigenvalue decomposition, just like you do principal component analysis. It's the same thing. And the major and the minor, the major, middle, and the minor eigenvectors and eigenvalues, not so much the eigenvectors, the eigenvalues are going to tell us what the shape is. So if it is elongated, as in the major eigenvalue is much higher than all the other eigenvalues, we get it to be like a tubular structure. So it forms, it is on the boundaries. And if it is flat, as in the first two eigenvalues are comparable, and the last eigenvalue, the minor eigenvalue, is very small, then it's a surface thing. And if all of them are equal, then it is a spherical thing. And so it's a junction point. Now, what we do here is we find this thing called the covariance matrix. So covariance matrix just takes the variance of the variance and covariance of the XYZ coordinate values of the neighbors. So it's basically a statistical descriptor. And we form this matrix. And this matrix then tells us how a point is away from all the other points in that neighborhood. And once we do the eigenvalue analysis, it essentially gives us the shape of this neighborhood. So this is a covariance matrix. This can be substituted using tensor voting. It can be substituted using several other kinds of tensors that we can think about in this particular case. Right. So before we go any further, I want to give an impression of what space and time, how they feature in this. So the thing is, when we look at these LiDAR point clouds in the airborne LiDAR point clouds, the point side, the regions that they're capturing are very large, right? So they come under this region. So this is the spatial scale is very large. Now, if you look at the time scale is very small because you capture the data within that one particular, say, a few hours or something that you want to fly the aircraft and get that, right? So the thing is, we can then do the analysis as a single timestamp, as in we say that this the entire point cloud has been captured in a single timestamp. So we do only spatial analysis then. There is no temporal analysis, even though I took 2 hours to capture the data or 5 hours to capture the data, it doesn't matter because the time scale is much, much smaller than the spatial scale. Right? Now, if the spatial scale and the temporal scale are comparable, like for instance, the vehicle LiDAR, then we do other kinds of analysis. So we have to take into account the temporal aspect of the data as well. So as far as airborne LiDAR point clouds are concerned, we don't take the temporal aspects unless it is like a timestamp. Say I take it in this year, then I take the point cloud after 5 years and then try to compare those point clouds. That's a different question altogether. But in a single shot, when the data is acquired, the time doesn't have much influence on the data because the scale of time that is involved is much, much smaller compared to the scale of space. Right? Now, this is essentially an image to show that depending on the spatio-temporal aspects of the data set, we have different techniques for capturing data. So if you want to, it's essentially if the information is at a microscopic level or a macroscopic level, how do you capture data? So the data here is essentially at a macroscopic scale, right? As far as space is concerned, and it's a microscopic scale if it is time is concerned. Okay, so this scale is important for us to understand that that is the scale at which the data has to be collected. But what we are saying here is there is a physical spatial scale involved here. So what the information that you get from the local neighborhood, depending on the size of the local neighborhood, the information that it will give will be very different. Right? And for different points in the point clouds, we want to employ different scales because for a corner, I want very small radius. For a surface like a road, if it's a very large radius also, it doesn't matter because I get the same information. If the information is homogeneous across so many different neighbors, right? So what we generally do in this kind of analysis is because we are unable to figure out what is the physical scale in which we need to extract this information from, we take multiple scales. We take multiple neighborhood sizes and then we combine the data together, right? So in terms of the types of neighborhood, we use cylindrical neighborhood, where it just means that you take the circle and then all through the height, you take the neighbors. This is K nearest neighborhood, which is also very widely used. So this is how it's done in machine learning. And radial neighborhood is you give a radius as a constraint, and all the points that is within that radius are neighbors. So one thing I wanted to say here is the type of the neighborhood is decided based on the application that we are trying to use, and also the amount of computation that is required for searching for the neighbors, right? So that those two decide what kind of neighborhood you would end up using. Okay, so one way of combining these scales is something that has been widely used in airborne LiDAR point cloud analysis, is to find something called the optimal scale. Now, optimal scale is where when we measure information theoretical metric, right? That is the Shannon entropy at that point. If it is minimum, what that means is it is at a stable state and I can figure out what kind of shape of the neighborhood I can get. And that optimal scale is what I would then use for figuring out I would take the features at that optimal scale and run it into my in my random forest classifier or whatever. So that's one way of combining scales. Another way is you can average across different scales if that feature is something that you can average across the scales, right? So in general, you can then extract all these features. And what is generally done is we have used it for geometric classification, as in to figure out if it's a line type, point type, surface type features, and that has further been used in the semantic classification. So that is where we are at, right? So the feature extraction is completely related to semantic classification. Now I'll switch gears and go to the general point cloud processing, right? And what point-based deep learning is for. Now, if you look at point clouds in general, there are two types of point clouds. There are several types of point clouds, but there are two main ones. One is the laser scanned objects that you see, say, in the indoors or just a single object or an indoor scene, etc. right? And then there are these geographical regions which are scanned at large, right? So these are, again, the thing is, these are all again sets of points. They define a surface if you look at it geometrically and all of that. But the idea is there are salient characteristics which are very different from each of these data acquisition point of view. So if you look at this laser scanned objects, essentially the laser has the sensor has to move around the object, or the object has to be rotating to capture all aspects of the data, the entire view of the data, right, of the object. So it is a multi-view point cloud, but this on the other hand is a single view point cloud. Right, and depending on the kind of laser sensor that is used, you can have different kinds of point density. Typically, the airborne LiDAR scanners have very high point density compared to TLS and vehicle LiDAR and all of that. Okay? So we talked about this local neighborhood thing and all of that, right? So the other thing, so there are other ways in which this information is captured. So one way is to capture this thing called the surface variation. So without doing too many things, we can just capture that major eigenvalue. And this is used for finding these kind of feature lines in the objects. So you can see the salient difference when we look at the point clouds, which are for the airborne LiDAR, we are using that for semantic classification, semantic segmentation, ground point filtering. But if you look at the objects like this, which are computer graphics or just geometry based objects, what we are doing here is finding feature lines so that we find characteristic silhouettes of the object for doing computer graphics and all of that, right? Now, again, these use similar principles. We are again looking at the entropy values for finding all these things. So the concept is very similar everywhere, right? So these are the edge detection that we want to do for sketching, or we want to do for rendering using computer graphics algorithms and all of that. If you look at the TLS dataset, there are also applications where instead of just finding this optimal scale, you can add all these features together, form a very long vector, and then just run that into a random forest classifier or a CNN. That also has been done, right? So what I'm getting towards is, depending on the kind of the data set that we are using, the kind of the analysis also is very different when we look at point clouds itself. So the point cloud, if you look at a very 10,000 feet view, it has different types involved. So one is like it's a single point cloud, a single view point cloud, or a multi-view point cloud. And based on the point density, you will have different kinds of characteristics. Based on if it is a spatio-temporal attributes have to be included, the kind of analysis has to be different. And specifically the source, right? So some of these are from computer vision related applications where we look at structure from motion techniques, LiDAR, 3D scanners, sensors like Kinect, and all of that. So these are again different kinds of point clouds that we get. Even though they are all effectively, they are all categorized as point clouds, the kind of processing that has to be done is very different. And usually the challenges that are involved are trying to infer the spatial structure from the point cloud, which is implicitly encoded, right? So like I said, for us, even in the airborne LiDAR, we had to find the shape of the local neighborhood, find the shape of the local neighborhood using eigenvalue analysis, etc. Right? So it's not straightforward. I mean, as in you don't look at the point cloud and you just get that information. That has to be extracted through tedious computational techniques. Then point clouds themselves have issues with sparsity. Some have a lot of noise. Some have outliers. So all of these are regular issues that you find with datasets. In point clouds also, depending on the kind of acquisition that is done, this also features. Then the other aspect is, if you have time varying data set, like for the vehicle LiDAR, that the LiDAR sensor is rotating as the vehicle is moving. So time also has to get captured there, right? And multi-view data. So that is also a good example of the vehicle LiDAR is a good example of capturing data from multi-view as well. So the traditional machine learning that we just talked about for airborne LiDAR also is that we first take the input, do the feature engineering, feature extraction, then classification, and then we get a classification output, right? But what deep learning does is we skip this, we combine these two and sort of transfer that responsibility to the learning model to finding the features themselves and then extracting the outcome, right? So the real benefit of using deep learning really is about this feature extraction part, right? So the feature extraction part is non-trivial when you're dealing with billions of points in a point cloud, and it is non-trivial when you're dealing with like these kind of different spatial scales and temporal scales and all of that. Then feature extraction becomes a very messy affair. So deep learning is somewhat neat in that sense, but again, deep learning comes with this caveats that training models for deep learning is not very trivial, right? It requires a lot of computing resources. So, so where can we use these modern deep learning techniques in point cloud analysis? So one is to find a representation of high information density from a sparse point cloud. So usually it involves densification of point cloud and all of that, which has to be, which would have been traditionally done separately and then feature extraction on top of it and all of that. Here it can be done in a very neat manner. How to build a network satisfying necessary restrictions like size variance, permutation invariance, etc. So this is with respect to the neural network that we would be using for deep learning. And the last part is how to process large volumes of data with lower time and computing resource consumption. As I mentioned, point clouds are not, they are not 10,000 of size, right? It is usually millions or billions of points that describe geographical regions. Now, so deep learning is not new for point cloud analysis. This is sort of the laundry list of the taxonomy of all the methods that are used for deep learning. So just to look at the first cut, what it's used for, it's used for 3D shape classification, 3D object detection and tracking, and 3D point cloud segmentation. Now, when it comes to airborne LiDAR, none of these matter. 3D shape classification doesn't matter. 3D object detection and tracking doesn't matter. We purely look at 3D point cloud segmentation, which includes ground point filtering, semantic segmentation, all of that, right? Now, if you look at this one, this is showing the chronology of how the deep learning in point cloud processing itself has been worked on. So it started around 2015 and it's still going on, right? So one of this, which is the point net, is something that sort of was very successful. And there are a lot of work done on top of point net, which is point net plus plus, etc. And a lot of these are variants on point net where certain other characteristics have been included to support the data itself, right? So this is what we have in general for the deep learning solution. So this is all good stuff. So then the natural thought process is that, okay, if this is out there, then I should be able to use this for airborne LiDAR, right? But that is not true, is what we will learn soon, right? So for airborne LiDAR, what we see is that the application we require, this is for ground point filtering and semantic classification, right? So I would bucket them together, but ground point filtering is a salient task in itself. So that's why it's put separately. Now, the traditional methods are we use handcrafted features, we require multiple scales or hierarchical properties. This hierarchical properties is for the neighborhood search, right? So if I have to find neighbors, then I need to use hierarchical data structures like KDDs and octrees and all of that, KD trees and octrees, which will allow me to search efficiently, right? So those are some of the things that are required. And the focus is on minimizing commission errors. Now, commission errors are essentially false positives, right? So what it's a type 1 error. So the idea here is that we are saying that the points which are not, ground points are classified as ground points, right? So those are commission errors. This is different from omission errors. Omission errors are false negatives and type 2 errors, where the idea is that we omit finding the positive. So those are false negatives. So the requirements from computer vision applications is very different from the requirements from ALS point cloud, which we already saw. Because for computer vision applications, we look at 3D shape classification, object detection, object tracking, etc. When you look at it from the point of view of airborne LiDAR point clouds, specifically for classification, we don't need those things. We are just focusing on segmentation. So one disclaimer again I would say here is, of course, we can do object detection in airborne LiDAR point clouds also. There is, say, for example, Professor Ramanathan from IIT Madras, his lab looks at, say, roof classification, right? So looking at just roof as objects in ALS point clouds and being able to use deep learning solutions for that, right? So then it is about crafting that problem to suit what is already there in computer vision related application, right? Now, the two primary learning problems in computer vision are 3D point cloud recognition and segmentation. Okay? Now, so if that is the requirement, this is how really its workflow looks like. When we look at the data analysis, there are all of these different processes that are involved in analyzing that sort of data, right? So there is sensing, which is the acquisition, there's localization, perception, map creation, prediction, planning, etc. Right? Now you see that this is very, very different from the workflow that we had for the airborne LiDAR point cloud analysis when we looked at for semantic classification, right? So this is for autonomous driving. These are the requirements, and the representations are also different, because the representation here is for the 360-degree view. So the data can be either represented as 3D voxel based representation, or there can be a range view, which is based on the 360-degree view, and there can be a bird's eye view. So if you look at it from the point of view of ALS point clouds, only 3D voxel representation and bird's eye view makes sense. There is no range view that can be generated for ALS because it's a single view data set. Now, so if we look at it from this point, we already see that the requirements and the characteristics of airborne LiDAR dataset are very, very far from, not too far, but they are different from what we see for, say, the vehicle LiDAR datasets or for the general computer vision geometry related datasets. So the challenges of applying deep learning in these airborne LiDAR point clouds is that the accuracy differs. The accuracy of the classification begins to differ when we use it in different environments, because these are naturally occurring environments. We see that there are differences in the accuracy. So what it comes to is generalizations are very difficult, right? So this is not to say that if the vehicle is moving in, say, a forested region versus a urban or a rural region, the data is going to be different, and the way deep learning would work for vehicle LiDAR is not going to be challenging. That's not the case. What we are saying here is, even if we just apply the deep learning solution, the same thing that works for urban data set, and then we apply it for say, for a forested region, there have been studies which showed that the kind of errors that you find in the accuracies itself is very different. So for example, in urban data sets, the kind of errors that you see is the commission errors, that is false positives. And the kind of errors that generally are observed in forest area data sets is omission errors, that is, you miss out on the points that are actually pertaining to ground or whatever, right? Now, the spatial locality is not captured very much. So as I mentioned, PointNet is one of the very successful neural network that has been generated for point cloud processing, 3D point cloud processing, right? Now, the thing with PointNet networks is that it does not capture spatial locality the way it has to be captured for the airborne LiDAR dataset, given that there is a lot of dependency on the spatial scale alone in the airborne LiDAR dataset. It does not do enough justice to the requirement of the dataset itself. So what then it comes down to is there is a trade-off between, so you can use PointNet, right? It is not that you cannot use PointNet on ALS, But the thing is, it will give you reduced accuracies. It will give you reduced computation, but it will the reduced accuracy is from missing relevant features because the spatial features don't get captured as well. Then the other one is the representation of multi-view point clouds cannot be imposed on the aerial LiDAR point cloud. So I'll show you some of the success stories in deep learning in ALS point cloud processing. So for ground point filtering, the point cloud, the point net has been improvised to using a point-based fully convolutional neural network. Now there are a few things that were added. So one is the spatial transformer network and these other things, right? So one of the key aspects that I want to bring out here is this particular model was fashioned to use the spatial locality as well. So they incorporated that by using tile-wise features. So this is not alone just using the point-wise features, but it also used tile-wise features. And the idea is that this, so the tile-wise features are different from the spatial neighborhood, local neighborhoods that we talked about, because tile-wise is a representation of an entire small region of points. But if you look at the local neighborhoods, it was a property of each point. But so what we are getting towards is this doesn't solve the problem as much as what the traditional methods used to do, but it gets closer where it also captures the spatial locality aspect. Right? So, so the next one that I wanted to mention is about semantic segmentation, where graph attention is used. So this is the same Bahingen data set that ISPRS benchmark data from Germany that has been, that I had shown earlier as well in a previous slide. Now, this is the result of the segmentation that has been gotten out of using the deep learning method. And here, the key aspect is to use graph attention, right? Now, the specific aspect of the graph attention that they use here is to use KNN graph. KNN graph is essentially the K nearest neighbor graph that is generated, and that graph is used as also as an input to improve on the spatial locality information, right? And apart from that, there are attention modules that are included. So there are global and local attention modules, which also decently capture this spatial locality requirement. So again, so I'll end my talk. I shortened it quite a bit to meet the time requirements that Amia had mentioned. So I'll just conclude saying that this, the whole idea to imply here was to say that when we do this kind of analysis, or when we are generalizing deep learning analysis from, say, a wider category of point cloud processing to a specific application in airborne LiDAR scanning, the reasons why it doesn't work is because there is a complete mismatch of the point cloud characteristics themselves. Then the idea is to understand how it works now with the traditional machine learning process and to incorporate those characteristics of feature extraction in what we see in deep learning, and that gives us much better results. So if you look for deep learning in airborne LiDAR, it is way more recent, like in 2019, 2020, when people have started successfully using deep learning in airborne LiDAR point clouds. Again, with airborne LiDAR point clouds, the problem is also, as any other point cloud, annotation is a big problem, which has to be sort of still solved, and which has to be done because that is the only way to checking if these models work correctly or not, until we get a good enough model which we can sort of very confidently apply on any data set that comes our way, right? So this is sort of the thing that I wanted to present today. And I would like to acknowledge the funding that we have gotten for doing this kind of work since 2012. So we have been generously funded by DST, SERB. Recently, we also got the Intel India Research Fellowship to working on the vehicle LiDAR dataset, which sort of gave us this full view of how these different LiDAR point clouds can be processed and worked with. These are my students who worked on these projects. So Veena, Satendra, Akshay, Pragya, and Dwani. So I would like to thank you for your attention, and I'm again grateful to IEEE GRSS Mumbai chapter for inviting me for this talk and presenting my views on this. So yeah, I'll be happy to take questions. Thank you.
Ma'am, I have a question. See, when we talk about our drone technology nowadays, and then the different type of sensors and leaders, then of course drone technology has its own drawbacks also there as of now, though technological is growing also. But how do you see that one, that the leader and drone that is going simultaneously?
Right. So if you look at, so again, this is an interesting question. So a lot of the airborne LiDAR point clouds, if you look at the data acquisition aspect, I have my good friend Gurudatta here as well. He could also attest to that, that the data acquisition costs are very high when it has to be done using the airborne techniques that are these low flying aircrafts and all of that. So drone does bring down the cost quite a bit, but the aspect of drone is that the scale, the spatial scale that it is covering is much, smaller compared to what the aircraft would have covered. So what then happens is the kind of data that you get has a lot more of noise and outliers, and then the techniques that you have to use have to account for these things, right? So have to account for the noise in the data, right? Which is not as much if you look at the airborne LiDAR, right? And I think if I'm not wrong, the point densities are also very different. So for drone technology, I think the point density is going to be lesser than that of the airborne LiDAR, if I'm not wrong. But yeah, I'm not, I haven't studied that enough to make a confident comment on that. But yeah, so this is what
I think this Gurudatta has answered probably. The drone flies for a shorter time, and the weight of the radar sensor further decrease the flight time. That's true. That was the really challenging thing as far as viable solution.
But yeah, that's it. There is a benchmark data set that has been released in 2021 by the same lab, the group that has released the ISPRS benchmark data for airborne LiDAR point clouds as well. And they released that in 2015. So by 2021, they have released a data set that has been captured using drones, which is a very large scale data. Again, I don't know the exact area that has been covered and all of that. The other aspect is they have also released data set for the surface mesh that can be generated from those point clouds as well. So they have actually released a data set which is of a lot of good value for the community to work on. Yeah, so that is something that we are also looking forward to working with that particular data set to understand. So again, most of these it's a hard way to learn that depending on the data set. I mean, the thing is, once you say that you've cracked a very difficult technique for one point cloud, you have this thing that, okay, now I'll just apply it on everything else that comes my way. It's like you have that proverbial hammer and you would see everything as a nail, right? But the hard truth is that not everything is a nail then. So one size does not fit all, right? So each of it has to be done separately. So, yeah.
And there are very few people who work on the LiDAR, obviously, it's India and abroad also. So there is also another point of thing. I think maybe you are, I know very few people only, as far my knowledge is concerned, works on LiDAR, yeah.
Yeah, so Professor Bharat Lohani from IIT Kanpur and his set of PhD students continue to work on a whole lot of LiDAR applications. Professor Ramarao from IIST works on LiDAR. So yeah, so the collection of people in academia who work in LiDAR is still very few. And like I mentioned, Professor Ramanathan from IIT Madras also works on. So if I look at it from that point of view, so the good part is it's something that everybody can work on. I mean, I think that is true for all the things that you would have talked about in the symposium, right? So for example, if you see the kind of point of view I have is purely from computer science, data visualization, graphics, geometry point of view. And Professor Ramanathan also has that. But if you look at Professor Ramarao's or Bharat Lohani's points of view, they would look at it more from the civil engineering, surveying point of view, right? And the kind of analysis you get is somewhat different. I mean, the kind of emphasis you would pay for the kind of techniques you would use would be different.
Yes. Okay.
So
very nice talk, madam. Actually, so many insights were there. So probably we have a shortage of time. That's why we have less, duration that I talked. Otherwise, maybe I think you are giving a talk, another talk in our next coming week also. And there's another program that's in GRSS Mumbai is doing. That's in the computational intelligence. Probably I will listen to more on that also for you. In fact, from Professor Daya Sagar also there. Of course, I will listen to more on that. What you people are trying to say. Yeah. Thank you very much, ma'am.
Thank you so much. Yeah.
Thank you so much, ma'am. Now I would like to call upon Ms. Levisha Nadar for giving the vote of thanks.
I'm privileged to propose the vote of thanks on behalf of the IEEE GRSS Bombay Chapter and the entire symposium organizing team to acknowledge the contribution of those who have really worked hard to make this session happen. I would like to thank Dr. Jaya Nayak for the time and efforts you took to give us a better understanding in deep learning for airborne lidar point cloud analysis. The diagrammatic representations of each phase helped us understand things in a better way. I'm sure our audience here have gained a lot from your insights. Thank you everyone for being a part of this session.
Thank you.
Thank you, Levisha. So we are now moving forward with our concluding session for today.
Yeah.
I would like to invite Dr. Amya Kumar Tripathi to brief the audience.
1 minute to wait for. I'll just ask whether Abhik sir will join. Let me just give me 2 minutes. I'll just call him so that if not, then we could proceed.
Okay, sir.
Yes, actually, Professor Abhik sir a little bit, not health-wise not okay. So hence, he said that when you carry on. So we'll proceed our further proceeding for that one, right? So we have started this program. This is Geospatial Intelligence with our team members. I mean, like our Professor Sangeeta Madam, Professor Sanjay Thole, today he is not there, and Professor our Sangeeta Mishra, Professor Safiuddin Saib, and Professor Ujjwala. All these we have started and teamed up, to carry out, particularly on the. Of course, most of us in computer science background, and some of us also in the physics background also, right? Professor Safiuddin is in physics background, right? And so we teamed up to do something on this, and then this proposal came in, whether we can apply for such kind of things over there, right? So somehow we have proposed, and this also been granted also, but and then we thought that one, let's have a joint together with the other chapters also. So hence we have a thing with our Kolkata chapter, because they have more experience on them. That's what I feel also. So hence we have a understanding of both, that both will join, do something on that. Right. So initially I was saying that this will become first, later on Kolkata chapter will do something, but somehow it has not managed at our level, because we have a different kind of situation and geography with respect to our Mumbai surrounding is concerned over there. Though it's online, but actually we have applied for an offline program. All these were applied for a more on offline when it has been applied over there. But somehow the situation in Mumbai and all things were not going so good. In fact, so because of the corona and all things are there, so we have getting delayed, and then the Kolkata chapter has started, and then they have done the work with joint work with the Mumbai chapter also. Then later on we have also a little bit lagging behind that, when to do, not to do, all thing, and in little bit hot and push, and then we have somehow we agreed to do in a quick. Of course, we got a green signal from our higher authorities, also from the the other chapters. So hence that we started within a couple of not a weeks, within a couple of days we started thinking on this, and we tried to contact with our professional network and personal network and fix this, and somewhere agreed, somewhere not agreed, and that way even if I asked the Professor Daya Sagar also very quickly, he agreed so quickly also, but on my first call itself. And similarly, sometimes it happened like this way also, right? So we started the program, and we have calculated how can we do this one, but anyhow we started. So we have done variety of programs, like from the industry point of view, from the students point of view, as well as different speakers from different domain, particularly for the geospatial application, and of course AI part. Obviously we've taken into account a bit of more on that. So we have taken into account, because ultimately the aim it is to make the audience or the participant or to aware of certain things that we have been particularly in this area. In fact, when we look at many universities and all things, this program is particularly geospatial, remote sensing and GIS is not even put up by Mumbai University and all things. There are very few colleges we have such kind of programs where there. So somewhere we feel that when we have, this is what we have to take it up and let people aware of that such kind of things are there, that there could be good amount of research, good amounts of funding, good amount of career can be there also in this case. That's what we started for such kind of things over there. And moreover, we have carried out in the 2 days program with the speakers, well-known speakers, obviously from different corners, and agreed and to carry and given the time to this one, including the panel discussion. Also, there is a good panel discussion from different people from different background also were taken out. And it was, I feel, I mean, in fact, though many more things I learned, but still there are many more things to learn, that I feel that when this knowledge is still, infinite for, and then for everybody, it should be same also, that we have a so-called the lifelong learning. When we talk about everything we learn, and when we talk about such kind of thing, everything is connected to everything. That's what we talk about nowadays over there. So that is what the things about. But behind the scene, we have, many of my colleagues, many of my students, many of my chapter members behind the scene. They were working since couple of days, and that's what this they became the reality, right? And that's what we're talking about. And we have also, as I said, that when we have for the student point of view, we have some ongoing works also given some so hence different people, and of course those are the recommendation based, of course. That was not, we have not taken any kind of thing. So the recommendation based some projects where we have asked a few people to showcase their activities, what they are doing in this area, and that's what we have. And our judges, honorable judges, that is Professor Ujjwala from from the Thermal Science College, and of course he's IIT alumnus, and also Dr. Prakash, also again IIT alumnus, right? The both are done PhD under Professor Drupasa. They were ready to in quick sort of time, and then they have able to judge this one, and that's what the thing has been carried out, right? And that's what I say as of now we have done. And we have also given this is as a free, because it's a sponsored program. So that's what we have not asking anybody to anything of things from any participants. And the participant from different regions from India, across India, as well as from abroad also. I have seen also many of the people who are interesting. They are listening to our speakers. And I would like to thank you very much to them to essentially, they have listened to many of these programs over there. And the certificates, what we say that when the certificate, like there are variety of certificate we are going to provide them participation, and then the winning certificate, like from the presentation, as well as the what is called the volunteer certificate also. Grejo, could you like to show a glimpse of it, though we cannot show everything over there? Grejo, okay. Yeah. Just glimpse of this few of things you can show.
This would be the participation certificate for all the participants of the symposium.
Yes.
Here.
Next. Anything next? You could something like that? Anything?
Yes,
So 1 second. It's not changing.
Not changing.
1 second, sir.
Yeah, quickly make it. Okay, leave it. That we understand that. Okay, leave it. Okay, we'll see. Yeah. So as rightly pointed out by Professor Paul Rosen, that the another initiative that we have taken for the regional language, where we want to carry it to the K-12, that means the high school students, to make aware of such kind of things, so that when they will come up and they will really look into differently this kind of the geosocial technologies. That is what we want to make it with a regional language. How can you do? The pilot project we have started last time. Last time means obviously in this year itself only, around the online mode. But we will take it a little further so that it will reach to the interior part of it. That's what we would like to next task is that. And the next what other program I'm trying to say, prior to this program we had also from Bombay chapter, and we have also one mapathon. Mapathon has been taken care by Dr. Sangeeta Mishra at MIT University. It was a very good program also, particularly it was concentrating more on the GIS based one, and more hands-on, and as well as the very interesting people have joined with that program. The upcoming program we have also with the computational intelligence by Dr. Sangeeta Chaudhary from, and that is also again a good program. Is a very interesting speakers were coming up that way. So Bombay chapter is trying to provide a lot of activities to educate the different section of people, so that this kind of knowledge can be spread, and working together, join together, and working from the what is called our the working together collaborative work. We are promoting such kind of thing. Even next also promoting for the intensive programs for the from this chapter also we are going to make it, and that's why we want to carry it further for this Bombay chapter is concerned. However, as I said, we have our guest Professor Daya Sagar, who is the pioneer and is well-known person in across India and abroad also, and who is a distinguished lecturer, of course, and of course he has already established many more chapters in the southern part of India. And I would like to ask Professor Daya Sagar to say a few things that the journey of the geosocial technologies, particularly the GRSS, as a community and all thing, and that's what I would like to request him. Professor Daya Sagar, please, sir.
Yeah, so it's nice to see all of you, and I know everyone by name, and I could see several people here. And yeah, so mostly in India, so as someone was telling, more than geosense and remote sensing, our emphasis is more on geospatial technologies. And this is what I remember our good friend Dr. Paul Rosen was telling. And mostly India, I believe more than 70% of the members are paying more attention on geospatial technologies. Yeah, what is wrong in that? And so there was some proposal in GRSS to start one IEEE transactions on geospatial science. But unfortunately, they have taken a lot of feedback from members, but they didn't eventually launch that particular transactions. I think we should also try once again, and so to tell people, and we are the one of the largest groups in GRSS. The country is now having more than 800 members, and so to tell that, you see, GRSS is growing and becoming more popular. How it was in 2012, there was no single chapter here. There were hardly a few members, not more than 10 across India. Now coming to this level, it's a long way. And so seeing these programs, one way, online programs have increased the one is productivity and efficiency. Now, so we are all giving lectures round the clock. Some countries, they are telling they fix up some lecture at 8 o'clock in the night. So we don't know how to say no when somebody is asking us to give a talk. So it's always enjoyable, though we talk the same thing, but we expect different questions. And so that's where we have to keep on giving talks, and that's a wonderful outreach program. And those who are not members of GRSS, and I would request all of them to become members. If they are already IEEE members, and taking GRSS membership is not that big a burden. I think just think about it, and then so yeah, let me congratulate. So as GRSS Mumbai chapter is doing so good, and I think these are like back-to-back programs, and Professor Sangeeta is also organizing that is computational intelligence and remote sensing. And so she also invited me, and probably I'll talk the same thing, but it is like, though there is repetition, but it would be nice if there is a kind of more interaction. And if people can, ask questions, but how to make that possible through online lectures is still a question. But had we been in, to give in-person talks, that would be nice. And I gave several talks, in-person talks, both in IIT Mumbai and IIT Kharagpur and IISc. And the kind of question they ask, actually, they are very challenging questions. And for the speakers, it's also a kind of learning process from the questions that we get from the audience. And so what is there anything that you expect, Amir, that I have to focus talk specifically on something?
No, Professor. That was in general only. That's what.
Yeah. So enjoy doing it, and so this is also another thing. Out of so many chapters are the IEEE societies and councils, and GRSS is doing so well, and we are about, I believe, 6,000 members across the globe.
Yes.
Close to 6,000. I think it is slightly lesser than that.
Yes.
Out of which 800 from India. And so we should make sure that this number is maintained, and how to maintain that and show the benefits to the members. One is through organizing some good lectures and this kind of events. But it is always good if things improve. We should meet at some place. It is not just in-person talks. We should meet at different places. Like now we have 8 or 9 chapters.
Yes.
And I think all chapter chairs, if you all decide, and probably yearly one chapter should organize one in-person conference or a symposium. Like INGARS is one of the things.
Yes, yes.
And we can also think parallelly. See, INGARS probably gets some support from GRSS.
Yes.
But even without having support, our institutional support is fairly sufficient. We can organize events as long as the audience and participants can bear their expenses. But we can always try arranging their accommodation, because our gathering in any kind of school or conference would be 50 to 100 people. And say our institute is a small institute in Indian Statistical Institute. We organize so many events, and typically why we have started this chapter is to have IEEE GRSS distinguished lecturers. To have an eligibility to invite the IEEE DL, we have to have a chapter. That's how we have, that was the motivation for us to put the petition. Those days putting petition and getting it approved is a laborious process. It was almost 8 months we were struggling to have the signatures, physical signatures on the petition form. Eventually subsequently we got several IEEE DLs. And now IEEE DLs, now all DLs, and everybody is giving talks.
Yes.
Because of online mode. And so offline mode, if they come here, actually that would be very beneficial for young students and researchers. And they can interact with them, and they have many of them, they have a lot of opportunities for Indian students and researchers. I think that we have to think about it, and keep inviting not just Indians to give talks. call, foreigners, and now everybody will, they agree as long as they have some free time.
Yes.
And
Yes.
put some 4-5 foreign speakers.
Yes.
And I'm sure if you, I don't know whether you're familiar about IEEE Brazilian chapter.
Yes.
And their young group, along with ISPRS group, they organized a kind of school, summer school, and which is in a staggered manner. And so they give 2 or 3 lectures in each month. And it started somewhere in August and it is going to end on 9th December.
Yes.
And I have seen all out of 5 DLs, I think 3 DLs, they have given talks. I have given my own talk, and then Carlos has given his talk. Though it is the same thing, but having good interaction with people, we don't know suddenly where from the young guys get opportunities. And so there is other thing, and we all know that IGRS, we could bid for it, but we missed it. Someone was telling because some members, crucial members, they were worried about COVID, and they felt that Australia is a better place.
Okay.
So that's what I had from Professor Bill Emery. He told me, oh, it's just because of COVID. Otherwise, our proposal was very strong. So let us be very, very alert, and then we will bid for 2028 again.
Yes.
I think all of you should help us there.
Yes.
So though I will become another 3-4 years old, but we should bid for IGRS 2028.
Yes.
Again. And but IGRS 2022, I am not sure any one of you are attending. So that is being
Malaysia
hosted by my former colleagues. I worked in the same place in Malaysia. My immediate boss was Professor Chua Hintek, and he is the general chair for IGRS 2022. And all other people, they all are my wonderful colleagues. So with all that, I think let us keep in touch. Anything you inform us, any problems, and sometimes students will have problems writing papers. I think other education also, there were some I think yesterday, I believe,
yes,
weekend,
there was a program.
so I could not attend because my PhD students Viva was to be arranged. I could not attend, but those things, keep attending.
Yes.
And so if some youngsters, they face problems, paying PACE charges, which is used for them. But look for a rich researcher in the sense who has money. The sense sometimes we can use our project money. And so work with that people. I'm sure in the IIT Mumbai, you have many people. And if you have great work, approach a researcher, whether you tell frankly, I want to have a paper in IEEE JSTARS, IEEE GRSL, or IEEE TGRS. Everywhere you have to put a lot of money once it is accepted. And so that is it's a burden, but it's not too difficult now. And some professors, they have additional grants. I think this is the message for the youngsters. And we can also talk about our IEEE India GRSS license is Dr. Shivamohan. And we can always put a proposal. And I think unless we propose something to Dr. Shivamohan, he may not put it at the ADCOM, GRSS ADCOM.
Yes.
So any publication PACE charges thing, just because of money, our great work not appearing in IEEE GRSS journals and transaction, I feel that is a kind of thing that we are getting deprived. And we have great works, but because of money, we are unable to publish there. I think AMIA, you have to raise this issue, and we will talk to GRSS chapter chairs. I think there should be a solution. Sometimes, there are some philanthropists and they may come forward. We can have a kind of trust and we'll put money. And I remember 30 years ago when I have a paper accepted for geophysical research letters, I went to my college principal, that was College of Engineering, Andhra University. He said, I have money, but by paying you for your publication, what does this institute get? And that's what was the response from. That was horrible. But now we know, and if somebody has great work, I think we should see getting those space charges sponsored should not be a burden. And we have to think about it. A kind of trust we have to open. And so some philanthropists, if they pay money, we can ourselves, sponsor, not fully, at least partially. So 5,000, 10,000 rupees individually, and growing that money and helping a few others to have their publications in GRSL and TGRS. This is where if somebody tells that Indians are not publishing in our IEEE journals, transactions and letters, and I don't agree that. And so we have a lot of talent. And a lot of talent. You look at any IEEE journal or transaction, out of 10 papers, the 7-8 papers are from China. Because they have that incentives and support they are getting. But we can also do it. And so, but somewhere somebody should initiate. And please talk to other chapter chairs. I think a kind of memorandum we can prepare and we can put it to ADCOM. See, whenever there is a special issue, one special issue came in 2017, which Avik, me, and Paul Rosen and Lorenzo have edited, specifically meant for IEEE India remote sensing.
This one I will take in the chapter chairs meetings come at that time. I will
take it, and then for that they have actually waived the page charges. But now asking them to waive the page charges is no use, because it's money for them, and then they are getting the money what they are expecting. But for we Indians, what to do, and we will raise this issue and just put this. And I'll also talk to Professor Ramarao. And Ramaro's voice, always is very loud and clear.
High pitch voice.
Then we will help young researchers. But keep working for getting good results. And
so one suggestion you want to give to our audience?
Which one?
Any suggestion you want to give?
Suggestion is no. Do great work and aim for the best journals. Don't look for quick publications. And so nothing wrong if your paper is rejected 5 or 10 times. Nothing will happen. But that would get you more stamina. So I always used to tell that editors and reviewers, sometimes they spoil our work, but don't get dejected or disheartened. But keep trying, and that's how my IEEE TPAM paper was asked for revision 7 times. But it's not just the brilliance and intelligence. It's at the end of the day, your perseverance is more important. I think these are all, I think, 2 big words for youngsters, but they speak better than, oldies like me. But just take it to heart and keep working, publish in great journals. That would get you a lot of visibility.
Thank you, sir.
Yes.
Rejo, anything?
The feedback form is shared in the chat of the meeting, so everyone is requested to fill that as well.
And now you announce that awards.
Yes.
Oh, so there are awards. Okay. Sorry, I took long time. I think people are waiting for awards. Yeah. Please go ahead. Yes.
So yeah, moving for the much awaited awards, the results of the student presentations. So we'll start with the 3rd prize. Screen visible, Aiden?
Yes, Ganesh.
So moving with the 3rd prize first. So the 3rd prize goes to a novel technique for spectral reduction in SAR images for evaluating classification accuracy by Vijal Jain from Usha Mittal Institute of Technology, SNDT University.
Thank you so much.
A great round of applause for her and for the amazing presentation that she gave. Moving on to the 2nd prize. The 2nd prize goes to optimized shelter accommodation by Athira Lonapan, Esther Fernandez, and Jovinci Prince from Don Bosco Institute of Technology. A great round of applause for them as well.
Thank you so much.
And the much awaited, the first prize. The first prize goes to Decision Support System for Groundwater Governance by Tayyabili Sayed from Don Bosco Institute of Technology, Mumbai. The prizes for these awards are, just a minute. The first prize gets a cash prize of 4,000 rupees. The second prize gets a cash award of 3,000 rupees. And the third prize gets a cash award of 2,000 rupees. Congratulations to all the winners for the amazing presentations and the great work.
From audience, any would like to share anything? Dr. Mirza, are you there? Anyone? Bina? Or anyone want to say something on this in these sessions? Bijal, you would like to say something? Bijal Jain.
Yeah. Thank you so much for the opportunity, and it was a really great session. Like the 2-day symposium was very informative, and I really liked all the sessions. So thank you, everyone.
Thank you.
I'd also like to thank the IEEE GRSS Bombay Chapter for giving us this opportunity and considering giving us a platform to showcase our work, and Dr. Amya sir for mentoring us throughout the project, and also the DBIT faculty for being a constant support and giving us feedback and improving, and also for the entire informative talks that we had over the 2 days. Thank you so much.
Okay, so now it's, I think, formally we have to come to the end of the session. Probably, Dr. Sangeeta, can you please follow it? Sangeeta Chaudhary, madam.
Yeah. Thank you, sir. Very good evening to one and all present over here. On behalf of IEEE GRSS Bombay Chapter, it is my privilege to extend a very hearty vote of thanks. First and foremost, I would like to express our deep sense of gratitude to Dr. B.S. Dayasagar sir for accepting our invitation on short notice and being over here in the concluding session despite of his busy schedule. Thank you very much, sir. Special words of praise and thanks to our mentor and founding chairman of IEEE GRSS Bombay Chapter, Dr. Avik Bhattacharya, for always being a source of inspiration and being the backbone of all the activities of GRSS chapter. Thank you so much, sir. I would like to take this opportunity to thank IEEE GRSS officials for accepting our proposal and granting us the funds for organizing this symposium. Let me express my sincere thanks to IEEE GRSS Kolkata chapter office bearers for collaborating with us and actively involving in planning and execution of this symposium. I would like to thank IEEE Bombay section for always supporting and helping us in every aspect in organizing events which we are planning throughout the years. We are very grateful to the partnering institutes, associated institutes. So we are grateful to Don Bosco Institute of Technology, Mumbai, Ramrao Adik Institute of Technology, Nerul, SNDT Women's University, Mumbai, Amity University, Mumbai, and Milia Art Science Management Science College, Beed, for always supporting IEEE GRSS Bombay chapter. I must mention our deep sense of appreciation to all our national and international speakers and panelists from industry and academia for sharing their knowledge in the field of geospatial intelligence. It was indeed a feast of knowledge for all the participants as well as for us in these 2 days of symposium. Let us be grateful to the person who always led by example. I would like to thank Dr. Amiya Tripathi, Chairman, IEEE GRSS Bombay Chapter, for his keen interest, guidance, and his active involvement to make this symposium a reality. I would like to thank all office bearers of IEEE GRSS Bombay Chapter, Dr. Sanjay Shitore, Dr. Shafiuddin Sir, Dr. Ujjwala, Dr. Sangeeta, Dr. Magar, who are actually involved in all the activities of this symposium. I would like to thank all of them for giving the suggestions time to time in the planning as well as their active involvement in the symposium. No event could be complete without enthusiastic and dynamic volunteers. I take this opportunity to thank to DBIT faculty, Professor Imran Mirza and Dr. Firoz Sheikh, and DBIT student volunteers, Grejo, Hayden, Crizel, Athira, and their team, which includes Grace, Lebisha, Noel, Riha, Sarah, Smriti, Siddharth, Tiffany, Alvina, and Mansi for their sincere efforts to plan and execute all the sessions in symposium. My special thanks to Grejo and Hayden and DBIT faculty coordinators, Mrs. Ditti Verghese and Mrs. Dipali Gainde, who are working around the clock behind the scene, and they have done lots of work, and you can see the results in this 2 day symposium. So thank you all from DBIT ACM Student Committee and the professors. My heartfelt thanks to all the participants for actively participating in this 2 days Geospatial Symposium. Also, I would like to thank all the participants who have actively presented their work in the presentation slot, and actually very diverse fields on various diverse fields, and they try to showcase their research. Not only the research scholars, but even UG students have participated. So that is one of the achievement of this event, I must say. Finally, I would like to thank each one of the person who is directly or indirectly involved in this symposium. So thank you one and all who have joined the online concluding ceremony. I would also like to thank Jaya ma'am. She was there in the concluding ceremony. So thank you ma'am for staying back after your session. So thank you one and all, and we will be doing such events, many such events in future also. So hoping your participation in all such events in future as well. Thank you very much. Thank you all. Over to Grejo.
Thank you, ma'am, for your wonderful words. Sir, we'll have a photo with everyone.
Yes.
Everyone who can start the cameras, please do so. We'll have a pic taken. All the participants, the team, everyone can start their cameras.
You have to say 1, 2, 3 now, then otherwise they will already how they will come to know.
Yes, yeah. Waiting for everyone to turn on the camera.
Yeah. In one frame it won't come, you have to take 2 frames, it seems.
Yes, sir, we'll do that.
Yeah, quick. You have to say something, is it done or not? How do you come to know?
Still people are turning on. So I'll take the pic.
Yeah. Multiple pics required. Yes.
Yes, sir.
Countdown.
3, 2, 1. Yes.
Thank
you so much.
Thank you.
Thank you all.
Thank you so much, everyone. You all were a wonderful audience throughout the 2 days. We had a really good event.
Thank you, sir. Daya Sagar, sir. Thank you very much. Right. We'll meet again for some other things over there.
Okay. Bye-bye.
Yeah.
Bye, everybody.
Thank you, sir, and see you in the next week.
Yeah, sure.
Yeah.
Okay.
Thank
you, sir.
Yeah, thank you.
Thank you.